All right, awesome. Thank you so much. So thank you everyone for joining today. Welcome to the hands-on bootcamp in computer vision. I have a very specific agenda in this bootcamp, which I will mention what exactly we will be covering in this bootcamp. Who is this meant for? What can you expect to get out of this, etc. So before that, let's spend a little bit of time. I can introduce myself a little bit. My name is Sridhar Panat. I am one of the co-founders of Vizuara AI Labs. So my education was from IIT Madras in 2012 to 2017. And after graduation, I went to MIT for my PhD. So that was from 2017 to 2022 for 5 years. And then after graduation, so my PhD was mostly in interfacial engineering, little bit of electrical engineering, little bit of machine learning, robotics. So it was like an interdisciplinary field of many different things. And I had a lot of fun time during my PhD. But after that, or I would say slightly before that, we ended up working together, Raj, Rajat, and myself. You might be familiar with them through LinkedIn or our YouTube channel. So we decided to start Vizuara to basically do many things in the AI domain. If you are interested, you can check out this video. This is a 3-minute video of my PhD thesis work, which was published on
located in desert region
MIT's YouTube channel. It has almost 300,000 views now. So my basic work was to build a self-cleaning solar panel, which can remove dust and clean itself and recover almost 95 to 98% of lost power output. Because when dust is accumulating on solar panels, which is very likely in desert settings, it can drop the efficiency significantly. So this was like a waterless electrostatic self-cleaning robotic system. So it can clean it can clean solar panels without having the need for a single drop of water. The interesting thing was, while working on this project, inadvertently machine learning entered the picture, because there was something called as dust removal voltage. So dust removal voltage was how much voltage per centimeter do you have to apply to charge and repel a particular particle of, let's say, 30 microns in size or 50 microns. There are particles of different sizes. So this dust removal voltage was completely dependent on the particle size. Now, how do you know the particle size? You don't know, right? You can't take a microscope and check the particle size in every single region of a solar panel. So what is a sensible thing to do? So I purchased a very cheap camera, which could get 50x to 100x magnification. So it was not as good as a proper microscope, but it could magnify a little bit and give me like thousands of dust particles in one single frame. Now, from this single frame, I wanted to get a dust particle size distribution, especially its mean and standard deviation, so that I know that, okay, most particles are in this size bucket, so that the dust removal voltage could be applied, whether it is 10 kilovolt, 12 kilovolt, 15 kilovolt, whatever that is. And how would you do this? Are you going to count? Are you going to fit circles around every single particle and measure the average size distribution? No, you won't be doing that. Here is where machine learning enters the picture, especially computer vision. So I implemented a convolutional neural network, which could real-time process the images coming through camera. And then this can classify the dust particle sizes into different buckets. So 30 micron bucket, 50 micron bucket, etc. And based on that, my autonomous solar panel cleaner could decide what voltage to apply. So this was an interesting use case of computer vision, or specifically deep learning in computer vision, for a complete hands-on physical experimental setup and a product. So I just wanted to share this with you because I'm pretty sure that people in this call will have background not just in computer science. I'm sure you are from different backgrounds like mechanical engineering. Some of you might be from computer science. Some of you might be from totally different, not even engineering background, right? And you might be wondering, why is deep learning, computer vision with deep learning relevant to you? It's relevant because I just wanted to show you this example to show you the relevance, but it's anyway relevant because the field of computer vision has penetrated into various domains in various industries. I will show you in today's lecture some of the example industries. So this was just my introduction. And I'll also mention one more small story of how what was one of my initial research attempts at traditional computer vision. So this was more than 10 years ago when I was an undergraduate student. So we were working on a problem for classifying rice grains. So if you have a bunch of rice grains on a surface, there are many different varieties. There is basmati rice, jasmine rice, ponni, idli rice, and there are many dozens of varieties of rice grains. On an average, these grains have an average size. There is a distribution, but sizes differ based on what rice grain variety it is. And there are many configurations in which rice grains could be on a surface. Sometimes it could be sparse. It could be distributed such that there are only few grains on a surface on any image, right? Or they could be on a heap. So there are many rice grains touching each other. So at that time, although deep learning had slightly entered into the scene, thanks to AlexNet, which we will discuss a little bit, the traditional computer vision approaches, which had nothing to do with deep learning, was still prominent. So what were we trying to do? We were trying to do something like ellipse fitting. So let's say you have a rice grain that looks like this. These are actually in the image when you perform some kind of thresholding. So when you convert an image into pure black or pure white image, you may notice features, shapes like this, which are not representative of an actual rice grain. So what could be happening? What could be happening is two rice grains are touching each other. So you have to first figure out under what conditions, what is an algorithm which can detect when two rice grains are touching, because their outline will be just one single shape, and then split those shapes into two different shapes, find the center of mass or center of geometry of those shapes and fit ellipses, then calculate the length and the breadth of this ellipse, and then plot this size distribution such that this could be the longer axis, let's say B, and this could be the shorter axis, or vice versa. And then what will happen is rice grains of similar varieties, let's say idli rice, may be distributed here, and then maybe another variety of rice may be distributed here. So this was a pure traditional computer vision approach, which had nothing to do with deep learning. Neural networks were not even in the picture. But this could have been done with neural networks also, right? As we famously know now. But the good thing is this paper got us a really good exposure into various techniques that were happening in machine vision and computer vision at that time. This work was accepted into the 9th International Conference on Machine Vision, which happened in Nice in France. And it was very clear to us when we presented our work in that conference that the research community is entirely going to shift in the near future into deep learning based approaches for computer vision. Nobody is going to work on hand engineered features. And this major shift I was so lucky to experience this major shift almost in real time. Of course, there were other shifts that had already happened in more, deep communities in computer vision or in computer science. So AlexNet was the paper which came out in 2012 that showed for the first time that, and this was in 2012, and this paper showed for the first time that you could use deep neural networks for training on large data sets of images. And they even used GPU for training. So it showed for the first time that you can leverage parallel computing to make everything faster. And if you look at the NVIDIA's stock, right, the rise of NVIDIA's stock, everything, it can't be attributed to one single event, but if it can be, then this would be one of those events. The proposition of AlexNet. So Alex was the name of the first author of the paper. Then there was Professor Geoffrey Hinton, who won Nobel Prize in physics for his work in neural networks. This was in 2024. And Ilya Sutskever was also there. He's one of the founders of OpenAI. So this all was happening in 2012. And then people had gradually started to eliminate hand engineered features from their work. So how does hand engineered features work? Because we know that in convolutional neural networks, they use something called as convolution filters. So filters are important. It is just that humans do not define the filter values. It is learned in the process of deep learning. So it's learned during back propagation. So, but before that, what exactly is this filter doing to an image? If you had an image and if you had a filter, what exactly happens to this image? We should spend some time on that. So just keep in your mind the two types of systems. First one is rule-based, where in my case, I was manually meaning I was writing an algorithm which could measure the length and breadth of the grains. And then I was using that length and breadth to predict the category of that rice grain, right? But in deep learning, you won't do that. You are simply feeding the image to a deep neural network, and all the features that the neural network has to learn to make a prediction will be learned automatically. If the feature includes the color, that will be learned. If the feature includes the textures that is present in the rice grains, that will be learned, right? So features are there. The only thing is it is not hand engineered. It is automatically learned during the process of training. So this course, I would say 90% of this course will be dedicated to deep learning approaches in machine vision or in computer vision, because that is what is most sensible for us to do. So if you think of bunch of tasks which you may have seen people implement using computer vision approaches, the classification is the easiest one, right? I'm sure all of you have played a little bit with CNNs for MNIST image classification for handwritten images, or cat versus dog classification. So this is the easiest thing to do. How many of you have heard of this website called Teachable Machine? So this is by Google. So if you want to build a convolutional neural network, I mean, not build, you can upload images and you can build a CNN to make predictions here. So just to get a flavor of how the training works. So it has become such an easy task now that classifying images is not at all difficult, provided there is sufficient diversity in the data. But there might be tasks that you have seen, like object detection. What is this? You draw bounding rectangles, something like this. So classification would be something where you have an image, you are trying to classify the entire image into whether it's a cat or whether it's a dog. So like a two-class classification. But in object detection, you are not classifying just the image. You are trying to identify an object in the image, and you will draw like a bounding rectangle. And this bounding rectangle is characterized by its, I would say, this left-hand side top corner, its width and its height. So if you know those four parameters, x coordinate of this point, y coordinate of the point, width and height, you know where the rectangle is. And whatever is there in the rectangle, you can classify whether it's a cat or dog or whatever. So these are called object detection. Then there are other tasks, which is semantic segmentation. So semantic segmentation is not about drawing bounding rectangles. So if you were doing just object detection, you would draw a bounding rectangle around this person, right? And you will generally say that the person is found inside this bounding rectangle. But there are techniques such as UNet, which we will be discussing in today's in this bootcamp, where you can perform semantic segmentation, where the contours of the object itself is captured, not like just a bounding rectangle proposition. So these techniques we'll be learning because these are very industry relevant. Then there are techniques which can help you with tracking objects. So tracking objects means if you have a video, in the video, let's say you have a CCTV footage where people are walking. And if a person is walking, in one frame, the person is in one location. In another frame, the same person might have reached another location in the image. How do you know it is the same person? You have to somehow figure out a way to track that, okay, this person has an ID. So let's say ID of this person is 233. So you draw a bounding rectangle and that bounding rectangle has an ID. And then when the person walks and reaches another point, so let's say the person is now here after like 5 seconds, then the bounding rectangle will be again drawn here through object tracking. But somehow you have to be also, you should be able to assign the same ID. That's how you know that you have tracked the same person when the person walked from place A to place B. So these are techniques called object tracking, which we'll be see again in this course. There are techniques for counting objects. Counting meaning if you have a conveyor belt through which things are moving, then you can count how many objects pass through the frame. If you are having a CCTV camera in a traffic signal junction, then you can count the number of cars that have passed through. And this may help you devise traffic signals in such a way that roads that experience too much traffic should probably be given the green signal for more time. So when I go home from here in my office, usually the route I take has only 30 seconds of green signal, and then you have to wait for 150 seconds for you to pass through. On the other hand, if it's through the main road, the signal is on for around 120 seconds and you have to wait only for 30 seconds. So how do people come up with these decisions? Because these are numbers, right? You quantify certain things and you take certain decisions, and computer vision comes into picture in such applications. There are applications where you might want to estimate the pose of a human. So a human has a shape. There are nodes like this. There are edges like this. And you want to figure out how the person is moving, and you want to fit a posture or pose in real time to a person's movement. This might be helpful in sports, in martial arts, in many settings where fast, dynamic human movement is involved. And then there are classic computer vision techniques, which we will briefly discuss today, which will help you identify the outer edges of an object, the top edges of an object, the corner edges of an object, etc. And at the end of the day, in an industry, you have to implement whatever method you have to implement it in a pipeline. So this pipeline also we will learn how to build. And for that, we will be using a platform called Roboflow. So this pipeline will consist of model, data set, model, training the model or using pre-trained model, and then deploying it so that it is real time, it's live on a website or on an application. So what all techniques are we going to cover in this bootcamp? Let me just scroll back up. So in today's lecture, our primary focus is OpenCV. OpenCV is by far the most popular computer vision library. If you are a person who is serious about computer vision, you must spend time on OpenCV. The second part of the bootcamp will be about RCNN, region CNN. So it's a technique for object detection. Then we will learn about UNet, which I showed you earlier for semantic segmentation of images. So contours can be extracted. And then I would say YOLO might be the most popular model among all these in today's world. So there is a very modern method called YOLO V8, using which you can perform very fast real-time object detection. And finally, we will see how many of these different models can be deployed for an actual real-life application in the Roboflow platform. So that will be a very, and one more thing is, whenever we are implementing all these frameworks, we will obviously be using OpenCV there also, but we will initially have a brief introduction to OpenCV before we go into these different architectures. So each architecture I am splitting into two parts. In the first part, I'll be covering the theory. What exactly is this architecture? How did people come up with it? We will try to code it as much from scratch. We won't be coding entirely from scratch, but we will try to do it as much as possible. And then we will try to train a data set for a particular application. And that's how we'll get hands-on experience. So I want all of you to be able to code along with me during the lectures. And the setup required for that, I'll be explaining how to do it today in today's lecture. So this is the rough outline of what we will be covering in this bootcamp, right? So here are some logistics in case you are not aware of. So we'll be meeting for 5 weeks. All the lectures will be live. We'll meet 2 times a week, first on Monday and next on Thursday. And the timing will be 2 to 3:30 p.m. IST. So that is about the lecture schedule. And there are 2 types of people in the program. There are people who are part of the free plan, people who are part of the pro plan. So for free people, the lecture videos and the basic code material, which we'll be discussing in the lecture, will be available. And the rest of the things will be available for the people who are enrolled in the pro, which will include GitHub repo, Discord community, certificate, a hands-on CV book, which we are currently writing as we speak, and all the other things, including handwritten notes, assignments, etc. So just check it out if anybody is interested. And with that, I think, yeah, one more thing which I wanted to mention, because in this month of August, we have actually 3 bootcamps running, and many people had asked, like, if they want to attend everything, what is the best idea? So we have thought of bundling this into one single thing. So there are 3 bootcamps. One is this hands-on computer vision. There is another bootcamp on reinforcement learning, which started last week. So it will be for 8 weeks, taught by Dr. Rajat from our team. And Dr. Raj is teaching build SLM from scratch, small language model from scratch, which starts from August 9th onwards, which is this Friday, I guess, right? Friday, sorry, this Saturday. So just check it out. There is a 3-in-1 bootcamp link. You might want to see if this is something that you are interested in or not. So I will share the link to this website here in the chat. So Jayadeep has asked a question. What about a DTR method? So basically, we'll not be covering transformer-based approaches in the current bootcamp. That is not part of the agenda. Although I would like to teach vision transformers and other attention mechanism-based approaches, which also involves techniques like UNet embedded in it. But that I don't think that will be within the scope of the current bootcamp. All right. So now that being said, what all have you heard of computer vision? Whatever it is, in general, I can make a blanket statement that whatever we have heard is just the tip of the iceberg in computer vision, because usually we are exposed to solutions for customer facing problems or computer vision implemented in customer facing applications. So what is a customer facing application? Maybe you may have seen of some KYC, know your customer thing done automatically using some face recognition. You may have seen Digiyatra, which still does not work very well, but in many airports, it's getting implemented. It has computer vision embedded in it. You have your maybe iPhone unlock feature, which again includes computer vision. But these are applications where you as a customer is directly getting exposed to. And what you see as a customer is, I would say, a very, very small fraction of all the industrial applications that is out there for computer vision. There are many things happening in the backend, which most likely we will never get exposed to in the computer vision domain, right? So I just wanted to lay this out there just so that you are aware of the fact that there are many other applications. Now, these are some domains in which you can, in some of these applications, you are finding it easy to imagine how computer vision is coming to picture. So if you think of healthcare, I know personally know some companies who are building simple solutions for robotic assisted surgery, where the robot is primarily guided. I mean, it has a lot of sensors and probes, but at the end of the day, vision systems are one of the major part of these robotic surgical systems. Self-driving cars, needless to say, you're already aware of this. But then there are many other applications, like in manufacturing processes. If there are computer vision applications going on, you will never get exposed to it because you will only get exposed to the final product. You will have no idea what people are doing using computer vision, quality control, or inspecting the assembly line, what's happening in the assembly line, etc. In fact, 2 of my friends are running 2 separate companies. One company is in the physical security space, another company is in the industrial automation space. Both of them are heavily using computer vision systems. So one is for CCTV surveillance in airports, in general public spaces, or even private spaces. Let's say you are running a business, a physical center, or a store, like a grocery store. How would you ensure physical safety? What kind of computer vision systems can you implement to alert you of any security threats that's happening? So one of the projects that we are going to implement today in today's lecture is like a burglar detection system. We will code it from scratch using OpenCV. We will not be even using any complex deep learning techniques yet, but you will see how beautifully it works. So we will get to that in the last part of today's lecture. But there are countless number of applications. There is one of another friend of mine who's running an agricultural technology company. And in that company, what they're trying to do is they're quantifying how much pesticide, when you are spraying pesticide, how much of it is actually ending up on the plant. Because if you won't quantify that, the problem is you will almost always end up overspraying. And what happens to this oversprayed chemicals? It will, at the end of the day, it will reach inside your body or inside some animal's body, which is not good for you or the environment. So there are computer vision applications in almost every domain. You may have heard of this company called Blue River Technologies. So this is a company based in the US, and they got acquired for almost $300 million or something by another big agricultural equipment company. And what they were doing was they had a thing for, they have these sprayers, right? So there are so many mini sprayers equipped by cameras, and these cameras were activated. I mean, these sprayers were activated only if a crop with weed is detected. Otherwise, it won't be spraying. So this was tested on a specific type of crop, I think lettuce or something, lettuce or cabbage or something. And then they showed the proof of concept of how it works. And yeah, I think they were acquired by John Deere, this company, which is like I think they're $100 billion company. So there are many such applications. So as a customer, you are just eating the food, but before the food reaches your plate, it has already gone through a bunch of computer vision applications. Last year, I think this was in 2024 or early 2025. I forgot the timeline, but you might have seen this back and forth happening between Jan LeCun and Elon Musk. So Elon was saying, we don't use CNNs, to be honest, these days in their fully self-driving. So FSD means fully self-driving cars. But then Jan was asking, okay, if you don't use convolutional neural network, how exactly are you saying your real-time camera processing works in self-driving cars? So this was an interesting series of tweets you could follow. And of course, this was the same time when terms like vision transformer became popular in not in the scientific community, but among the general public to some extent. So we'll start the lecture with OpenCV. But before that, I want to show you one video, just in case any of you haven't watched this.
So I'm currently in Los Angeles. Actually got invited out here by...
Can you see the video? Can you just, I just made it full screen. Just wanted to ensure that you guys can see the video. Okay, sure.
Waymo to come.
So I'll just show you. So this is Waymo, another big company. So basically it works like Uber, right? So you have an app, you call the taxi and taxi arrives, and this has no driver. This is actually there in Chicago and various other parts of the US. So one of my friends who recently went for a conference there, he actually went in a Waymo taxi. There is actually no driver. It's crazy. Like it feels like we are living in the future. Although this has been coming, like for the past 10 years, we have been hearing fully self-driving car, self-driving taxi, self-driving buses, but now it has become a reality in many parts of the world. And although while watching this in a video, it doesn't feel as amazing, but I can only imagine the excitement of the person who is actually sitting inside that feeling. And it can go pretty fast. It's very cool. It can go pretty fast. So, and how does this work? Of course, computer vision. I don't know what models they use. So I have spent a lot of time trying to exactly understand what all models do Tesla self-driving cars use. Most of it is proprietary, but they don't use one single model. They have a plethora of models for different tasks. So for object detection, they have one type of models. For classification, they have some other model. But these are still the tip of what is actually happening inside their algorithm. I don't think we'll never know what exactly happens. But one claim that Elon Musk has made, I think, is they also use vision transformer, right? So if vision transformer is being used, as Aravind is mentioning, it can have a mixture of experts instead of mixture of experts for text, mixture of experts for vision. And these cars are apparently safer than human drivers. They have tested it over many 100,000 plus kilometers, and then they have made only very little safety incidents. All right. So now let us get into the main part of today's lecture, which is OpenCV. So with this, we can get to our work. So OpenCV is a Python library mainly meant for processing images or videos, because videos are ultimately collection of frames. So we will spend our first two lectures, so today's lecture and next lecture, purely on OpenCV. Every single one of you will 100% sure end up using OpenCV, right? So this is what was happening in the scene of computer vision, as I mentioned earlier. Before roughly around 2010, people were using hand-engineered filters. So what is hand-engineered filters? It will look like a bunch of matrices. This is an example of a hand-engineered filter. You have a 3x3 matrix, and you have some numbers inside this matrix. And this matrix performs convolution operation on top of the images. And this will result in a output image, which may capture some features from the image. So for example, I have a picture, not this, but this is actually a picture of a girl with a hat. And if you apply a certain type of filter, see, it detects just the edges, the places where sudden transition in pixel values happening. So these are classical filters that are hand engineered. But then, as I mentioned, AlexNet in 2012 changed the entire scene. I don't expect you to understand how AlexNet works or even the architecture. That's not the point of this bootcamp. But just remember the name AlexNet. Just remember the year 2012, because it really marks a division between classical computer vision and deep learning guided computer vision. Now, let's spend a few minutes on these filters, right? And we will try to implement. So let's say this is your input image. And this input image is represented by pixel values. Let's say it's 0 and 1. So white pixels are 1s, black pixels are 0. So the pixel representation of this input image would look something like this, right? Now, if let's say you want to apply an edge detection filter, what does that mean? Where is the edge? First of all, the edge is here. This is the edge. And if you want to detect an edge, if you want to detect this edge, you are essentially applying a filter where you are seeing when the pixel values are changing from 1 to 0, 1 to 0, 1 to 0, right? So this is what you want to get. So if you apply some filter to the image, it will only highlight the edges. Everything else that is not an edge will not be highlighted. What does that mean? Everything that is not an edge will be black in color, as you see in this region, black color, this region, black color, and whatever is an edge will be highlighted in white color. And this may be represented like this. All the pixels in the exact middle are in values of 1. All the other pixels are of value 0. Now, how can you accomplish this? Let's see. So let's say we are using a filter like this: 0, -1, 0, -1, 4, -1, 0, -1, 0. So this is how you apply the filter. So I'm going to write it here: 0, -1, 0, -1, 4, -1, 0, -1, 0. Okay, so this is being applied. So the way it works is, you will, let's say the filter is overlapping with this set of 9 pixels. You will do 0 multiplied by 0 plus 0 multiplied by -1 plus 0 multiplied by 0 plus, like that you will do. And the resulting number, whatever that is, will be assigned to this pixel, this center pixel. So here, what will be the resulting number if you perform this operation? So if I perform this filter operation to this subset of images in the input image, the result will be 0, right? So here it will be 0. So this is the output image, by the way. The input was this. So I was supposed to write here, but here also, if the filter is, let me just bring the filter up here. Okay, so here what will be the output? The output is assigned to this center pixel, but what will that be? That will be 0 again, because whenever there is a 1, those are getting multiplied by -1, and those -1s are getting added up 4 times, right? And then -4 you will get, but then that is getting cancelled with this +4. So the pixel value of the output corresponding to this will be 0. So you are supposed to get 0, because output should be something that looks like this. But let's say my filter is somewhere here, over here. What would be the output? The output will be assigned here. And let's say I'm applying the filter and taking absolute value for simplicity. What would be the output? Let's take absolute value for simplicity. It'll be 1, right? And 1 will be assigned here. What if my filter is over here? What would be the output if my filter is here? Oh, sorry, I have selected 9 plus 3, 12, but let's say these 9. The output will be 4 minus 1 minus 1 minus 1. Again, it will be 1. So what this shows is if somehow I can have a filter that follows a certain logic, then I can use this filter to extract some relevant information from this from our image. Okay. Now what I'm going to do is let's all design a hand engineered filter. Instead of writing it mathematically, we will open a website. So I will share the link to this website in the chat. So just go to this website. Okay. And I will also share an image with you, which you can play with. So the image that we are going to use is this one. All right. So please use this image. And what we will do is go to the website, scroll down. In this section, you will see this choose file option. So here, choose the file and upload the image which you just took the screenshot of. Okay, so that image will appear here. All right. Now what I'm going to do is I will apply a filter which will detect just the top left edges. So top left edges means these edges. Okay. And I will use a certain logic. I will tell you the logic later, but I'm going to enter certain numbers here and you will see that the top left edges are getting highlighted. See, the top left edges got highlighted. So here I hand engineered a filter for this. Now let's say I want a filter for just identifying the bottom edges, no other edges, just the bottom edges. Then I will do something like this. See, now only the bottom edges. So here there is actually a very interesting logic which you can follow. Okay, so let me go back to the original configuration. So the original was, I guess, the original was something like this, right? Now imagine that these shapes are protruding outside. So this circle, square, triangle, diamond, those shapes are protruding outside the screen as solid objects. And imagine that there are light rays going from one location to another. The light rays should go from bottom to top if you want to illuminate the bottom edges. The light rays should go from top to bottom if you want to illuminate the top edges because they are protruding. Now consider negative numbers in the filter to be source of light ray and positive numbers to be destination. So basically imagine that light rays are going from negative numbers to positive numbers. Then your filter, let's say you want to detect the top edges, your filter should be designed in such a way that negative numbers are in general at the top. So at the top row, I will put -1, -1, -1. Middle row, I'll just put zeros. And the bottom row is 1, 1, 1. Then see, top edges are getting illuminated. So negative numbers are at the top, positive numbers are at the bottom. It's as if the light rays are going from top to bottom. And these light rays are now illuminating the object at the top edge, these protruding objects. It's just an analogy. There is nothing like this. I just made it up, but it works. Now, if you want to illuminate all the 4 edges, right? Let's say not just the top edge, not just the bottom edge, then how should light rays come? By the same analogy. If you want to illuminate all the edges, what should the light ray look like? It should come from all the directions, correct? So you want light rays to come from all the 4 directions to the center. So center is now the destination of the light ray. So center, I'll put some positive number, let's say 4 plus 4. And I could maybe say the corners, I could maybe put 0. It's not a problem. But these 4 numbers, I'll put negative, -1, -1, -1, -1. Now you see all the edges are getting illuminated. If you want to increase the brightness, I think what we can do is just double the numbers. Then the contrast will be increased, enhanced. So see, so what did we do here? We defined a human logic for designing a filter for detecting certain features. If the features of interest are edges, all the edges, then we can design the filter accordingly. If we only want some corners, we can design it accordingly. And like this, there are dozens of filters that people have developed over many years before deep learning. for detecting different patterns in the objects. And this was classical computer vision. But it works. It works for many, many cases, right? Today, what we are going to do is we will use a classical computer vision approach for a similar task. So before that, OpenCV, please know that it has huge number of downloads per week. So apparently the numbers are close to or above 5 million per week. It's crazy number. So OpenCV is by far the most popular computer vision library. They even have a website. So just check it out, OpenCV, this one. So they have bunch of courses also. If you're interested, just check it out. It's a great platform. But that being said, our goal is figuring out how to use it, right? So you can use OpenCV for many different tasks, for reading images from camera, from your computer, annotating on the images like drawings, or you could run object detection algorithms. So you could have had a deep learning model that is trained elsewhere, but you could perform inference using OpenCV on your system. So we will implement those in the next lecture, but today let's focus on a few things. So today what we are going to do is we'll read an image, we'll try to read video, perform basic image processing, and then at the end of the lecture, let's build a burglar alarm system, which is if, let's say, you have a CCTV camera, it's a live feed and it's in the indoor, okay, inside your house. Now, how do you know if, assuming nobody is there in your house, how do you know if a burglar has entered the house? You will know that when the camera feed has changed, if some changes have happened, it's a signal that something has moved in your camera feed. It could be an animal, it could be a person, maybe some object has fallen down, it could be anything, but it's an anomaly. It's an anomalous incident which you have to notice. So by the same logic, we will be implementing a computer vision system using OpenCV. But before all of that, we have to install a few things, okay? So I will be using VS Code for coding. So all of you, I recommend you to install VS Code, but if you use Anaconda or any other platform, it will be good. Google Colab will have some issues with respect to allowing camera access. So I won't recommend Google Colab for this particular bootcamp. I would recommend ideally VS Code. So VS Code is like an interface for programming in various different languages, and you can install it here. So I'm sharing the link. So as I'm speaking, just download VS Code for your computer. And don't worry if you have never used this, it's not an issue, but please have it ready, okay? So this is the first tool. It's available for Mac, Windows, whatever. Now, what else? Okay, next is Python. So go to Python website, go here and download whatever is the latest version. So you can download from this link. So go to Python website and download it. Then the last thing will be installing OpenCV. But before installing OpenCV, you should have your setup ready. So preferably VS Code, and you should definitely have Python, okay? So assuming that you will be doing this on the side, let me tell you how to install the OpenCV library once you set up your Python installation and once you have VS Code ready. So we'll be creating a virtual environment. So a virtual environment is something where all the libraries or all the packages that you are installing for this particular project, it won't be installed globally on your entire computer. It will be installed in a local environment in which you can play with. So it's a very good practice. So what I do is go to VS Code, okay? I will start from scratch so that you guys can also follow. Click maybe and go to your folder wherever you are having your folder to be installed. So keep a folder called hands-on computer vision for this entire bootcamp, and in that create subfolders so that you have everything stored in a systematic way. And here I can press Ctrl+O to open any particular folder. So I have a folder which I had created last week called Computer Vision Hands-on Bootcamp, in which bunch of things are there, but you can ignore all of this. I'll start from scratch. So this is how I can open the folder. So go to any folder, create an empty folder there named Computer Vision Bootcamp, and then open it using VS Code. When you open it, here, if you click the file button, you should see ideally all the files that are there in the folder. For you, there will be no files because you have not added anything yet. For me, you can see that there are some folders and files. Oh, you can only see Miro board. Thanks for letting me know. Let me stop sharing and reshare it again. Okay, did you guys see this Python website and everything? All those part was okay, right? Only when we started VS Code, you did not see, correct? Okay, awesome. And do you see VS Code right now? Okay, thanks for letting me know. So I'll repeat once again. So open VS Code and go to your downloads or wherever you want, or desktop or wherever you want to keep your folder for this particular bootcamp. So let's say here I create a new folder called I can name it as CV Bootcamp. Okay, and then go to VS Code, Control Open, Control O, and then you can go to that folder, navigate to that CV Bootcamp and open it. And this will open the blank folder on your computer, on your VS Code. One more additional thing which I want to ask you to do, which will help you tremendously, is installing Copilot. So VS Code has this thing called extensions. So click this extension. So this icon is extensions. And here search Copilot. And this will help you install the GitHub Copilot, which is like an AI coding assistant. Although we won't be using it extensively in the course, because here our purpose is learning, not just implementing. So we will try to not use it as much as possible. But when you are actually building your CV systems, when you have a Copilot, it will be very helpful. So I'll show you how this helps. So I have installed Copilot already. It's already activated in my computer, right? So now let's say I have this folder opened. Let me open my computer vision folder. Okay, so and here I just create a test.py. Okay. And my Copilot, you see this icon, that's the Copilot icon. I can just go here and then whatever code I want to, let's say here I'll say, write a hello world. Oh, there is actually one more level of automation which you can do. So I use this software called Whisperflow. I'll show you the website, Flow. So this is like a speech to text software and it's amazing. I'll show you how I usually use it. So if this is my VS Code here, I'm not typing, okay. I'm just pressing the function button on my keyboard I'll just say, write a simple code for writing hello world in Python and execute it. So I just said it and it converted into text to speech. So this is how you can do a lot of vibe coding. But anyways, do it with caution. So here what happens is this Copilot will write the code. So this is very similar to Cursor, right? You might have heard of Cursor for programming in like vibe coding. So this is pretty much the same. And here, if you want to implement this into your code, you just need to click this button. Then it will come here, like it's in your code. Or if you want to make changes, you can just say that. If you are encountering error, you can use it. So it's basically like using ChatGPT only, except here you are having it embedded into your IDE. And here you can see that there is GPT-4o. There are different models available for you to choose. So my default model is Cloud Sonnet 4. Anyways, I don't want to spend too much time on this, but I thought I will just let you know that such an option exists in case in future you're kind of bored with coding by hand. Okay, now let's come back to our main thing, which is installing OpenCV. So all you need to do is, this is the, or before installing OpenCV, we have to create a virtual environment, right? So this is the code for creating virtual environment. I'm just pasting it. Basically, this will create a, I would say, a localized space where you can install your libraries and run your code. So my virtual environment name is hands-on CV. So you can choose whatever. This is the name of the virtual environment, the hands_on_CV. You can put whatever name you wish to. Yes, you will have access to the recording. anyone who is wondering about that. And here, this line will activate that virtual environment. So you create a virtual environment and you activate it. And how do you know if your virtual environment is active? So here you see, I have this in the bracket, I have hands_on_CV. That is the name of my virtual environment, and it is active. So this is how I know that my virtual environment is active. Now, once this is ready, you are now ready to install OpenCV. And this is the code for installing OpenCV: pip install OpenCV-Python. So pip is like a package manager for Python. So whenever you are installing new packages, new Python libraries, you will use pip. So just use this code, pip install OpenCV Python. This should hopefully install OpenCV. I don't think you will encounter any error. Now, let's do some basic operations. Okay. So first we will do a little bit of image reading, image processing. We will try to annotate on a particular canvas. We will try to draw rectangles, etc. And then we will move on to accessing the camera feed or accessing the video, like a video on your computer. And then you will be able to implement a code for detecting burglar presence in your video. So we will build this entire project together in today's lecture. So, but before going into the project, I want to spend a little bit of time on OpenCV basics. Okay, so just open a new file. Can anyone mention in the chat if you guys are ready with your Python and VS Code? Yeah. So everybody will get access to the recording, so don't worry about that. Okay, so you guys are ready with VS Code and OpenCV. Did you install OpenCV? Okay, still installing. One error some of you might encounter while running some of the projects, not these ones, later, will be, it might show that NumPy is not installed. Usually NumPy is available, usually NumPy is already there on the computer, because if you have run basic Python projects, you might have already used NumPy. If you encounter that error, it's most likely because you have to downgrade the NumPy. So once we reach that stage, just remind me, like if you ever face the issue of NumPy not found or something like that, just let me know in the chat. But today, I don't think you will face that issue. And feel free to help others, like, because I'll be coding here on the side, but if your fellow classmates are encountering any issue in installing, just feel free to respond to them to help them. But here, let me open a new file. So I will say this file could be read under, or maybe I'll create a new folder called lecture 1. Inside this folder, I'll create a file, read_image.py. Okay. And then if you want to import OpenCV, this is what you can do. Import CV2. So this will import OpenCV. Of course, you have to have OpenCV installed first. And then for reading, you use cv2.imread of whatever is your file name. Okay, so whatever is your image name, .jpg or jpg, whatever it is, you have to write it here. So in my folder, in my present working directory, so if you want to know what is your present working directory, type pwd here. You will see the present working directory. My present working directory is computer vision hands-on bootcamp, which is this entire folder itself. So here I have a file called sridhar.jpeg. So all I can do is here I can put my file name sridhar.jpeg. And if I run the code, I have to assign also. So I will say img1 image1 equal to cv2.imread of sridhar.jpeg. Now, if I run this image will be read. Okay. Now, next step is the read image has to be displayed. So cv2.imshow of, and then here we can give some name to the displayed image, the original image. And then here we are displaying the image that we just read, which is img1. So here we will display, using imshow, we will display the read image. And one more thing is cv2.wait key of 0 for closing the image. So let me do one thing. Let me first of all close a bunch of these things and start from scratch. So see, this is the original image. So we just read an image from our file. The original image had a file name. Then we are providing a title and then we are just displaying it. And here, if we press escape key, the image will close. So I'll share the code here. So just check it out. Now, a simple thing which we can do is cv2.imWrite, which is writing an image. So we can save this image which we have opened as such, or we can modify and save. We can crop and save, we can annotate and save. But basically, at the end of the day, we can save it back into our computer with the name saved image, let's say saved underscore original underscore image.jpg. And what are we saying? Saving, we are saving this img1. Okay. So if I run this now, you should see a new file appearing here with this name, saved underscore original underscore image. So see this one. Where is my saved image? Yeah, saved underscore original underscore image. So basically we did the following. We opened an image, we just displayed an image and we saved it. Very basic operation, nothing fancy. So I don't want to spend too much time on this. Next is we can perform a little bit of processing of these images. So let me create a new file, which is named as image underscore processing.py. So here we will be opening an image and we will perform certain operations. So import cv2 for OpenCV, and then we will read the same image, img equal to cv2.read .imread of sridhar.jpg, and use whatever file name is there for you. Then what we can do is let's perform some operation, resizing, and then grayscale. Then we could do blurring. Then we could also do something like edge detection. That's it. So we want to do these following operations on the red image, and we want to maybe display those images. We don't want to save it. So resizing can be done like this, cv2.resize. So here, this cv2.resize will resize the image into a 640, 480 pixel image. Okay. And gray will be cv2.convert color. So cvt color of. So we are converting the color of the resized image. So we can convert the color of the resized image, or we can convert the color of the original image. So here I'll convert the color of the original image. So we are converting the color of original image. And what are we converting it to? We are doing color underscore BGR to gray. So BGR is same as RGB, but this image is following a different convention. It's not RGB format, it's BGR format. Then blurring equal to, let me just delete this automatic fill. cv2.Gaussian blur. And in Gaussian blur, I want to use the original image only. So img, comma, and now the blurring happens again using a filter. So you saw the filter for detecting edges. Here, blurring also can be done using a filter. So here we could use 5x5 filter. Actually, you know what? Let me use 2x2 filter first. And then let's display what it looks like. Then there is an edge detector called Canny edge detector. It's also a certain algorithm which involves usage of a specific type of filter. So cv2.canny. So Canny edge detector is actually very, very famous. We will be using it on img and 100, 200. Now let's try to display this cv2.imShow of all of these, right? So we have to show the resized image, we have to show the grayscale image, blurred image, we have to show the edges, and then we'll add a wait key for basically exiting. So exiting meaning we want to quit the image window and then destroy all windows. So this is not needed. Okay, so now if we run the code, hopefully it should show you the processed images. Let's see. Okay, I think let me go back to 5,5 and then let's see if it works. Yeah. So this is the edge detector. So canny edge detector worked. This is the blurred one. This is the grayscale image, and this is the resized image for 640 comma something, right? 480 or something. So now let us close this. Now what will happen if I change this to 15 comma 15? What do you think will happen? In the blurring, I just changed 15 comma, change it to 15 comma 15. It should ideally become an even more blurred image. You see, it's even more blurred now because now we are using a bigger filter. Similarly, we can do something like, so canny, I think somebody has asked a question, what is this 100 comma 200? I think it is something like this. You want to define a bounds for the pixel values. So I might be wrong, just do check this one. 100 comma 200 is the lower pixel bound and upper pixel bound, I guess. I forgot what it meant. Now, in the Gaussian blur, what if we keep this as 50 comma 50? Right? We can play with canny edge detector values also, then we will see. If this is 50 comma 50, then we will have extreme blurring, but here I'm facing some issue. Maybe let me go back. Okay. So can anyone mention in the chat how far along are you? Have you been able to implement some of this? I'll paste the code here. Have you been able to implement at least the first part of the code? Okay. Now let me run the code. Okay, so now let's play with canny edge detector. So I don't want to display these. Let's just do canny. So here I will say 0 and maybe 255, and let's see what happens. Then we can understand what the numbers are doing. All right, so here we go. So this is the canny edge detector with 0, 255. What if this was 0, 0? Yeah, so when this was 0, 0, it is detecting far too many edges. I guess, is it because are we reducing the threshold for what should be an edge? Something like that. Let me go to 255, 255. So when it is 255, 255, it's only detecting the absolute sure shot edges. When it is 0, 0, it is pretty much detecting all the edges. And when it is 100, 200, it's detecting something in between. Actually, you know what? Let's ask our Copilot. In canny, what happens if the arguments are 0, 0? Yeah, so all pixels will essentially become edges, loss of edge selectivity. So lower threshold. So yeah, so lower threshold is 0, upper threshold is 0. So I think it was not the threshold for pixel values. It was the threshold for gradient, I guess. So if there is a sharp gradient, how sharp the gradient should be. I think this 100 is a measure of the minimum sharpness of the gradient. 200 is the measure of maximum sharpness of the gradient. And how is a gradient defined? Gradient is the change in pixel values happening from one pixel to the next. Okay, so basic pixel manipulation, right? That was what this was. Now, let us do one more thing. We will implement a burglar alarm. Actually, before that, let me show you how to implement drawing or annotating on an image. So I'll create a new file called annotation.py. Okay. And annotation simply means we are drawing some shapes. You might have seen object detection almost always involves drawing rectangles on top of images. Rectangles are superimposed. So import CV2. Then here you will need NumPy. So import NumPy as NP. So if you don't have NumPy on your computer, just say pip install NumPy, I guess. Then we have to define a canvas. So canvas equal to numpy.0. So it'll be like black canvas. You define the size of the canvas. It could be 512 by 512, comma 3. So you have all the colors, comma data type equal to np.unsigned integer. So this will define a canvas in which we can draw. What can we draw? We can draw many things. We can draw shapes. We can put text. So we'll be using all of this in the burglar alarm detection. So we'll be using there how to read an image, how to annotate an image, and how to detect changes happening from in the pixel cluster from one frame to another. So here, actually, this code that I have in the recommendation is already looking perfect. Rectangle canvas, it has the 100, 100, 400, 400. Yeah, that looks fine. So CV2, we can start maybe with a line itself. So line is, we are drawing it on the canvas. And let's first display this. So CV2.imshow, and we will say canvas with shapes. And what are we displaying? We are displaying canvas. So first let's see this, but we have to add the wait key and destroy all windows. The reason why we add these two lines is so that we have a key press available for closing the canvas. So when we run this, hopefully we should see a canvas with black color in which a line is there. And the line, I guess, should be red color. Let me see, where is my canvas? It is BGR, not RGB. So BGR. So if I keep this as 255 and this is 0, I guess the line should be green now. Where is my line? Yeah, so this is my new line. So this defines the starting point of the line. This is the ending point of the line. This is the color of the line, and this is the thickness of the line. So if I make this 15, you will see a giant line. Let me run this. Very thick line, right? So this is the characteristic of the shape. We could do now a rectangle. So CV2.rectangle. Where are we drawing? We are drawing it in the canvas. And this is one of the vertex, the diagonal vertex, the color. So BGR. So this rectangle will be 255. And that's it. So we have a rectangle and we have a green line. Now we could also put a text. So this rectangle is very useful because we'll be putting rectangle, bounding rectangle around shapes. Then CV2 dot, I would say, put text of canvas, comma, we could say something like OpenCV text addition. And we want to define a place where this text is added. And font, I don't care about the font. So 10, let's say 500. Let's see without adding the font what happens. Maybe some default thing will happen. Okay, I guess font is needed. So, comma CV2 dot font, Hershey Simplex, some random font that was in my recommendation. So now if we run this, it will use this font. I think one of them is the font thickness, and this is the color. So font color now should be white because it's BGR 255, 255, 255. So the text should be white. See, OpenCV text addition. So this is how you manipulate canvas. Now the canvas could be anything. Canvas could have another image on top on the background. So it will look as if you are now drawing pictures on top of the image, right? So I will share this link, I mean, this code also in the chat. Just let me know if you are able to run all of this. 1 second. Yeah, just let me know if you have been able to run some code, because now the whatever we are going to run right now is the most important one. So I want all of you to be able to run this. I think it's to mention the pixel values. So in NumPy, you can add floating point numbers. You can add any type of numbers, but here in the canvas, you can't have a pixel value of 1.5. You have pixel values ranging from 0 to 255. So here I can, let's say I avoid this. I don't know if by default it will be integer or not. So let's see. I am removing the data type. Okay, now it is working. But what if it's a floating point? Float 64. How about this? Maybe, I'm not sure. Oh, this also works, surprisingly. Maybe somehow it is converting the numbers into integer by default, like it is rounding it off or something. But usually it is a better practice to ensure that the number that is in the canvas is a whole number, like a integer which is positive. Here you are starting with np.zeros. So you don't want 0.0, you want 0. Now what else? That's it. Let's now start with the burglar alarm detection code. So start a new file, not burglar alarm, burglar presence .py. Okay, so this we will start from completely from scratch. Now here is where you will be using both. You will be accessing camera on your computer using OpenCV, and you will access the camera feed. And you will also do one more example where you are uploading a video file, MP4 file, and then from that you will annotate whenever there is a moving object. So as usual, import CV2. You are importing computer vision OpenCV library. Then you say capture equal to CV2.video capture of 0. So you know what this will do? This will ensure that you are capturing the real-time camera feed. So video capture of 0 means you are capturing the camera feed. Cap means you are saving that whatever is being captured into this variable. Okay. Now what we will do is we want frames. For saving the frames, we are having an empty array. Then what I want to do is the following, right? The logic of burglar detection is this, a simple logic. I will first capture the frames from a video. Can you see the Miro board? Can anyone confirm if you can see the Miro board? Okay, thank you. So what we are going to do is either from camera or from a video, we will capture the frames. Now, when do you think in an indoor setting, when the house owner is not available at the home, and if nobody is there in the home, if there is an indoor CCTV, when is there a suspicious activity happening? Whenever somebody is moving, whenever something is moving in the screen, right? So for that, all we need to do is find the difference between two adjacent frames. Because if there is a burglar inside the house, in the CCTV feed, burglar will be moving somewhere, right? So initially in the current frame, maybe burglar is here. And after that, the burglar has reached here. So when you look at the difference between the frames, in the first frame, you will see a person here. In the next frame or after 5 frames, you will see a person here. So if you take the difference between those two frames, if you pixel by pixel, if you subtract, you will see that there is some difference. Rest of the things will be same, because if there are static objects in the frame, if there is like a wall painting, that wall painting there will be there in both paintings. So you are specifically targeting moving objects here, right? So first we define an array for storing the frames, and then we say gap equal to 5. So this we can say is for defining, okay, are you going to look at the difference between every adjacent frames, or are you only going to look at frames, one frame and then the 5th frame, then the 10th frame, so that significant changes can be detected? So I'll say gap equal to 5, and then count equal to 0, like frame count. So we'll start with 0. Okay. Now what we want is, we want a continuous camera feed to happen. So if we have a real-time camera, which I can show using webcam, I want it to run constantly. So then I will do this while true, so that this while loop will by default execute many times, unless we say otherwise. A value that is returned, comma, the frame that is returned, equal to capture dot read. So this, what this is doing is, you are defining the captured video in this variable called cap. Then from the variable cap, you are reading whatever is there in that frame. So the read things will be there in this frame, and whether something has been read or not will be there as a binary in this return variable. Now, if nothing is returned, so if not returned, so if return is false, which means then if not return will be a true condition, then you have to break out of that loop. Then you say just break. Break meaning you are not seeing anything in your camera feed, like nothing is coming into this cap variable. So you're going to return out of, you're going to move out of the this logic, exactly. So Shivam has mentioned this logic will identify cats and dogs also as burglar. Exactly, this will. So here we are taking a very simple logic where nothing is expected to move in the home. If there is anything moving significantly in the home, we will detect it as an anomaly, right? So that is the logic that we are implementing here. Now, but if this is not true, meaning the return thing is not false, then what we will do is the frames that we have captured, so gray equal to CV2 dot convert color of frame. So we are converting whatever frame we have captured into a grayscale image. So gray, I'm using a variable called gray, where I'm converting the frame using CV2 dot color BGR to gray, and I'm using this CV2 dot CVT color, which is convert color. Then I will append it to this empty variable. So I had an empty variable called frames. So frames dot append of gray. So the grayscale image, which is the grayscale version of my current frame, is now appended to the frames variable. Now, what I want to do is, I just want to check if the length of this, so after you append, right, I just want to measure once in every 5 frames. I mean, between frame 1 and frame 6, there are 5 frames. So I want to find the difference between frame 6 and frame 1. Then I want to find the difference between frame 11 and frame 6. Then I want to find the difference between frame 16 and 11, and so on. So I don't want to look at more than 6 consecutive frames at a time. So if count, I have to increase the count also somewhere, which I will do. But if, let's say, length of frames is greater than gap, gap is 5, so gap plus 1. So if my if the length of frames, which is this empty array, has now, let's say, 6 images, that is when I have to implement my logic. Then I will do frames dot pop of 0. So what does this mean? Gap is 5 and gap plus 1 is 6. If the length of my frames is 7, so let me draw an array here. I have an array for storing the frames. Okay, so I'll start my frame number from 0. So I have frame number 0. I'm appending frame number 1, number 2, number 3, etc. up to number 5. So once I reach frame number 5 here, now the total number, my length of frames is 6 here. Okay. Now if I append frame number 6, which is technically the 7th frame, then I don't need this anymore because I am calculating the difference between 6 and 1. So I don't need this, the 0th one anymore. So then I can remove this. I can just pop this. So this pop operation basically pops whichever is the first element in my array whenever the length of the frames array is greater than 6, meaning equal to 7. So then it will be popping the useless one, which is the first one. Now, if yeah, I can also add some text. So cv2.putText, put text, and I could add like a frame number. So cv2.putText. So inside the frame, I am adding a frame count, and it is equal to the variable value count. So count is starting from 0. So I will start with frame number 0, frame number 1, and so on. And what I'm saying is cv2.putText inside the frame, I'm going to put this text. And why do I have this F inside double quotes? Because it's like a dynamic string. It's not a fixed static string. Then I have the color, I have the font, etc. I have the location where I'm putting the text, etc. So cv2.putText, I'm putting it at certain location and for certain color. So color will be BGR. So it will be green color in this particular example. Then what should I do? If length of frames is greater than gap, and what is gap? Gap is 5. So if the length of frames is equal to 6, basically, because greater than gap means greater than 5, which is 6. So if the length of the frame has reached 6, then what I will do is I will calculate the difference between two consecutive frames. So cv2 dot absolute difference. So absdiff is the function for absolute difference, and I will calculate the difference between frame number 0 and frame number -1. Can anyone tell me what is this -1, frame number -1? Exactly. So 0th element is technically the initial element. -1th element is you are circularly going back to the last index. So last item in the list. And absolute difference, because we only care about the difference. We don't care whether the difference is positive or negative. So we are taking absolute value of the difference. Then we will say we are using a thresholding, and we will say we are thresholding whatever is the difference such that all pixels with value less than 30 will be eliminated. So which means if the difference is very high, it means those regions will be bright, and you are only picking regions with certain brightness or above, because in the image maybe there is a flickering tube light. You don't want that flickering to affect your moving object detection. You ideally want only major changes happening, which means you're looking at higher values of pixels in your difference between frame 0 and frame -1, which is frame 0 and last frame. So if the difference is greater than 30 and less than 255, 255 is anyway the maximum value, you are thresholding that. So you are only selecting that. Then you will say this threshold is passed into a function for finding the contours. So contours equal to this will be contours equal to, or contours comma, there is also one more argument, cv2 dot find contours, and you are finding the contours in this thresholded image. So you will find it in thresholded in thresh, and cv2 dot, so for finding, so contour is nothing but where are the clusters of pixels that are happening, that are experiencing maximum value of change. So you are now finding those contours. Yeah, I'm getting suggestions while doing code because I have installed Copilot, I think, but there is also a native one for VS Code, I guess. But I'm not sure which one is giving me the suggestion, but I'm definitely having Copilot. If I switch this off, perhaps this will not come. But do install it, okay? Yeah. So contour is, imagine that you have a collection of pixels. So here, for example, in this image, the difference would look something like this. Let's say in my image, a person moved from here to the immediate next location. Let me just. Okay, let's say the person moved here. So then the bunch of white pixels that I will get in my difference will be over here. So pixels around this general region will be kind of white. However, if some small leaf also moved somewhere here, let's say there is a small leaf that is moving, there also I will see a collection of pixels. Then if I have some other small changes happening elsewhere, there will be a collection of pixels that are white. Now, what is a contour? A contour is nothing but this big group of pixels is now determined by, okay, let me just draw it using pen. This big group of pixels is now determined by this contour. There is another small group of pixels defined by this contour. This is another small group of pixels defined by this contour. Now, all these contours have certain size or certain area. And I only want to consider contours that are big enough. Meaning, if the contours have certain minimum area or above, I will consider those. Rest of the contours I don't care about, because maybe in the image some small thing has moved. I don't care about that. I only care about major things moving, because a burglar will definitely move, right? So maybe contour sizing threshold is one way in which we can eliminate a cat moving in the video, because a cat is a small animal. There are many methods, but I'm just showing you the most primitive way in which you can implement a basic logic, right? Now we will say, now that we have got the contour, for C in contours, so you are getting every individual item in contour. I'm sorry, I just pressed the tab for accepting the suggestion, but let me just put it from start. Then CV2 dot contour area of C. So you are picking each individual contour in the contours variable. Then if the individual area of that contour is less than 500, then you ignore it, because then this 500 is also like a experimental number that I came up with. I noticed that in sometimes for some type of videos, 200 is a better number. For some types of videos, 1000 is a better number. So we will play with this number, but basically this will eliminate those contours which are too small. So if the contour area is too small, it means it's a region where some minor changes happen, which you can ignore. So that is why you have continue here. Otherwise, you draw a bounding rectangle around the contour. And what would that look like? It will look like this. So I hope you can see the Miro board, but basically the bounding rectangle around the contour will look like this. It will look like this. It will look like this, but only for those contours which are big enough, not for all the contours. Okay. So now, if the contour is big enough, if it's greater than 500, then I have X coordinate, Y coordinate, width and height. X and Y coordinate of what? I just need 4 numbers to define a bounding rectangle. I just need the X coordinate and Y coordinate of this point. Then if I have that with the width and with the height, I can find the rest of the coordinates. So a bounding rectangle is defined by just 4 numbers, X, Y, width, height. Then what I will do is I identified the contours, and now I will say one more thing is I want to identify the motion. Like I need a binary variable for motion. So if I have motion variable like this, motion, any of CV2 dot contour area. So in the contour area, if in the CV2 area for individual, if any area is 500, then has it. So here what I'm going to do is contour area greater than 500. So within the contours, every individual C, check if at all for any of the C's, the contour area is greater than 500. If for one C condition is means at least one contour which has an area greater than 500 in that particular frame, which means in that particular frame, you have detected the motion. So motion will be true. If this condition is not there, which means there is no change that has happened in the contour, then this will be false. Then what we can say is if motion has happened, and so it's an and condition. So if motion has happened, and let me not put the count variable now, just let me put if motion has happened, then I will say cv2.put text. I will put something like this: motion detected in the image, and some font values. So this is the font family, the font color, etc., which we can change later. And I should also do one thing. Other than putting text, I should save the image. So it will be great if I have a CCTV footage, but instead of going through the entire, I went for a vacation for 3 months and then I'm back, or whenever I want to check a CCTV footage, it'll be great to just see the anomalies, right? Just the anomalies happening in the image. So I can save cv2.imWrite. I'm writing the image saying f motion frame count. So the count variable is counting the frame count. Then I'm saving it, and that's it, right? Yeah, and I can print also. Print that this thing is saved, and then I can show cv2.imShow. I'm displaying the image. Motion detection frame, and then count plus plus, or count plus equal to 1. Then, yeah, I need to exit somehow. So if cv2.wait key, then I'll exit. Otherwise, I'll continue and then release the capture, destroy the windows. That's it. So first, let me run the code and show you what is this doing exactly. So I hope my camera will be visible, although it is being used in Zoom. So can anyone tell me if my camera is visible to you? Let me quit this first. That camera in which the green rectangles are coming, it's visible, right? Okay, awesome. So let me just delete all of this because there is too much things here. Okay, motion frame. So I should save the frame only if motion has happened. That is true. Let me keep this as the threshold as 1000 because 500 is too much. Okay, now I'll show you how exactly this works. So I run the code, and if I am, yes, I will share the code in the chat. If I'm static C, I'll sit for a second without saying anything, okay? See, my mouth is moving only little, it's not detecting. But the moment I move my hand, it's detecting the motion, and it's drawing bounding rectangle. So it's drawing bounding rectangle wherever there is a collection of pixels that are detected, okay? And then this is saving those frames. So I don't have to check all the frames for anomalies, but I just need to check for these saved frames for anomaly, making the work very easy. Now let's play with the size of the FPS is frames per second. Now let's check with the, what is the FPS? I think it's 30, right? 30 frames per second, 30 or 60. But we are not saving all of them. We are only saving whenever this anomaly is detected. But let me just delete all of this, too many files. Okay, so now what will happen if I change this to, let's say, 5000? What do you think will happen? Will my detection be more sensitive or less sensitive? Why do you think it's more sensitive? Who says more sensitive? So I'll tell you what the 5000 is. 5000 is I am discarding those contours whose area is less than 5000, which means small movements will only bring small changes in the adjacent frames, right? So if I increase this number, I'm making my system less sensitive. So let's run and see. Okay, so Now see, if I'm moving my head, nothing much is being detected because the contour area is not very big. But when I'm moving my hand, it's detected because there is too much movement happening here. So this is less sensitive. But if I want to make it more sensitive, even if you want to capture my blinking eyes, let's see what to do. So if I keep this, let's say 250, then I am capturing those contours whose areas are 250 or above, which is much, much more sensitive than 5000. So here you will even see my eyes blinking being captured. Let's try. Did you see my eyebrows are getting captured? You see my mouth, eyebrows are getting captured. It's so funny. So, but this is basically how you can manipulate basic algorithms to, detect what you want to detect. Now let's do one more thing. Okay, I have a video here which I got from YouTube. Where is that? I think it's this one. So here I just got this from YouTube. It's an actual real CCTV footage where a couple of guys are actually performing a burglary. Before running this video, let me share the code with all of you so that you can also run this with me. Okay. So I will split the code into two parts so that, so these are this is the first part because I can paste only so much text here in the chat box. Or rather I'll download it and I'll send it to you as a file. Yeah, I'll send the file right now. Yeah, so this is the file. So just use the code from the file. Now, if I want to have this video inspected, right? So there is, at I think 2 minutes or something, there is one more person coming in this video. So just go to this, and instead of video capture of 0, just put video, whatever is the video name, it's video.mp4. Okay, then it will detect the burglars from the video as if it's a CCTV footage. You see? So now it is very sensitive because my threshold is, I think 250 or something, no? But if it's amazing, right? It's such a simple algorithm. There is no fancy deep learning here at all. Tell me, where is deep learning? There is no deep learning involved. It's pure logic and it's working beautifully. But of course, as somebody mentioned, if you don't want to detect cats or dogs, you just want to detect people coming into your private space. If that's your goal, then this algorithm won't work. But of course, there are ways to, even manual ways to deal with that. But also you understand this is why deep learning was introduced. But it's fascinating. Let's change this to 1000. Okay. I'm going to change this to 1000. And I think if somebody has a video of a human and a cat in one frame, just try playing with this contour area threshold. And I'm sure you will be able to find a threshold where if you keep the threshold as a certain number, you will be able to detect the human moving, but you will not be able to detect the cat moving. I'm sure there is a threshold that you can play with and figure out. So that will be very cool if any one of you can just try that. But see, now I increase my threshold. My algorithm became very less sensitive. Only if this person makes vigorous movements, something will be captured. Otherwise, it will not be captured. You'll be blocked when small kid is burglar. Yeah, of course. Yes, that will be there. But see, only if this person is moving very fast, you are detecting. But now let's change it to a small number. Let's say 50. If this is 50, what would happen? See, now it's like, it's so vigorous that even minute changes are being detected now. So it's amazing, right? Simple algorithm. and real-time detection. And then you, in the CCTV, you just check for these anomalous incidents from the saved frames. But now I have these giant, huge number of frames, which I have to now delete. But it's very cool. So just an exercise for you. Please, try running this code for different cases of thresholds and different videos. I'm very, very curious to see what you get. I have some other videos here of like people walking. I have like a football video here. We can try that. Let's see. Footer.mp4. Let's see what happens. And here I think I will have to reduce this thing even further. And this is anyway not a CCTV like thing, right? Because there are so many things happening in a football match. But let's see what we get. Okay, I don't want this much. So 500. Yeah, this is not very good because it's not a static camera. People are being detected, but you see background is also getting detected because camera is also moving. Camera is moving means the background is changing. But if you have a static camera, you don't need any fancy algorithm. That is what the inference is. But I think we can wind up this session, guys. Thank you so much. We are at the end of the session. So I enjoyed learning about this one particular non-deep learning approach, because we know that deep learning is very cool. But sometimes we also want to know how proper mathematics work, right? And this is that. So guys, I have to leave now, but please, I know that you may have questions. So you can drop your questions at this email, hello@vizuara.com. I'll be happy to answer, or you can email me at this. This will also be good. So for the folks who are in pro plan, please check out the section where there is a quiz section also added, where I have added a CV2, like a computer vision related interactive quiz. So just go through that, and the rest of the material will be uploaded in both. The recording, all of you will be able to access. But thank you so much, everyone. I'll be looking forward to meeting you again on Thursday, same time. So we'll continue with some cool applications of OpenAI, OpenCV. And after that, we will move on to RCNN, UNet, YOLO, Roboflow. So thank you all. Take care. Bye. Okay, so in the last lecture, we got an introduction to OpenCV library in Python. We also discussed a little bit about filters, especially the intuition about filters, right? And at the end of the last lecture, what we did was we built a simple burglar detection algorithm, which had nothing to do with deep learning. It was a pure logic-driven system where we were just looking at the clusters of pixels that were different from one frame to the next frame. And then what we did was we constructed a bounding rectangle around clusters of pixels whose contour area was greater than certain threshold. So depending on this threshold value, if we put 1000, it meant our system was less sensitive to movements. If our threshold was low, it means even smaller changes happening in group of pixels were getting captured in the frame to frame difference. So today we'll be building more applications using OpenCV. However, today we'll be using pre-trained deep learning models. Although we won't be going into the details of those deep learning models today, which we are leaving for a later part of the bootcamp, we will, however, be building these following things. So we will start with a simple object detection. So simple object detection means you are only looking at one single object, and that object will be annotated by a bounding rectangle. And this will be from an image, or it could be from our camera feed. It could be from a video. So the input can be anything. Then after this, today itself, we will build a multi-object detection, which is just a simple extension of single object detection. Then after detecting an object, how do we track these objects from one frame to the next frame? Because the algorithm has no idea that the object where you are drawing a bounding rectangle, it is the same object in frame number 35 and frame number 30. You have no idea. So if you were to create an ID for the object, how do you ensure that the same ID is being maintained from one frame to another? So we will implement that. Then we will also implement an object counting algorithm. So object counting algorithm meaning if you have a conveyor belt and there are objects moving through this conveyor belt, you could use this algorithm to count the number of objects, or if you have a traffic junction and there are n number of vehicles passing through this junction, you could count that. And last, if time allows, we will also work on object segmentation. So I will also tell you the difference between detection versus segmentation, right? And here, object could mean a person, it could mean animal, it could mean just physical things. So object is like a general term used in computer vision to represent any of these things. And as you might have already known, the data set that we are using would be videos or images from YouTube or from Pexels or from any stock video source. So you can take whichever video you wish to use. I will be sharing the videos that I am using for these projects, which are the data sets. The model that we are using will be YOLO V8. It's a pre-trained model that we are going to use. So YOLO is an object detection algorithm primarily, which expands to you only look once. And the reason why it's named like that is because you are just using one forward pass of a neural network to make a prediction. I'm not going to go into the details of YOLO today because we have an entire section dedicated to YOLO in this bootcamp in the last part. But we'll be using a pre-trained YOLO, which works really, really well for real-time object detection. And obviously the framework that we are using is OpenCV. So before going into all of this, let's make sure that all of us understand the difference between image classification. This is what is most familiar, object detection, tracking, object counting, and segmentation, because these things are different things. These are 5 different concepts. Classification is the easiest, and I'm sure all of you know about classification. You have image, and this image overall is classified into one of the n categories. If it's a binary classification, there will be 2 classes. So if it's a cat versus dog classification, you are trying to assign a probability to an image for it being a cat. So you might say that this is 99% cat. So this classification can be done using just a simple convolutional neural network with a softmax classifier at the end of it. In object detection, however, you perform 2 things. You try to either, if it's a single object detection, you try to perform a classification, but also you try to predict a bounding box. So here it's a multi-object image. There is a dog and a cat. And what you're trying to do is you are trying to come up with a bounding rectangle whose coordinates are known. So you will know this coordinate, you will know its width, and you will know its height. So x, y, width, height. With just these 4 parameters, you can define a bounding box. And you will also say what is there inside this bounding box with what probability. So you may say the bounding box location is this, and inside the bounding box, you have dog with a probability of 98%. Similarly, you can draw another bounding box, and this bounding box will say that there is a cat. And how do you build these bounding boxes? That part is taken care of by YOLO. So YOLO is that algorithm which allows you to construct these bounding boxes, which generally encloses the object of interest. Now, this might be in just one frame. So you are looking at, let's say, frame number 533. But tracking is different. In tracking, you are looking at people or objects or things that are moving from frame to frame. And in tracking, you could either assign an ID. So you could say this person has an ID of 1. This person has an ID, or this bounding box has an ID of 3. And if there are 3 bounding boxes in the current frame, in the next frame also there could be 3 or 4 or 5 bounding boxes. But at the end of the day, the bounding box that corresponds to this person who is moving should still have the ID of 3. The ID should not change. So the ID of the bounding box uniquely determines the location of this person. Now, if you want to actually track the movement of this person, what you can do is you can define the centroid of the bounding box. Centroid is nothing but x coordinate of or the width divided by 2, and you add that width divided by 2 to the x coordinate. So you will reach this x coordinate. Similarly, you do height divided by 2, you add that to the y coordinate, then you will move here. So basically, if x coordinate is this and y coordinate is this, you are looking at the centroid, which is this. And then this centroid, you can track and annotate from one frame to another. And that is how you make sure that you are tracking the movement of the person from frame to frame. Then This can be applicable for people moving. This can be applicable for traffic. So if you want to track one single vehicle and its movement, you could do that using this tracking mechanism. Now, counting can also be done using pretty much the same algorithm where you have the object ID. So if you have the object ID, you could simply say, okay, I have object ID 31, object ID 35, like that. And you just look at how many unique IDs appeared in your total video. So if 15 different unique IDs appeared in your entire video of, let's say, 5 seconds, then your total object count is 15. If there are 13 different unique IDs occurring in a current frame, that means at the moment you are looking at 13 different objects. So object counting happens as a result of you being able to assign unique IDs to objects. And this can be used for conveyor belt systems where you are primarily interested in vision rather than sensor-based approaches. So we will also implement this, and segmentation is very different. So segmentation here, you can see that you are getting the contour of this camel. You are not just drawing a bounding box and saying the camel is inside this bounding box, but rather you are able to meaningfully separate out the pixels that represent camel. And this is often called as semantic segmentation, because you are teaching an algorithm, which we will implement later, but you are teaching an algorithm to understand pixels that have a certain meaning. So all the pixels in this red color zone, they represent this object camel. Here, all these pixels represent a moving car. So we are teaching an algorithm to figure out those pixels from an entire image. So this image can be part of a frame. And if you are processing multiple frames very, very fast, that means you are performing this segmentation on a video effectively. So we'll be implementing this also in today's lecture. So let's think about the whole setup once. So the data that we are using is images or videos or camera feed. So please be prepared to do all of these things today. The model we are using is almost always YOLO V8 and V8 for version 8. YOLO is one of the most popular models for object detection. But at the moment, don't worry about its architecture. Just understand its application. We will go into the architecture and details later. And we will be using a pre-trained model. And where is this pre-trained on? So there is a very famous data set called COCO. Not this COCO data set. This one, common objects in context. So this is a very popular data set with, I think there are 80, it's like an 80 class classification. It has various types of objects, animals. So many YOLO models are trained on this COCO data set, and which means you can, whatever objects come within those 80 classes, you can make classifications, right? So that is the YOLO model. And then this model will be used for detecting the objects, IDing the objects, tracking the objects, etc. And what will we be displaying at the end of this? We will be displaying the input image or input video along with the annotations. So the annotations can be bounding boxes, annotations can be the ID of the object, annotations can be the count of the object, or this center of mass or center of geometry trail. And then we will finally save the annotated video to result in something like this. So let me once again share my screen to show you some sample videos from my past experiments. Just a second. I hope you can see my screen. So some annotated videos that I have created from my past experiments are, so this is, can you see this vehicle moving video or no? Okay, you can see the video, right? Okay, awesome. So this is a video where I implemented a pre-trained YOLO where we could track the center of mass of, or center of geometry of those bounding rectangles. It's not perfect. As you can see, it's not detecting all the vehicles, but that's fine. Our goal is not to build a perfect algorithm today. It's to understand it's working. Or this is an example of segmentation where we will have a video which we take from internet, random video, and we will perform segmentation to detect the bounding boundary of people who are walking in the scene. And we could also perform people counting. So here you are drawing a bounding box, you are IDing the person, you are tracking the center, and you are also making the count. So count in a given frame, as well as count the total count throughout. And one more thing which we will do is for an industrial applications like this, we will implement an algorithm for counting the total number of bottles. And I will also show you cases where this kind of fails, these algorithms fail, and cases where this algorithm actually works very well. So with that, please get ready with your Visual Studio Code. I'm also going to open my VS Code. I hope you can see my VS Code screen. So last lecture, we had created, what we did was we created a folder. Inside the folder, we created a subfolder called lecture 1, right? And then we created a local environment, and we were building everything in this local environment. So please make sure that you are in the local environment. Otherwise, it will be very difficult to take care of the packages. You will have to reinstall the packages again and again. So here, what I'm going to do is I'll name a folder called lecture 2 live. And in this folder only, I'll be working on the code. So please get ready with your VS Code. And now we are going to start coding. So first code that we'll implement is something like simple object detection .py. So I'll implement a simple object detection for a individual image. Okay, so import CV2 for OpenCV. One more thing you have to import is install is something called Ultralytics. So Ultralytics is this company. So Ultralytics basically have proposed YOLO V5, V8, and they now even have recent model YOLO V11. So Ultralytics package you have to install, and I think installing is just pip install Ultralytics. You just need to do pip install Ultralytics. So just make sure that in your local environment, in your environment where you have activated, just install Ultralytics using pip install Ultralytics. So I have already installed it. So I will do from Ultralytics import YOLO. So basically I'm importing YOLO model from Ultralytics. Then what I do is there are different YOLO models. It's not just V8, there are V5, there are different YOLO models, but I'm going to use a very specific YOLO model. So I'll say model equal to YOLO off. And here I have to mention the model name. So I will say YOLO V8 nano N for nano dot PT. PT means pre-trained. So I am taking a pre-trained model of YOLO and small size model. So this N suggests it's not the entire big YOLO model, it's a smaller version. Now we can read the image. So image equal to cv2.imread. So imread is the command for reading the image. And here, let's say I have a bunch of images here in my present working directory. So just note one thing. I have different folders here. Okay, so these different folders correspond to the lecture codes that I've been working on. But that is not my present working directory. If I want to see my present working directory here in the terminal, I can just type pwd. And you can see that my present working directory is the parent folder in which all these things are there. So if I keep my image inside this lecture 2 live folder, then I will have to specify the path of that image. Otherwise, if my image or video is in the parent folder, then I don't have to specify the path because my present working directory is that folder itself. So here I could just say, maybe I have a photo of myself. So sridhar.jpg. And what I will do is results of what? Results of our segmentation equal to model of image. Model is YOLO V8. Image is the image that I have read, which is this sridhar.jpg. And results are this. But now, why don't we see the results? I mean, first of all, we have not run the code. But even if we run the code, we are not going to see the results because we have to display the annotation. So now we say annotated underscore image equal to results of 0. So the first item in the results is will give you the annotations, and then you do plotting. And then this plotting is not enough. You have to always use imshow, cv2.imshow to display the images. So cv2.imshow, and I will say annotated image. That is the title of my image. And then here I will just simply put the annotated image. And then cv2.wait key of 0 means you are waiting for the, let's say, escape key to be pressed so that you can close the image once it is opened and then destroy all windows. So now if I run this code, this should open my this sridhar.jpg image, and hopefully it should annotate the image also. GitHub code file, so I can download the, yeah. So yes, I have uploaded the GitHub code link in the pro version plan, but I don't think people have, if you have submitted the request to be added as a collaborator on GitHub, I'll accept it today. But otherwise, I had added a Google form also for you to fill. So just fill that. I'll make sure that you are also added onto the GitHub. Now, I'm not sure why this is not loading the image yet, but let's see. Annotated image. So basically, this is the image, and I am definitely facing an issue. Meanwhile, let me share the code with you so that you can also run parallelly. So this is the code. Please try that along with me. Yeah, it worked now. So here you see, this is the annotated image that it is displaying. And how did this annotation come? The annotation came because we are using a pre-trained YOLO model. Where are we mentioning the pre-trained? This .pt for pre-trained. And this 0.87 is the likelihood of this bounding box, whatever is inside this bounding box, to be a person. Now, you might be wondering, how come we can identify other objects? So if I had some other objects in this image, how do we specify I want to identify person or cars or something else? I'll show you that in the next code. So this is the simplest code, okay? And can you guys let me know if this kind of code is working for you? Just one single image and you are annotating that image. Can anyone mention in the chat? Okay, awesome. So please, whoever is facing issue with Ultralytics installation, just do this, okay? Pip install Ultralytics. So just make sure that this is installed. Now, next code is we will be displaying multiple objects or even individual objects from a camera. So let's say live_camera _feed.py. So now we will do the same thing. Import CV2, then from Ultralytics, import YOLO. Then we'll say we have to capture a frame now. So capture equal to CV2.video capture. So this time we are capturing a video, not from a file, from a camera. So video capture of 0 means it will capture from the camera, from webcam. But if I say some file name here, it will take it from the file. So here I want to capture from the camera. So give it as 0. These suggestions are coming because I have enabled, so here in GitHub Copilot in configuration, I have enabled this, where is that code completion? Enable the code completion. I could disable it also, but let us keep it enabled so that I don't make any silly mistake while coding. Then I have to mention the model equal to YOLO of YOLO V8 nano.pretrained. And then now, camera feed is something that is continuous, right? It's not just one image. Previously, it was just one image. So I did not need any while loop. But here, the capturing has to happen continuously. So I will say while true. So this while loop will run forever unless interrupted. Then I'll say whatever is returned, comma frame. So returned is true or false. RET is just a true or false binary. Capture.read. So from the capture, which is the video capture, I am reading frame by frame. Then I will say results equal to, so previously I did results equal to model of whatever was the image. So results equal to model of image. This time I will say results equal to model of frame because I'm capturing each frame. Then I can again create the annotated frame equal to results of 0.plot. And then I can do cv2.imshow. So I display this annotated frame. So from the live camera feed. So the title of the live camera feed, I'll just say live camera feed, and I'm cv2.im showing the annotated frame. And here again, we can add a wait key. So if wait key is pressed, if wait key pressed is equal to escape or Q for quit, then you break out of the loop. Otherwise, you continue the loop. So basically, camera feed will be taken as long as you don't press the wait key. And that's it. You then you release the capture. So that is cap.release and destroy all windows. So now let's try running this code. And meanwhile, let me also paste the same code in the chat. The structure is very simple. Import CV2, import YOLO from Ultralytics, use video capture, use YOLO V8 Nano pre-trained, then while loop to capture the frames as a continuous feed from the camera. You are treating each frame separately and you're passing each frame to the model. The results are here. From the results, you create the annotated frame, which is the annotated image, individual frame, and then you are just displaying it. And let's run the code and see what happens. Okay, so this is working. Can you see my camera feed on the screen, the annotated camera feed? Okay, awesome. So it denotes the person. Now let's see if there are any objects that I can show. Okay, I have my phone. So it says remote. I don't know. Yeah, now it says cell phone. When I hold it like this, it says cell phone. Otherwise, it says remote. And I have a pen using which I'm writing on Miro. I don't know if this works. I think I have to hold it a little bit. It says toothbrush. I have a computer mouse here. Let's see if that is identified. Remote, it says remote. So it's not extremely accurate as you can see, but it's accurate to a point. For people and for some traffic related objects, it's very, very accurate. So this is the YOLO implement and it's real time, right? As you can see, there is very minimum delay happening. And here for quitting the feed, I just need to press the button Q. So this code also, let me share. I don't know if I shared it. So just try running the code and let me know, is anyone getting the results for this code? Like, are you able to see the camera feed and you put different objects and multi-object detection working? Yeah. Okay, so that is object detection from live camera feed for not necessarily one object, it's multiple objects. Now let's do for a video, I guess. We can upload a video and from that, let's try to identify multiple objects. So I'm closing these two in Python code. And in the same folder, let me create a new file, multi_object from video.python.py. Again, import CV2, then from Ultralytics, import YOLO, then my capture cap equal to CV2 dot, what should I do here? CV2 dot video capture of, should it be 0 or should it be something else? What should I provide here? Exactly, the file name, whatever is the MP4. So I have a file called street.mp4. So I can give that. Let me see if I can say share this MP4 file on the chat. I'm not sure if it works like that or not. Okay, I managed to share the file on chat itself. Just let me know if you're able to get it. It will be arriving in few seconds. Okay, so this is my file. And then I need the model. So model equal to YOLO of which one? YOLO V8 nano dot pre-trained. So this is my model. Now I have to run the while loop. Why? Because the camera, I mean, just like the camera feed, the image is also a continuous feed of frames. So while, oops, I don't want these suggestions. So while true, the return comma frame equal to capture dot read. So from my capture, I'm reading frame by frame. And then rest of the steps are very simple. Results equal to model. I'm passing the frame into my model. So model of frame. And then now I need to create annotation. So annotated frame equal to results of 0 dot plot. Now this is the annotated frame. Now I just need to display. So cv2 dot imshow of annotated video, comma, and here I can pass annotated frame. And that's it. Now I just need to if cv2 dot wait key of 1 and oxf f equal to ordinary queue, then you break out of the while loop and then you release the capture. So basically you stop capturing and you destroy all the open windows. Now let's run the code and see what happens. So here, and I'm pasting the code. So just look at the code, okay? The code is exactly same as the previous code. The only line which differs is this line. If we put 0 here instead of the street.mp4, you will have the, you will just have the camera feed. Otherwise, you'll have the video feed. Now here, it's doing it frame by frame. But the video which I showed you was playing very smoothly. That is because after saving only, this can be played like a proper 30 frames per second video. Right now, it's capturing each frame, processing it and displaying it. It won't be very smooth. And you can also see that this is detecting multiple objects, not just people. So if you only want to detect people, you could make some changes here. I think you can say classes equal to 0. So from the frame, you only want to detect the classes whose index is 0. This is nothing but people. So people belongs to 0th class. So if I run the code now, hopefully we should only see people being annotated. So previously other objects were the C. Right now only people are there. Now, what else can we add here? Another thing which we could do is tracking. So here we can say persist equal to true. So here, if we say persist equal to true, and then if we run, persist is not a valid YOLO argument. Persist is a valid YOLO argument, but not like this. Okay. This I will stop for now. Can anyone confirm if you can see my screen? Not yet, but almost once this is running. 1 second. So persist, yeah, so that's a good question. So persist is whenever we are adding ID, it's not working in the current code. It needs in the next code I will show you. But basically persist is used for making sure that the ID is not changing for one bounding box from one frame to next frame. But right now we are not using persist. But can you see the frames being displayed with the annotation? Can you confirm? Okay, awesome. All right, so this is the, so we are going one level difficulty, like in each code, we are going one level difficulty above. Now let's go to the next one, which is object counting. Okay. So I'll close this and I'll name this as object underscore counting. So far you guys also should have been able to follow me, right? Because the code difference between live camera feed and the video feed are just one line difference, right? So object counting dot py. Now same thing, import. Yes, there is so for frames per second increasing, that's what I was saying. Whatever was being displayed is just based on the processing speed. But when we save it as a video, we can define whatever FPS we want to display it at. So the videos which I showed you at the beginning, which was MP4 files with annotations, they were playing like normal videos because those are the videos which I saved. But these frames which you are seeing right now, it's not a saved MP4 yet. It's just the frames being displayed with annotation one after the next, right? So it'll be a bit slow. Okay, so import CV2, then from Ultralytics, import YOLO. Then we need model. So model equal to YOLO off, YOLO V8 pre-trained, and capture equal to, so this time we are going to count the object and ID the object, okay? So capture equal to cv2.video capture of, instead of 0, this time I'm going to add a video called bottles.mp4, which is the video which you saw where bottles were moving. This one, this video, okay? So I am sharing this video in the chat. So please feel free to take it once you have it. I assume you might have received the previous video in the chat, right? Which might have taken a few seconds to arrive, but I think it should have been there for you. Okay. So this bottles also you can take. Now that is the video. Now what we need is, we need to have a variable for storing the unique IDs, because the ID for one bottle should not be duplicated for another bottle. So let's say unique underscore IDs equal to, we are just creating a set for that. So this will be like similar to a dictionary. Now again, while true, because we are fetching frame by frame from a continuous stream of video called bottles.mp4, return, which is a Boolean, comma frame equal to capture dot read. So we are reading frame by frame, then results equal to model. So this time it's slightly different. So what we need is results where only certain types of objects are there. This time I'm adding a video called bottle. So I don't need people. I want bottles. So result, last time what we did was results equal to model of frame. But this time what we'll do is model dot track of, and then here we pass frame, but not only that, we pass classes. And classes, should it be 0? Should I say classes equal to 0? Yes or no? No, because classes equal to 0 is for people, but this time it's for this object called bottles. So bottle class number is 39. That this you can easily find from the documentation of YOLO. And here we will say persist, because we want the ID to, we want the bottle ID to not change from frame to frame. So persist equal to true. And there is one more thing. So you saw this lot of these processing related things being displayed in the console here. 0, 320 by 640, 21%, 102 millisecond. So if you don't want that thing to be printed, you can just say verbose equal to false, because that printing thing is annoying. So verbose equal to false. Then again, annotated frame. Same thing what we did. Track is a method in OpenCV or Ultralytics. So it's not a method in OpenCV, it's a method in it's based on the way YOLO model is defined. So an YOLO model, this particular model is defined by Ultralytics. Now, annotated frame equal to results of 0 dot boxes. But there is one more thing, not boxes, dot plot. There is one more thing, if. So in the annotated frame, if there are no boxes, or if there are no items, like no bottles, then we don't have to do anything. But if results of 0 dot boxes, so these are the boxes, annotated boxes, and results of 0 dot boxes dot id is not none. So what we are checking is whether the results dot boxes is not empty or not, and whether the IDs of those boxes are not empty. So we are checking those two. If that is not none, then for each box we have to define an ID. Then we say IDs equal to results of 0 dot boxes dot id, and we convert this into a numpy array dot numpy of 0. So now I'm missing something. Can anyone tell me what am I missing? I'm missing numpy import. I never imported numpy, so import numpy. I could say import numpy as np or just numpy itself. Then I need the box IDs. I also need the I also want to make sure that individual boxes are having unique IDs. So IDs equal to results of 0 dot boxes dot id dot numpy. Now then we say for OID in ID. So we are picking each individual ID from the IDs variable. Then we say we append that ID into unique IDs. So what we are doing is for any item in the ID, any new item in the ID, we want to append to unique IDs. But then we say CV2 dot put text. So this is to annotate the ID number in the image. So put text. So this is something that we had done last time also. We had put some, I think some computer vision or some text on a canvas. So here we'll put text on where? On the annotated frame, annotated underscore frame. And then we put a variable here, count is equal to whatever is the length. So total count is length of that unique ID array. So if we have total 20 unique IDs in the unique IDs array, that means we have total 20 items. So we are displaying that this 10,30 is the coordinate where exactly we want to display. We want to put this text. Then cv2.font Hershey simplex is the font family. This is the color of the font. I think one of them is the thickness. This I have to check what exactly is this one. One of them is the font size and one of them is the font thickness. Now, this is the text for the object ID. Now, what else should we put? cv2.imshow of object tracking, and then we just display annotated frame. And that's it, I guess. We just need to now close if escape or rather Q is pressed. So yeah, if cv2.wait key is pressed, then I am going to close. So here I don't need any else condition. So just make sure, just let's go back one step. Okay, I'll before we take this further ahead, I will go back to the starting. Let's just take a step back and see what we have done. So we imported OpenCV library. From Ultralytics, we imported YOLO. We have NumPy because we are converting the IDs into NumPy array. We have YOLO V8 Nano pre-trained model. We have a video called bottles.mp4. Then we have a unique IDs, which is starting as an empty set. Then the while loop ensures that we are taking frame by frame input. And that capture from video is being read frame by frame. This is just a Boolean, which we are not using right now, the return variable. Then results, in the results, we are only interested in for the frame input, we are only interested in class number 39, which corresponds to bottles. Persist equal to true. I will show you this persist equal to true and persist equal to false. Verbose equal to false is to prevent random things being printed in the console. And then annotated frame is basically the results from this experiment. I mean, from this one frame. Then if in the results there are boxes and there are IDs, then we create the IDs as NumPy array. And for each individual ID, we add it into the unique ID, and that's it. Now let's run the code and see if everything is working or if there is any issue. And meanwhile, let me also share the code in the chat. Yeah, so the results array has bunch of things. So if we are trying to just print the entire result, it will have a several things that are output from this model.track. But if we only want the input frame and the annotated boxes, then that is stored in the 0th index item of the results. That's why results of 0. Okay, I'm not sure if this run. Let me do once again. Okay, so now we have our count. So here you see count is being displayed, and count is based on how many number of bottles there are in each frame. And just see this, if you just track one single bottle, the ID of that bottle is not changing from frame to frame. But let's now make this false, persist equal to false, and then just see what happens to the individual object frame after frame. Surya has asked a question. If see here, you see ID is for the same bottle, the ID is changing. You see this bottle now has ID 4, 5, 6, etc. So ID is changing when persist is false. So that's the reason why we add persist equal to true. So Surya has asked a question. If person goes out of the frame and comes back, does it have the same ID? I don't think it will have the same ID, because the way ID is tracked, as far as I understand, is there is something called as intersection over union. So we can think of it like this. So let's say I have a bounding box. So I have a person here, okay, and a bounding box here. Now in the next frame, the person might have moved a little bit here, right? And we can detect a unique bounding box, or rather in the next frame, maybe this person, let's say in the next frame, this person is slightly over here, and my new bounding box around this person is over here, okay? Now this is frame 1 and this is frame 2. Now there is a concept called IOU, intersection over union. So between these two frames, the bounding box has this much intersection, and the union is the combined area. So intersection over union is nothing but area of intersection divided by area of union. Now, if area of intersection over area of union is approximately close to 1, it means between the two frames, the bounding rectangle around that particular object is almost at the same location. So basically, based on the IOU of a bounding box and a threshold value, so we can say that if IOU is greater than 0.5, yes, frame per second also should be available. That is the reason why if it's a very high speed image, it's very difficult to detect the object. So in the same conveyor video, right? If the conveyor was moving very fast, then what happens is for two adjacent frames, the same object might be far apart. And what that means is the IOU will be 0 because there will be no intersection between the bounding boxes. So if the frames per second is very fast, then the algorithm needs to be adapted accordingly. The current vanilla algorithm of detecting object ID won't work for that. And this is another reason why for fast moving cases, object tracking is very difficult. But normally, and you can test this with, all you need to do to test this is, let's say you take another conveyor belt video instead of this bottles.mp4, either you speed up the video or you take another video where actual conveyor belt movement is very fast. Then it will be difficult. Now, how does it make the distinction for object? So the assumption is that the video is happening reasonably slow, that if you are picking two adjacent frames and if the objects are similar inside the bounding box, so we are looking for class ID, right? So here the classes ID is 39 in the current example, but for this case, class ID will be 0. So first thing is the class ID should match. Otherwise, there is no object tracking because it's a completely different object. So class ID has to match. Then there should be a decent IOU, decent intersection over union. If both of those conditions are satisfied, then you can assign the same ID for the two bounding boxes, and then you continue doing that. So in the next frame, when you draw a new bounding box in the next frame, you are not going to compare the third bounding box with the first bounding box. It won't make any sense. You compare third bounding box with the second bounding box. Then in the next frame, you compare fourth with the third, like that. And the IOU for adjacent frames are calculated. Similarly, object class for those bounding boxes are also considered. Then what else? With respect to industrial application, what will be the accuracy of this detection? Yeah, very good question. So this particular code that we have right now, it's not very accurate. Like, as I said, if I slightly change the video, in some videos I have seen the bottles are very clear bottle, almost transparent bottles. There is no product inside the bottle. Currently, you can see that this bottle has actually some oil or something like that. But if these bottles are empty, and if the background is also like very kind of like a white or gray color background, it's very, if the bottles are transparent, it's very difficult to distinguish. So there is no blanket algorithm which will take care of all of your industry needs, but rather you have algorithms which you have to custom make sure that edge cases are taken care of. But I hope you understand and appreciate how, the basic idea works here. Let me, if I don't remember if I shared the code in the chat or not, but let me just paste the code just in case. So can anyone confirm if they were able to try out this code and if it is working for them or not? If FPS is high, the bottle shape would still be the same. Then even though bottle went away, there would be another bottle which could potentially get the same ID. Oh, great question. Yeah, I think that can happen. Yes, that's a very good question. Because you don't know which bottle is which, ideally. You only know the IOU from one frame to another for the bounding boxes and whether the items inside the bounding box are the same. Then if current bottle is replaced by the fifth bottle in the next frame, because the frame rate is very high, yeah, then it's likely that those two bottles may get the same ID. It's a very good edge case to think of. Okay, so code is working. Just let me connect my charger 1 second. Okay, so now we can move on to the next one, which is tracking people with a trail. So we should add a trail as the center of geometry. Okay, so let's open people underscore with underscore trail dot py. Now, as always, same thing, import CV2. From Ultralytics, import YOLO. We can also import NumPy, I guess. Import NumPy as NP. Then we should say model equal to YOLO of YOLO V8 nano dot pre-trained. Then we say capture equal to CV2 dot video capture. Instead of 0, I have a video called walkers something. Okay, walkers high-res dot MP4. Walkers high-res dot MP4. Okay, so this is my input video. And this time I need to keep track of ID, current ID, next ID. For the trail, I need a empty variable, and whether the person is appearing or not. So, okay, let's start one by one. So ID underscore mapping equal to empty. Then next ID equal to 1. I'll explain what we are doing exactly here, but this is mainly for tracking the center of mass, center of geometry, so that same person is being tracked. If there is a hand holding the bottle, will YOLO detect the bottle and the hand? So it depends on what we are asking to detect. So currently it will not detect the hand because we are only detecting class equal to 39. However, in the YOLO model, where is that? I'll show you an example. So let's go back to our previous code, lecture to where is which object counting, right? Yeah. So in object counting, I will say class is equal to 0,39, which means it should detect objects and person. And let's change this to camera feed. And I happen to have a bottle, which I don't know whether it will detect properly or not, but I have a bottle here. So let's see what happens now in the live camera feed. Oh, T is not, what is the T? Oh, persist equal to true. So here I have said two, could not find. Okay, this is not needed. So when you put 0, you don't need the quotes. That was the mistake. And now hopefully this should work. Okay, so now this is not detecting the bottle actually. It's only detecting the person. I'm not sure if, let's see what is the mistake. Classes equal to 0,39. We'll come back to this. I'm assuming the syntax here or something is wrong. But this part is easy to fix. I have done this before. But what I'm saying is, if we say multiple classes need to be detected, it can be detected. Now let's come back to counting people. So in counting people, now we need a variable for trail. So trail equal to, we will mention a default dictionary and lambda. So max length equal to 30. So this dequeue is like a JavaScript way of having a set of items in a dictionary. Then of integer. So we'll discuss what these variables are exactly doing, but let's go back to our usual thing, capturing frame by frame while true, return comma frame equal to cap.read. This is normal. Then result equal to model dot track of, we pass the frame and we mention the classes, and classes here is 0 because we are tracking people, and persist equal to true, tracker equal to, I don't think we need the tracker, we just need persist equal to true and verbose equal to false. Frame persist verbose, that's it. And then annotated frame equal to frame dot copy. So this time we are taking a copy of the frame, but I'll come to what we are going to do with it. Now, if result, so previously we were saying if result of 0, which is the actual result you get from your model tracking, from your YOLO model, if that is null, you are not going to do anything. But if it is not null, then you are going to do something, right? So here we say this dot boxes dot ID is not null. If it's not null, then what we are going to do is boxes equal to result of 0 dot boxes. But then you need the XY coordinate. So here you say XY, because each box has an origin meaning the left-hand side top corner XY coordinates, and it has width and height. Then you convert this into numpy array. So dot numpy. Previously, we were just taking these IDs. So IDs equal to result of 0. So from your results, you are finding the boxes, you are finding their IDs, then you are converting them into numpy array. Okay, now you have boxes and the IDs. Then what else do we need? That's all. So now for box and the ID and original ID in zip of boxes, comma IDs. If that is the case, then x1, comma y1, comma x2, comma y2. So these are the 4 items you need for every single box. Then you are mapping this into a box and then ID, or you need the center of mass, I mean center of geometry. So center X and center Y equal to, this part is simple. You just say x1 plus x2 by 2. So X coordinate of centroid, or x1 plus x2 by 2, comma y1 plus y2 by 2. So these are the centroids. Now, for among the boxes that are appear of OID, you are adding that by 1. So basically what we need to do is, the way we are going to display the trail is, we will display it for few number of frames. Like for a person who is moving for 200 frames, we will not be showing a trail that appears on all the 200 frames. We will just show the person's trail for the past 20 frames. So it will be as if a tail is following the person. Then what we do is, if appear of OID is greater than or equal to 5, meaning if the person has been appearing constantly for more than 5 frames, then and OID is not in the ID yet, then you are saying this is a unique ID. So I'll explain these lines, but I just want to show you the process overall. And so basically, if the OID is a new ID, which is not currently there in the ID map, then it's a new person. Plus, if the person has appeared consecutively for 5 frames, then we can consider that to be a new person with a new ID. And if OID in ID map, basically, if this is a person that is already existing, then the person's ID equal to ID map of OID. Because this OID already exists in the ID map, then we just need to pick that person's ID. Then the trail, which is the tail, that the center of mass that follows that person, will be trail of OID. Append the center CX, comma CY. Then we just need to display the rectangle. So display cv2.rectangle annotated frame. So this rectangle is the rectangle that goes around a person. Then we can put a text saying the person's ID is so and so. Put text x1 comma y1 comma and y1 minus 10. So yeah, x1 is the center of mass of person. x1 is the point where you have the starting point of the rectangle. Y1 is the y coordinate. Minus 10 means you are slightly moving up. Then this is the font. This is the font thickness. This is the font size. One of them is thickness. One of them is size. I forgot which one is which. cv2.put text of annotated frame. And then I guess that's pretty much it. We need a circle for the centroid. So centroid we are putting as small circles. So I will show you what I mean by that. So cv2.circle of annotated. So in the annotated frame, we are putting a circle. Where are we putting it? We are putting it at the center of mass. Circle has a certain thickness. It's put at a certain location, and it has a certain color. And that's it. Now we can simply say cv2.imshow show annotated frame, then break, and then go out of the loop. I don't think any of this is needed. Cap.grease. I'm sure some syntax issue exists, but we can check it one by one. Let's start from the top. We import the OpenCV library. We import alternative. These lines are fine. Import NumPy. Then model is YOLO V8. Captured frames are here. I mean, captured video is in the cap. Then we have an ID map. We have next ID. Then trail is being stored here. Whether the person has appeared or not is stored here. Then we have a while loop for capturing frame by frame. Individual frames are here. Results for individual frames are here. Classes we are tracking is just the people. Persist equal to true will ensure that the ID is ID will not change from one frame to another. Then annotated frame is where we will have the image plus center of mass plus rectangle plus text, everything. Then if the boxes are not null, then we find the boxes coordinates and we find the boxes ID. Then if those IDs are already existing, then, or rather for all the boxes, we basically get the XY coordinates and width and height. We also get the center of mass or center of geometry of those boxes. And if these people have appeared consecutively for 5 frames, we say that, and if the person's ID is new, then we say it's a new person, then create a new ID, otherwise don't. I think that's pretty much it. Let's run the code. I think my indentation is a little bit off, but we will see. And meanwhile, let me share the code. And if there is an issue, I'll let you know. Okay, default dictionary is not defined. We need from collections, import default dictionary and DQ. Yeah, thanks, Peter. Yeah, that was the issue. Okay, so now this is the thing, but something is not working, right? Put text missing is missing the argument color, which we can easily add. Where is my put text? So color can be simply this. Okay, this time I don't want to play with this. I will say fix the syntax. So last lecture I had mentioned about the Copilot. So go to extensions, go to here, type Copilot and just install the Copilot. It will be handy, especially when you are actually working on something, not while learning. If you're learning, of course, try to do from scratch. But if you are working on something, of course, feel free to have a Copilot. So I'm only interested in the put text part. Okay, so this is the put text part. Or rather, if you want to replace the entire code, you can just click here. It will replace the entire code with this code, which I don't like doing, but let's try. Because I think only 1 or 2 lines there was an issue. Yeah, this had an issue. This indentation was like this before. So this is supposed to be here. That makes sense. Okay, and they added a bunch of comments. All of that is fine, but I just want to see if this is working for the moment. Okay, it is working, and you can see that. I hope this video is not too small for you to see. Like, you can see that there is a centroid and there is a trailing line, and see the reason why the trailing line is disappearing is because we are only keeping track of these many number of frames. Where is that? We are not keeping it forever. We are only keeping it for a finite number of frames. And you see that their IDs are also not changing. Like, the unique IDs are being maintained. Because the readability is not very good, what we can do is we can change the color. So this is BGR, not RGB format. So now this will be red because this is 255. So if I run the code, the ID will be red, and font size, I think I can change by changing this number to 1.6. So now the ID will be more readable to you. And that's pretty much it. So the only extra thing that we added was this person tracking. Oh, video in the chat. Yes, Shivam. This video, I forgot that I had not shared this with you. This is called high-res, workers high-res. Yes, so the code I will share as a Python file. That will be better because this is a bit longer code. So this is the code. Just try this out. Has anyone managed to do this so far, or were you facing issue with respect to adding the text or some minor syntax issue? If yes, let me know. One thing which I haven't added here is saving. So saving part is actually easy. It's just 1 or 2 lines, saving this into an MP4, but I'll just show you. Let's ask Copilot, add a line for saving this as an annotated video. So whatever is being shown on ImShow, we can just save it. It's not detecting people in a group. You mean people who are standing at one location? Is that what you mean, people in a group? Let's see. Yeah, I remember like one section, like bottom left part, there are some group of people standing. They are not this, right? These people. Also, some people who are here, who are overlapping kind of, you see, they are not being detected. Here there are a few people who are not being detected. I'm sure there are ways to increase the sensitivity of this model, but let's do one thing. No, let's actually close this and let's pick some traffic video. And I want to show you how the same thing could be used for traffic. I think not this. Oh, by the way, this traffic video is hard to work because the default YOLO model are trained on ground camera, but here it's like a aerial view. So for this traffic, it won't work, but for traffic, for this, it will work. So let's see. So this should be traffic 3, but more importantly, the classes. Let me ask, what are the COCO classes for vehicles? Modify the code for vehicles classes. And here previously I have added the save option. So let's import the code for just the save. I'll show you the saving part is just this much. Where is that? So for saving, you need bunch of things, by the way. You need the you need like a codec, you need an output file name, you need the frames, the width and height, the frame rate, etc. So these things are used for that, but other than this, saving part is just this much. Out.write annotated frame. But I want the class names for vehicles. That is what I'm interested in. Let's see. Oh, is it? So Peter, I was using cursor until a few weeks ago. Then I thought, whenever I'm showing a demonstration, since many people don't use cursor, I know that industry professionals use cursor. They can also get that. It's $200, right? The actual pro subscription. The other one is $20 or something, if I'm not wrong. So I was using one of the versions. I forgot which, but then I switched back to VS Code. Anyways, what is the vehicle code? So these are the vehicle classes, I guess. 1, 2, 3, 5, 7. 1, 2, 3, 5, 7. So maybe I'll add that. And then let's see if for this traffic 3, it works or not. So is the code working for any of you? Like, did you manage to get the annotated people with the trailing lines? Okay, you see, this is working. So indeed, the classes are those numbers 1, 2, 3, 5, 7. Each one corresponds to a different vehicle type. I think they have trucks. So bicycle, car, motorcycle, bus, truck. So I don't think they'll have all the. So there are only 80 classes in the COCO classes, object classes. So you have to please take note of that. Yeah, so that is about object detection. So this is very cool, actually, this, tracking the trail. Since we have a few minutes, I also want to show you one last thing, which I thought I know that I went through this a little bit fast, but majority of this is not about YOLO or OpenCV. It's about the logic of adding the simple dot, right? So that part, I did not want to deliberately spend too much time on that. That's not the main point of the lecture, but let me show you the segmentation part now, because that is very, very cool. So let's open one more file, segmentation.py. Again, import CV2 from Ultralytics, import YOLO from NumPy, import NumPy as NP. And there is one small difference here. Please note this. It is not YOLO V8 PT. It is YOLO V8 Nano for segmentation. So you have to add this -seg dot pre-trained. Then we'll capture CV2 dot video capture. Instead of 0, I have this street.mp4. So I'll input that street video. And now while true, return frame equal to capture.read. Then results equal to, again, model.track. Here we are passing the frame. So source equal to frame. This is the syntax here. But we need to mention the classes. So classes equal to 0. Because in the street, we are only tracking people. We don't care about other things in the street. We can say persist equal to true. We can say verbose equal to false, just to prevent random things from being printed on the console. Then for R in results, so basically from the results, there are a bunch of objects. Annotated frame equal to, first we take a copy. And if R in the results, if there are no masks, then we should not do anything. But if R dot masks is not none, then we have to do something. And R dot boxes. So yeah, sure, we need boxes. R dot boxes is not none. And if the box ID is also not none. So if R dot boxes dot ID is not none. If this is the case, then masks, we can get the masks equal to R dot results, basically one instance of results dot masks dot data dot numpy. So we are converting the, and mask is nothing but the mask which defines the contour of the object. Boxes is the bounding box. So boxes equal to R dot boxes dot xy dot numpy, xy because there are 4 things you need for the box. Then ID is equal to R dot boxes dot ID dot numpy. Similar thing what we did. Now we say for I in I comma mask in enumerate mask. So basically inside the mask, there are several points. So person ID equal to IDs of 1, IDs of I, mask equal to mask of 0. This is not what I need. Now I need the, let's say, rectangle coordinates so that I can create the center. So person ID is IDs of I, then x1, y1, x2, comma y2 equal to boxes of I. Then I need one thing which we should do here, which I will first comment and show you, and then I will do it once again. We have to resize the mask because there is a default size in which the mask will appear. We have to resize it according to the frame size of our video. So we are resizing it as CV2 dot resize mask dot as type unsigned int, and we multiply it by this comma frame dot shape of 1, which is the y height, and comma frame dot shape of 0. This is the width. Then, so now we have, so I'll comment this and I'll show you if we don't resize what will happen. Then we need contours, comma dash equal to cv2 dot find contours for the resize mask. So the mask will have the person's contour, and these are the arguments, which is fine. cv2 dot draw contours, cv2, so that it will appear on the screen, and on the annotated frame we draw the contours. We can draw it as circles or whatever. BGR, I want red color, so 255, here it will be 0. Then that's it. We can put the text, but we can do that later also, or rather, yeah, let's put it. cv2.put text annotated frame with person's ID as the unique ID, and that's it. Now cv2.imshow, and if Q is pressed, you break out, then capture release, windows are destroyed. That's it. Let's run the code first and see if something is not working. Yeah, this should be results. Can't parse D size. Where is that? CV in the function resize. cv2.resize is I think what might be missing is we did not convert to NumPy in one of the locations. Dot as type int. Okay. I'll do one thing. Let's see what the issue is right now in the syntax. Can you tell me the syntax issue? Once I fix the issue, I'll share the code with all of you. Yeah, so we are converting to NumPy mainly, there used to be Python lists for storing array of numbers, and then later NumPy was introduced. NumPy is much faster. I have even created a full-length video on comparing why NumPy versus Python lists. So NumPy we are converting because it's the fastest way to take care of Python lists. Okay, first let's see what is the issue. Mask resize this. Wait, what is the difference? I don't see any difference. Oh, one bracket is missing, is it? Okay, fine. Okay, so that is fixed. Now let's see what is the other issue. If there is any other issue. Okay, everything seems to be fine. People are being recognized, and there is a ID that is being displayed, and there is the contours which are created from the mask. So the contours are the outer sides of outer edges of the mask, and that is working perfectly fine. I will do one thing. Let me share this video. This was the same video which I shared before, streets, but I'll share the code, segmentation.py. So just try out this code and see if it is working for you. So here, my point is this: we are not strictly using here. The magic is not done by OpenCV, although we are trying to understand OpenCV through these lectures. The framework that we are using here is OpenCV, annotation, doing things with the frames. Those things are done by OpenCV, but the hard work is being done by YOLO, because the pre-trained model comes from YOLO. It has nothing to do with OpenCV. So please understand that you can think of OpenCV as the skeleton which is being followed for this way in which you make annotations, save the video, process the video, do a bunch of things with individual frames, etc., or making the boxes, all of those things. But the hard work is not done by OpenCV. Okay, OpenCV has some libraries which, as we saw in the last lecture, which are traditional algorithms which has got nothing to do with deep learning. And there you can compare the pixel values, cluster the pixels, find the area of those pixel clusters. Those things can be done by OpenCV. But whenever it comes to deep learning, OpenCV primarily only allows inferencing, because here we are not training any model. We are inferring from an already trained model, right? So OpenCV does allow certain models to be used like this for inferencing, but not for training. But we will be throughout be using OpenCV as the framework, which we'll be following for processing images. Yes. So yes, Shivam, you can. So what I would like ideally all of you to do in the Discord is, I know that there are people from different walks of their life in terms of their number of years of work experience. Some people are students. So please make use of, there is a discussions channel in Discord. Please make use of that channel as a place to network, also as a place to initiate discussions, so that you can clarify someone else's doubt or you can get your doubt clarified. How can we use vehicles tracking part to estimate its speed? Is the correct method? Okay, speed part is very, I would say, straightforward. You have to know, first of all, you have to know a calibrated, an object of a known size. So if in the frame, you know the size of, like, let's say a bridge or something, then you know that each pixel is equal to these many meters, right? Then if you track the center of mass of movement, you know that from one frame to next frame, the center of mass has moved by these many pixels, which means from one frame to next frame, you know that the center of mass has moved by these many meters. And you also know that each frame, if it's a 30 frames per second video, each frame is what, 33 milliseconds or something, right? So basically you have moved X meters in 33 milliseconds. So X divided by 33 millisecond will be the, the speed of the vehicle. So yes, from the center of mass tracking, you can easily track the speed of any vehicle. You might have seen government installing many AI-based cameras, and these AI cameras capture your picture, and it also somehow it can capture two things. It can capture whether your seat belt is on or not if you are traveling in a car. It can also somehow capture your speed, and it also captures your this ID, or it can also detect your number plate. And at the end of the day, if you are over speeding or if you are not wearing your seatbelt at your home, you will get a in your post box, you will get a thing saying you have oversped and you have a fine that you have to pay, right? Yeah. So what else? I guess that's pretty much it that I wanted to cover today. I will be sharing all the details in the Discord server for pro people, plus in the course dashboard. So for the free people, you will get access to the recording, which I'm anyway also putting on YouTube. So we'll be doing that as well. The code files and handwritten notes I'll be sharing for the pro people. And one more thing which I would like you guys to try is try with different videos. So one thing I am interested, if you guys can try, is try for a high frame rate video or fast video to see whether accuracy is significantly diminishing. My experience is it is diminishing. Another thing which I want you to try is try for a slow video, but as I said, use empty bottles instead of filled bottles and see whether you are not getting something correctly or not. What else could you try? Another thing which I tried is there are videos where in YouTube, there are videos where people are grazing cows and they are tracking these cows or chickens from drone footage. So you need a different models for such aerial footages. So if you want to capture how many cows are grazing the field or how many vehicles are coming in the traffic from an over, like from a above the head kind of bird's eye view video. This is an example. This traffic.mp4. I will share this file with you guys. Just check that. There is also this aerial view. So obviously this current YOLO model won't work for that, but there are other models which will work. So just try that as a homework exercise. So this people aerial is like a set of people walking and a drone or something is moving. So it's not a static thing. Things are changing. So just try to see if you can use a different model to count the actual number of people in this video. It'll be very cool. Then I have another video, which is, this video is actually very easy because it's almost from the ground. But here the main difficulty is when two cars are significantly overlapping. If one car is covering significant portion of another car in front, then detection is difficult. Another thing which we will cover later when we come to segmentation is this crack detection. So this is a problem statement where there are companies who send small drones equipped with cameras through the pipe insides of these pipings, and detecting a crack somewhere far inside a pipe is very difficult. So these drones are equipped with cameras, lights, as well as other sensors. And if you can detect the cracks happening in the pipes in this way, it's amazing. It's a very, very industry oriented application of computer vision. So these were from my experiments. I mean, the current experiments that I'm running is not good enough for crack detection. But what else is there? I have, yeah, see, this is the saved video, which I just ran some time ago. It's saved video. It's working very nice. So what I was saying was, if you know this Japanese flag is 1 meter in width, and if you are looking at the same depth, of course, it depends on the depth, right? So if two objects are in different depth inside the field, then you can't use the same calibration. But there are a bunch of things you can do mathematically to know how much the size of a calibrated object is in the frame. How many pixels is that? Convert pixels to meters, convert frames to seconds, and calculate the speed. But I think we can wind up today's lecture here. I'll be sharing everything at the end of this. Thank you so much for listening. Please initiate your discussions in the Discord. I would really appreciate to have a thriving community there and try to network and find like-minded people as well. See you, everyone. We will meet again next week on Monday. And so now just one more thing. We have 4 more things to cover. So next I'll be covering RCNN. So RCNN has a series of RCNN, fast RCNN, faster RCNN, and mask RCNN. So those will be covered in the next 2 lectures. Following that, it'll be UNet. UNet you will also encounter in stable diffusion models. Then following UNet, we will cover YOLO, and following YOLO, we'll cover Roboflow. So that's the plan for this entire bootcamp. So I'll see you again next week. Take care. See you soon. We are in the second part of the course, and we'll be discussing about RCNN. RCNN is primarily used for object detection, but there is a variant of RCNN called mask RCNN, which is also used for segmentation. So just to remind everyone, one of the primary purposes of this course is to teach you techniques which can do segmentation, where you are actually detecting the boundary of an object, the contours of that, or an easier version of this, which is detection. So you draw a bounding box around the object. In the last couple of lectures, we saw how to implement this using YOLO, but we never went into the details of how the models themselves work. We were always just looking at the final result and just the in-code implementation. But today we'll be going into the details of how exactly were these models developed. What exactly is the theory behind the working of these object detection or image segmentation models, starting with RCNN. So the R in RCNN stands for regions. And I will tell you exactly why there is a regions term associated with the CNN. CNN for Simple Convolutional Neural Network. So let's take a step back. Let's say we were in 2012 or 2013, maybe 10, 12 years back. If we were to develop an image, an object detection algorithm, what might we do, right? Because AlexNet was already introduced in 2012. So by 2012, image classification was something that we could have done very easily. But right now we are talking about 2013 or 2014. So you know how to do image classification really well using AlexNet or VGG, other models. But now the objective is you have to detect the group of pixels inside which you have an object of interest. So let's say you have an image like this, which has a car, and your goal is to detect the bounding box around a car with some sort of probability percentage. Then the goal is to get something like this. You need a bounding box and you need some sort of like a confidence score. What would you do if you were building something like this without any additional thought? What is the most rudimentary algorithm that you might try? If you have any idea, just let me know in the chat. So the question is, if you were building a rudimentary algorithm for detecting the bounding boxes inside which you may identify a particular object, it could be car, it could be cat or dog, what is that you would have done? So while you type the idea, I will also just say it, but feel free to think on your own of what you could have done. So the simplest thing could be something like this. You take a random rectangle, right, which encloses some type of objects inside it. Sometimes it will be background, sometimes the part of the object will be there. And then let's say you are trying to perform a two-class classification where one of the class is a car, another class is truck. So you say you are now going to classify this particular rectangle into 2 plus 1 equal to 3 classes. One class corresponds to car, one class corresponds to truck, another class corresponds to background. So if you have C classes, you try to classify this randomly generated subset of pixels inside this rectangle into one of the three classes. Now, if you have AlexNet, you can easily classify this, right? Obviously, AlexNet will say this is neither car nor truck. AlexNet will easily classify this as a background. So done. You searched randomly in one rectangle and you found with pretty good certainty that this is neither truck nor car. It's a background. But just think about how many such rectangles are possible. Let's say the actual width of the image is W and actual height of the image is H. And let's say the width of your small rectangle is small w and the width of your height of your small rectangle is small h. Then basically you could place the rectangle here. There are many places where this rectangle could be, right? You could have the same rectangle placed here. I mean, let me move it up. It could be here, it could be here, it could be here, it could be anywhere without changing the width and height itself. So it actually will have W, capital W minus small w plus 1. These many regions, these many pixels along the width where you can place this rectangle. Similarly, you will have capital H minus small h plus 1. These many pixels along the height where you can place the rectangle. And since the placement along x-axis and placement along y-axis are independent of each other, you can simply multiply these two. So you have these many ways in which you could place this rectangle anywhere on this image. But that is not it. The width and height of the rectangle itself are numerous. So the width can be anywhere between 1 pixel to W pixels. The height can be anywhere between 1 pixels to H pixels because the maximum height of the image is H, width of the image is W. Now, if you look at the total number of rectangles like this that are possible, it's huge. So I have made a calculation here. Assume that your width of the image is 224 pixels, height is 224 pixels, you are now looking at almost 635 million boxes, 635 million rectangles in which your object could be there. So basically, now you will be performing a binary, or in fact, 3-class classification of these 635 million boxes. So what are the 3 classes? Truck, car, or background. It's so inefficient because it doesn't make any sense to search all the 635 million boxes. So what is the next best thing to do? You only search at some boxes, you only consider some boxes in which you think there might be this object, right? So those are called as proposal regions. So somehow magically, let's say I told you that, so in this, where is the car image? In this car image, let's say I told you that don't look at all the rectangles. Your object is likely found inside this rectangle, or this rectangle, or this rectangle, or this, like this. I propose you a finite number of rectangles, like 2000 rectangles instead of 600 million rectangles. And I tell you that these proposed regions have higher likelihood of finding the object. So all you need to do is check only inside these 2000 rectangles. Now your computation becomes much, much more reasonable. And this is exactly what RCNN does. R for region. So you are, instead of looking at the entire image, you are just looking at some proposed regions inside the image for the presence or absence of the object of interest. So now let's see how this is done. So now you understand, hopefully, what is the difference between the rudimentary approach of searching all the possibilities versus searching some possibilities. So first, what you do is you have an image, right? So the image may not be square shaped, but most of the neural networks, CNNs, that we are going to be using in the RCNN architecture will require square shaped input. So this RGB image will be converted into square shape. So if this was 224 by 440, it will be cropped or reshaped into 224 by 224. Plus, I mean, you will be multiplying it by 3 because there is red channel, green channel, and blue channel. So as you all know, the images are represented by pixel values. The red channel will have 224 by 224 values, where each pixel value can range from 0 to 255. Like that, there will be green channel, blue channel. Then what do? Then you perform something where you somehow magically get the proposed rectangle regions, which are those 2000 rectangles. Now, how do you get that? So for that, there are certain algorithms which are built using handcrafted logic. So there is no deep learning involved in identifying these 2000 potential candidates. What you look at is you could look at clusters of pixels with similar pixel value. So here, all these pixels have similar pixel value, like something like a brown or gray or whatever. All these pixels might have some green values. So just by looking at clusters of pixels that may have similar color, you could identify or you could propose some regions, right? There are also other ways in which, using the pixel values, you could define the geometry of an object. So in one of the works that I had done earlier, where 2 rice grains were touching. So let's say I have 2 rice grains whose boundaries I can easily find out when they are touching. But to identify whether there were 2 rice grains or 3 rice grains or 5 rice grains that were touching, what we did was we identified a centroid of this shape, something like this. And then we defined the radius of curvature like this. So, I mean, radius, which is radial distance from the centroid to its periphery. Now, if you plot this radial distance function, you can notice that at some point, the radial distance function will reach a minima. So let's say I'm going from theta equal to 0. So let's say this is theta equal to 0. This is theta equal to 10 degree, 30 degree, 60 degree, 90 degree, and like that back to 360 degree. So now if I plot theta on x-axis versus the radial function as on y-axis, you will see that there is a sudden decrease here and then there is an increase. So once theta reaches a particular value, my R will reach something like this and it will again start increasing. So this is one way in which I can identify that there are these regions where overlapping is happening. And if there are two such regions, two rice grains are touching. If there are more regions, more rice grains are touching. Now I'm giving you an example of a handcrafted logic. There is no deep learning. Very similar to that, you can construct just pure engineering logic to decide when you may have clusters of pixels that belong to same object. Now using that algorithm, you can easily get these proposed regions. You might remember that logic, similar logic we applied in the burglar detection project, where for detecting the burglar, we did not implement any deep learning. We simply implemented a plain logic that included changes happening to pixel values from one frame to another frame. So when we clustered those pixels, you will get a group of pixels, and then you can draw a bounding rectangle around those pixels. And what we did in the burglar detection code was we said, okay, if the size of this rectangle, if the area of these clusters of pixels are less than 200, discard them. If it is greater than 200, accept them. Now what we do is, now you have many proposed regions, right? Now I have to look at each of these proposed regions separately to see whether there is a car inside or not. So that is the logic that I'm going to describe here, but I will have a couple of questions here. Yeah, so Ahmed, exactly. So the name of this is called selective search. The name of the algorithm, what I'm saying is selective search. So you have an image, right? And this is the selective search proposed, one of the proposed regions, let's say. So this is not the full image. This is, you can say, part of the image. So maybe you won't have access to the full car. You can even say you have only access to part of the car, something like this, maybe. Now this image, which is one of the 2000 proposed regions, you have to classify. So how will you classify? You pass this through a pre-trained neural network such that this 224 by 224 by 3 representation is passing through some convolution layer, and finally it flattens out to some 4096 dimension representation. So this part of the neural network would be like trying to convert this RGB representation into another representation. Now this representation can be used for two things. One is to perform a classification to say, hey, this subset of pixels, which is one of the 2000 regions, has car, has truck, or has background. So it will perform. So this classification will perform a 3-class classification. And there is one more thing which performs a bounding box drawing. So there are two actions that are happening. I will repeat all of this once again. So first you have an image of a car. Then you will create 2000 proposals using selective search. Now you will have to process all the 2000 subdomains instead of 600 million domains, instead of 600 million boxes. You will process each of this separately. But now I'm going to say one example. So let's say you pick 555th proposal. Proposal means 555th bounding box. Then you convert the bounding box into a square image. You resize it into a square image. You pass it through a bunch of convolution CNN operations. And what happens is this 224 by 224 by 3 image will become something like 4096 by 1 representation. Now this representation, which results from a flattened layer, from this you have to do two things. One is, first you have to say whether there is a car or truck or background. This you have to say. Is that enough? No. You also have to say if car or truck is present, where exactly it is. So you have to draw a bounding box. So you also draw a bounding box. So this classification can be done by softmax, because you know that in multi-class classification, we usually use softmax. But in the original RCNN, they did not use softmax. What was more popular at that time was SVM, support vector machine. Now here, to draw the bounding box, BB for bounding box, okay? To draw the bounding box, you perform something called as regression. where you start with a random bounding box and then you try to move it in such a way that it is closer and closer and closer to ground truth. Now, let us take a step back, because before we go into anything further, I have a few questions to ask. Firstly, please tell me this. Support vector machine is nothing but you have a bunch of data points like this. Okay, you have a bunch of data points and you try to identify a line that best separates these two classes. Now, in SVM, you usually are doing binary classification. But here, there is no guarantee that you are only looking at a binary class. You could be looking at 5 classes, because maybe there are 5 different vehicles that you are looking at. Maybe there are 100 classes. So how exactly are we using support vector machine here to detect car or truck or whatever it is, to detect that object from the sub region? Why exactly, or how exactly does SVM work in this case? Can anyone comment anything on this? So my question is, SVM is used for binary classification usually, but here there is no guarantee that we are performing binary classification. It could be multi-class classification. So how exactly is SVM used? We know that softmax can be used for multi-class classification. So if we were using softmax, of course, no problem. But how exactly does SVM work here? So what is being done here is, in SVM, you train, if you have 20 classes, you train 20 different SVMs. So for example, let's say you had third class, another class here, okay? This is another class. So now you have to perform something sort of like a, I would say, 3-class classification. Then all you need to do is you train one SVM like this, another SVM like this. So the purpose of, or rather something like this. So one SVM could be something like this line. Another SVM could be something like this line. Now consider these 2 SVMs, okay? 1 and 2. The first support vector machine, what can it say? Anything to the right of that. And now I'm also going to call, let me just denote this by a different color so that you are not getting confused. So this can be, okay, so now this is class 1. Everything in this blue dot is class 1. Everything in this green dots are class 3. And these red dots are class 2. Now you have 2 SVMs here. The first SVM can say if something is class 1 or not. It cannot distinguish between class 3 and class 2, but this first SVM, this line, can say anything to the right of that belongs to class 1. If not, it's not class 1. So it's like in the Silicon Valley, hot dog versus no hot dog, something like that. So this can say class 1 versus not class 1. Similarly, this SVM, this guy can say, SVM2 can say whether something is class 2 or not, because anything to the left of that is class 2. Everything else is the rest of the classes. And similarly, if we had one more SVM like this, let's say this is SVM number 3, then this SVM can distinguish anything that is class 3 or rest of the classes. So this is how you can use SVM for multi-class classification, where depending on the number of classes, you have that many SVMs. So here, if you were having 20 different objects that you are interested in, you will be training 20 different SVMs. Similarly, the regression part also, which detects the bounding box, that also needs 20 different regressions. If you have 20 classes, one regression will be good at drawing bounding boxes around cats. Another regression would be good at drawing bounding boxes around trucks. Another for car, like that, depending on how many objects that you are training your RCNN for. But here is another question. What is the ground truth for your regression, and what is the ground truth for your support vector machine? Because you know the original ground truth. The original ground truth was whatever your image was, right? So if this was your image, you have a car image. Let me just copy that here. for car is here. The only ground truth which you are providing usually is something that looks like this. You have an image, you have a bounding box. So you will tell the algorithm, you will tell the neural network while training that the true class of whatever is there in this bounding box is a car. And the bounding box coordinates are x coordinate, y coordinate, width and height of the, so x and y coordinate are for this part, this kind of like origin. The width and height are the width and height of the, so this is the ground truth, the true class and the true location of your bounding box. So this information you are providing to the RCNN. But my question is not that. You know that SVM and regression are being applied not for the entire image. It is applied separately for each regions from the region proposal. And you have to do this for all the 2000 regions that are proposed. So what is the ground truth for this SVM? And what is the ground truth for the regression? Any thoughts? Like if the SVM has to be trained, how does the SVM know what is the reality? Because you are looking only at a part of an image. How do you know if this part of the image is car or if this part of the image is truck or something else? So to identify the ground truth, what you do is the following. So let's say your proposed region is something that looks like this. Okay, let me draw a rectangle. Let's say this was one of the proposed region. You look at a concept called as IOU, intersection over union. So you look at the total area combined by these two rectangles. So area of, it's not direct sum of the rectangle, but the total area that is spanned by these two rectangles. So that is the union area. And intersection area is whatever is the area of this region. So that is the intersection area. So whatever is the intersection area divided by whatever is the union area, that is called IOU, intersection over union. So now imagine if IOU equal to 1, it means your proposed rectangle looks basically like this. If your proposed rectangle was, now I have a question, right? So let's say this is your proposed rectangle. Now just tell me two cases, okay? In case 1, the proposed rectangle is here. In case 2, the proposed rectangle is here. So case 1 is this guy, case 2 is this guy. In which case is IOU higher and why? So this is the proposed rectangle 1 in case 1. And this is case 2. Just give me logically, why is case 2 better? Because in case 2, the intersection area is higher. That is the first thing. And the union area is lower, because union area, that proposed rectangle is not increasing the union area. So the IOU in case 2 will be higher. So in case 2, there is a, so what you do is to propose the ground truth. So now I have to, before processing the, these sub-regions, I have to let the algorithm know what is the ground truth for the sub-region, meaning I have to let my SVM know what is the ground truth for this case 1. I have to let my algorithm know what is the ground truth for the case 2. Now, let's say for case 1, the IOU equal to some number 0.23, right? Because it will be a number less than 1. Now, let's say in case 2, the IOU is 0.44. Then what I can do is, and one more thing I can do is, I can look at the IOU, and if IOU is greater than a certain threshold, then I can say that particular region, the ground truth corresponding to that particular region is whatever is the ground truth corresponding to this particular rectangle. So what is the ground truth of this original rectangle? It is car. Then I will say, if my IOU threshold is, let's say 0.3, then for this guy, I will classify it as background because it has neither truck nor car in it. But for this guy, because the IOU is 0.44, I will classify this as whatever is the ground truth of my original big rectangle. So here, the original big rectangle is enclosing a car. So the ground truth for this case 2 sub-region, which is this rectangle, is car. So this is how we can construct the ground truth for these sub-regions. And using that ground truth data only, we'll be able to train the SVM, because without the ground truth, how else will we train? Now, similarly, we can also train the regressor, where you know that, if you have a rectangle, something like this, if you have a region that looks like this, you know that you have this much overlap with the original ground truth rectangle, and using that you can say that the bounding box ground truth is something like this, and the original class, if IOU is, let's say, greater than 0.4, I will say for this sub-region the class is car, otherwise it is background. If there was a truck, I will say if IOU is greater than 0.5, it is like a truck, and otherwise it's a background. Now if it is a car, I also need to tell where is the bounding rectangle coming. In this case, the bounding rectangle, we can say it's coming here. And this also we will pass as the information to this regressor. And regressor will try to initially make random predictions about the bounding rectangle, but it knows the ground truth. So it will try to move closer and closer and closer to the ground truth. Similarly, SVM will also make predictions. Initially, the predictions will be random. Initially, SVM might say, oh, this proposed region encloses background, while it is actually showing a car. But then it will have a loss function, and the loss function will ensure that the SVM is also trained. So I will show you the entire network once so that you are clear. So just starting from the beginning, you have an input image, which you convert to square shape. And then you get the region proposals. There are 2000 regions instead of 635 million regions. Each of the 2000 regions, you pass through a CNN. I mean, you pass through a convolution and flatten operation to convert it into a different representation. And then that representation is used for classification as well as for bounding rectangle drawing. How is the classification done? A multi-class classification is done using a multi-SVM framework. Bounding box drawing is done using regression. Now, what is the total loss of this neural network? Because even if you are correctly labeling what is there inside the bounding, inside the small sub-region, the bounding rectangle drawing may be wrong. So there is a mean squared error loss corresponding to how well the bounding rectangle is drawn. There is a cross entropy loss, which is associated with the multi-class classification. And you can simply add these two losses to get the total loss of your entire regional CNN. And this loss is what you are trying to minimize while training the RCNN. Now, this is a huge, we will implement this RCNN today in code, but you might have identified how complex this is, because you have to do this process for every individual sub-region in those 2000 regions for every image. Now, if you are planning to train an RCNN on a set of, let's say, 1000 images, every single image will produce 2000 sub-regions, which means 2000 multiplied by all the steps starting from here till end. You are doing it for 2000 multiplied by 1000. What is that? 2 million, right? For 2 million kind of collections of pixels, basically 2 million sub images. So it's like a very, very time consuming approach, but it was working when it was proposed. So if I'm not wrong, I think this was proposed back in 2014 or something. But this was one logical step ahead of, like I would say, dumb approach of looking at all possible rectangles and seeing whether inside that rectangle there is your object or not. So, but this was not too far away. It was not very, very smart. The only smart thing that we were doing here was, instead of looking at all possible combinations of rectangles, you are only looking at some possible combinations of 2000 rectangles. Now, we can implement RCNN, but I want to give you okay, there is a question, object proposal, how is it doing? So object proposal is done using an algorithm called selective search. So that algorithm does not involve any deep learning. It's like a handcrafted algorithm. So there is no learning involved. It's like a fixed, rigid algorithm. And this algorithm based on the pixel color, texture of a group of pixels, and the size of that particular geometry, based on these factors, you can propose potential regions where you might find your object of interest. So that is how the proposals are created. Now, before we implement the RCNN, let's do one thing. Let's also look at another algorithm called fast RCNN. So tell me this much. In this entire RCNN architecture, let's look at this, right? In the RCNN architecture, what do you think is the most, I would say, most painful or most ineffective part? In your mind or in your opinion, what could be better in RCNN? Yes, SVMs, there are so many SVMs. So that part is a bit inefficient. Of course, that's a good answer. Right. Region proposal is an issue. There is an answer about training on huge images. So the image size, we don't have too much control over. Of course, we can always downsample the image size, but assuming that we don't have too much control over what the actual input images are. The images are what it is. But other than that, region proposal is a problem, right? Because for every single image, you are looking at 2000 forward passes through the entire architecture. Similarly, in SVM, if you have 20 classes, you are training 20 SVMs. It's also not good. So in fast RCNN, these two exact things were addressed. So firstly, just look at this. What are we doing in this particular region? In this region, what are we doing in this part? The only thing that we accomplish here is we are representing an input image in some format, right? The input image, which is 224 by 224 by 3, it is getting represented in another 4096 by 1 using a pre-trained neural network. So this could be a pre-trained neural network that has been trained on maybe millions of images from ImageNet. So essentially, you are trying to extract features from each of these region proposals, and you are trying to represent those features in another dimensional space. So here it is, the space has 4096 values. But why should you do this again and again and again for every single regions? You might as well just do this once so that you are representing the entire image using the CNN, whatever the CNN knows, because CNN is pre-trained on millions of data set from internet. So you can use a pre-trained network and you can already convert the features in your entire image, not just in your sub-region, features in your entire image, you could convert into a higher dimensional representation using a pre-trained neural network. And then you do your rest of the work. Then you somehow extract the interested regions and somehow you perform the classification and regression. But you don't have to be doing this part again and again and again. It's very inefficient to do this 2000 times because here you have to do it for every 2000 regions. But people realize that this part can be moved to this place, kind of. Not exactly, but I'll show you. But this part you could move to a place where you are proposing the 2000 regions after you convert your image into some higher dimensional representation using a pre-trained CNN. So I have created an image which kind of shows you the difference between CNN and RCNN. So just look at this image for now. So in RCNN, you have input image. You find 2000 regions using the selective search algorithm. From 2000 regions, which you kind of resize into a square shaped image, you pass that through some pre-trained neural network like AlexNet to get what? To get your feature vector, which is 4096 dimensional vector. Then use that feature vector to do two things. One is classification to predict the class. Another is regression to predict the bounding box. So this prediction of class and prediction of bounding box is something that everything does. So there is RCNN, there is fast RCNN, there is faster RCNN, and last is mask RCNN. In today's lecture, we'll be discussing RCNN, fast RCNN, and faster RCNN. Mask RCNN we'll discuss in the next lecture. Now, what is the difference between RCNN and fast RCNN? In fast RCNN, this part remains the same. Just look at this. This part remains almost the same, not exactly the same. If you look at this part, you basically have a feature vector. Then you are performing classification on one side, bounding box regression on another side. Here also the same thing is happening. But please note this. Here they switched to softmax classifier. Here they were using SVM classifier. So this is one good thing that fast RCNN did. And if you look at faster RCNN and mask RCNN, which came later, they all use softmax. So only RCNN was using SVM. The second thing is in fast RCNN, the way in which you get the 2000 proposed regions is very different. So you don't directly use selective search and you make a proposition for these are the 2000 regions, then pass through the AlexNet. You don't do that. What you rather do is you pass the input image through a convolutional neural network to get something called as feature map. Just one second. So once you get the feature map, which may look something like this, excuse me. So yeah, so this feature map is like a higher order representation of your image. It may not look like exactly your image. It won't be 2 dimensions. It can be multiple dimensions. It will be like a tensor. But this feature map will consist of, it will highlight the regions that are of your interest. Why? Because the CNN, which converts your image into this kind of like a feature map, already knows what are the relevant features for classification. So the CNN, the convolution operations, which are part of this pre-trained CNN, the weights, I mean, the values inside that convolution filter are attuned to recognizing or extracting the relevant features which are there in the image, which are useful for classification. Now, from this feature map, if you could, let's say you have 2000 proposed regions, right? Now from this feature map I have drawn here in X and Y dimensions, but this could have multiple dimensions because this feature map ultimately is a tensor. Now let's say you could say that, oh, this is the sub-region in the tensor, which corresponds to, let's say this selective search rectangle. Just a second. Then basically what you're doing is you have a region proposal, something like that, that looks like this, and you are just trying to map it to the corresponding region in this feature map. There is no CNN operation involved in this mapping. The only CNN operation that is involved is in creating this feature map for the entire image. So instead of passing every single 2000 subregions through a CNN to create like a feature map, you create a feature map using the CNN for the entire image once. So you don't do it 2000 times, you do it once. And then for whatever regions that this selective search is proposing among the 2000 regions, you pick one by one, and then you map it to this feature map to say, okay, this region in the feature map corresponds to this subregion. So there is no way of bypassing the 2000 region thing, unfortunately, because the basic way in which this algorithm works is you have proposed regions and you try to identify which among the proposed regions are the best candidate. Where are the objects of interest and where are the bounding rectangles? So that you cannot bypass, unfortunately, but you can make the process faster. So see here, in this image, this CNN AlexNet will go through 2000 region proposals. But this VGG here will only go through forward pass through it once because, excuse me, because you are only passing the entire image through it once. Now, this is how fast RCNN works. Now let's do one thing. Let's implement the RCNN first in code. We will spend a bit more time in fast RCNN and faster RCNN, and then we can come back to coding the faster RCNN. So today we'll be actually implementing the code in Google Colab, not in VS Code. The reason for that is we will need GPU access if you want to run the code fast. So I have GPU access here. Even if you don't have the GPU access, it is totally fine. But getting a GPU access in Google Colab is fairly easy. So let's do one thing. First thing is I want to share the data with you, the file that I'm using. So this is my data set. And I will share this link. Okay, so this is the dataset link in the chat. So first do one thing. Please open this particular Google Drive link and make a copy into your Google Drive. And then I'll tell you exactly what to do. This code link also I will share with you. So this is the link to the Google Colab notebook. So please make a duplicate of this Google Colab notebook so that you can also run the code along with me. And this time, unfortunately, we will not be coding this from scratch, because if we do that, it will take us at least 4 or 5 hours. But we'll rather go through the main parts of the code. Now, I hope you have access to both. So what you should do is the Google Drive RCNN data, you should make a duplicate in your Google Drive so that it's accessible to you. And Google Colab also, please, take a copy of that. Now you will have to install 2 libraries, which I have already done for myself. So you will have to install these 2 for yourself. Okay. Pip install selective search and pip install torch snippets. So most of you will not have either of these. So this is the only thing that you have to install. Then the second thing is the following. To get GPU access on Colab, what you can do is go to runtime, change runtime type. And here, by default, you will have only CPU and one of the TPU, T4 GPU and TPU. You won't have A100 GPU. So right now I'm using A100 GPU. That is because here at the bottom, there should be a link which appears for you, which says purchase additional GPU units, compute units. And I have purchased for, I think, $11, just one $11 purchase. So, but this is not mandatory, but I have seen that this code runs much faster with GPU. Then what we do is the other change that you have to make is once you run this piece of code, your Google Drive will be connected with your Google Colab. So when you run this block, it will prompt you to connect your Google Drive. Then you just click this, you log into your Google Drive, Google account, and just give permission to read. Just continue. And then your Google Drive and Google Drive will be connected to your Google Colab. Then what you have to do is, okay, I think I have to install torch snippets. The next thing is, once your installation is done, here the path, right? This path will depend on how the folder structure looks like for you. So to know what your path is, click this folder icon, click this Google Colab icon, so that, I mean, it should be enabled. This Google Drive icon should be enabled. Then click Drive to expand it. My Drive, click that to expand it. And here, when you expand, you should see that RCNN data folder. Just click to expand it. And now here I have two things. One is this images folder and one is this data frame CSV file. So click these three dots, copy path, and paste that path over here for the path of this image root. And the df.csv also, you click and copy path and paste it just here. So maybe it won't change you as long as your, the place where your RCNN data folder is coming is also in your drive. Then maybe this is not needed, but otherwise it will be needed. So please check this. And another thing is, sometimes when you paste your things in your Google Drive, it appears in shared with me. So if I share something with you, it appears in share with me. But if it is in your shared with me, from there, you have to right click and create a shortcut. So you just right click and click add shortcut and add a shortcut to your My Drive. So then I think you should be good to go. Then what we can do is we can run the code. But basically before that, can I just ask you, how far along are you? Are you able to run part of the code? Are these blocks functional? Can you just let me know? Okay, awesome. Are you using CPU or do you have GPU access? But even if you have only CPU, I can show you the results and you can continue running your code. One more thing which may be useful to you, when you run your code on Google Colab, what happens is, okay, run pod is fine. But otherwise, if you are running on Google Colab, what happens is sometimes if your screen kind of sleeps, then the Colab running will get interrupted. So what I have done as like a shortcut is screen sleep prevention. Actually, there is this, what is it called? This guy, keep awake. Yeah. So go to keep awake, Google Chrome extension. So you just install. So what I do is, if I'm running a collab, I just press this so that the screen will be awake. And then I won't run into the risk of, my collab disconnecting because my screen has slept. Okay, so basically the first part is just displaying the content of the CSV file, which you can open and see what is there. Basically, it is a bunch of images and then the annotations of those images in the CSV file. So that the ground truth rectangles, you will not draw directly on top of the image in the data, because then the data will be manipulated, right? Manipulated meaning you have a dirty data. Instead, the way the data looks like is something like this. So here the training data has, this is different data set, but I'm just showing you, see these images. There is no annotation in the image, but annotation come here in this file for that particular image. These are the annotations. For example, height is, for bounding rectangles, for example, yeah, see, bounding box, B box, 250, 616, 43, 124. So those are the X coordinate and Y coordinate of the starting origin. And then the other two ones are the width and height. So this is usually how training data will look like for object detection. So just run that also. And then the rest of the code, what it is doing is basically implement different parts of the RCNN. So in one, and some custom classes are also defined. So actually this code I did not write from scratch. I had to take significant help from cloud, Anthropic Cloud. But what I have realized is that getting a proper working code in RCNN is not very easy, because there are many parts that are at the same time functioning. So, but now I'm happy that I have this working code. So just let me just show you what the code is doing. So first it is reading the data set from the root. So image root, and reading and displaying. So you see, this is how the ground truth data image, on top of which the annotated rectangle are added, will look like. So here I think it's like a 2-class classification, truck or bus. So bus class, you can see here, it's feeble, you can barely read it, but you see the bounding rectangle and the bus. This is a very bad quality image, but this is how the annotation is. And here actually the car is being annotated as, maybe rest of the things are being called as truck. I don't know what is the definition of a truck, or maybe something that has a carrier behind is called as a truck or mini truck or whatever, but all of them are annotated as truck. Now, what we do is, so first here we have this extract candidate function, which is where the selective search runs. So selective search, we installed a library. If you remember, pip install selective search. So we are not bothered about internally what happens in selective search, but basically selective search algorithm will give us the potential candidates for those 2000 regions. So that is defined in this function, the whole thing. And here we are skipping, here we are eliminating few regions. So if selective search proposes duplicate regions, we will eliminate the duplicate. If the selective search regions are too small, we will eliminate it. If they are too large, we will eliminate it. And only those regions which do not fall into this category are being selected. Now, I will show you how a selective search region will look like. But once we have the selective search region, what is the next thing to do? We need to know what is the ground truth for the selective search region. Ground truth meaning whether the region includes a truck or a bus or nothing, and where is the bounding rectangle. So we first need to know the IOU, right? So we need to know the intersection over area for that particular region from the selective search, compared to the ground truth rectangle. What is the ground truth rectangle? If this was the image, this will be the ground truth rectangle. If this was the image, these will be the ground truth rectangles, these 3 green rectangles. So for the selective search region, we assign the ground truth value depending on the IOU. So that is why we have this extract IOU function. I don't have to explain it line by line, because then we will never end this lecture, but I'll at least show you what exactly each of them are doing. Then, so see here, candidates equal to extract candidates from image. So this is the input image IM. Extract candidates is the function which runs the selective search. Then from the candidates, now you can see that these are the bounding boxes from the candidates, the selective search regions, candidate regions in the whole image. So this IM at the top is simply the image name. We are just calling it as IM. But you can see that inside these region proposals are, by the way, covering most of the image. And now all we need to look at is which proposed region contain our actual object of interest. And object of interest here, you can see that there is something like a bus or something here. So maybe this rectangle will be finally what is picked, but we will get there. Then what we do is, for each candidate, we extract the IOU. Where is the extract IOU function? Extract IOU function is being called here, but it is defined up here. This is the extract IOU function. So for every candidate rectangle, we extract the intersection over area. If it is greater than a certain threshold, we say it belongs to that particular class of the ground truth rectangle. Otherwise, we ignore it. And then, yeah, this part is also basically for ground truth bounding box. But I just want to show you. So yeah, so in the example image that I'm displaying here, the IOU for the best candidate is turning out to be only 0.14. meaning there is not significant overlap between the best possible proposed region and the actual ground truth. The IOU is only 0.15, 0.145. The best possible value for this is 1. But now what we do is, this is the part of the code which takes a bit of time to run. So let this first finish running. So here you can see that the actual ground truth is here. The ground truth is here, but best candidate bounding box is this. So now intersection area is this itself. Union area is this. And this is turning out to be 15%, close to 15% of the total union area. So this was the 0.145. Now, can you let me know in the chat if you are able to run up till here, or whether you are facing an issue in running the code? Just let me know. And since I have already run the remaining part of the code, I will just show you some part of the results. So finally, I selected a random image while testing. So here, what we are using is, okay, in progress, right? Are you using CPU or just you have access to GPU? Anybody running this in, okay, T4 GPU, that will be better. Okay, anyone? Okay, A100 GPU will be good to have. Because in this course, anyway, we'll be training some models from scratch. So at least for this month, if you just purchase the GPU, I would say it's totally worth it. But while the code is running, let me just show you finally in the testing what I have achieved. So, okay, so I ran for 5 epochs and my best validation accuracy is like close to 80%. Training accuracy is 97%. So this is how it looks like. So, and can anyone tell me here? Okay, don't tell me the accuracy, at least tell me the loss. What does the loss mean here? Does it mean that my bounding boxes are identifying the object inside it really well? Or does it mean that my bounding box is being drawn in a very nice way, that the bounding rectangle is drawn at the right portions? Or does it mean both? Does it mean that my bounding box is being drawn at a certain place very well, and also inside that bounding box, whatever it is being classified very well? What does the loss mean here? Is it the classification, or is it the bounding box regression, or is it a combination? Right. So basically it's a combination. We are not just trying to do classification. We are not just trying to find the right place of the bounding box. We are trying to do both. We want to know what exists inside the bounding box. We also want to know the right position for the bounding box. So the loss, as I showed you here, is a combination of the cross entropy loss and the mean squared error loss. Over here, I had shown you so we have the cross entropy loss for the classification of the object inside the bounding box. We also had the mean squared error for saying how good your bounding box drawing is, right? So you are adding those two to get your combined loss. So the plot that you see here is for the combined loss. And as somebody mentioned, the validation loss is not reducing too much. So which is a sign of maybe overfitting, but not yet. But here you can see that when you plot the accuracy, after some point, after like 3 epochs, your training accuracy is continuing to increase, but validation accuracy has started to decrease slightly. I mean, these are only few iterations. It's not good enough to make a comment. But if I were to make a comment, I would say, yeah, kind of maybe overfitting is happening. So we might as well be better off stopping the training at 4th epoch or something. But training accuracy is good, 95, 97%. Validation accuracy is decent, like 80%. But these are my results. Now in testing, I selected a random image, which happened to be like a toy. And here you can see that the final proposed region is this. This is the proposed bounding box. And you can see the class here. The class of that bounding box is truck. So truck is correct. The even better bounding box would have been something that is just enclosing this, but maybe in the region proposal that did not come up for this particular image. So But for practical purposes, we have got the thing correct, but you can see that half of the image is being consumed by this bounding box. And in testing, we can, if any one of you have managed, all you need to do to play with the test data is change this number, change the index of the test data set of 1, of 5, or of 10. Then you can change this image randomly and you can see whether, you know, you are getting a good bounding box or not. But let me also check how much my code has progressed. Okay, so my previous thing has finished running. So I just need to run the rest of the code just to show you. Okay. Yeah, so this is the 3-class classification that I mentioned earlier. So here the class 0 is bus, class 1 is background, and class 2 is truck. Ideally, it's a 2-class classification. Actually, you know what? Sometimes here it could be multiple classes also, because a bus and a truck can be in one image, right? That is also possible. In usual classification, you will have only either or, but here it could be both. So, so we can't strictly call this as an original 2-class classification problem. But in any case, I'll show you how the training looks like. So here we are downloading the pre-trained VGG16. So VGG16 is a famous model. It was, if I'm not wrong, it was released in 2014. It came second in the ImageNet competition. So it was one of the famous models. AlexNet was the winner in ImageNet competition in 2012. VGG16 came to second. Are we to specify how many classes we need? Yes. So we have to specify the classes because the algorithm has no idea whether we are looking at buses, trucks, and background, because in many images there are many other objects, but we are specifying, right? Because in our training data, the bounding boxes are there available only around buses or trucks. So we have to also say that we are only looking at those two things plus the background. Then I downloaded the pre-trained VGG. Then this is the class for the RCNN. Yeah. So here is in this train batch function definition is where we are actually performing the training. This validation batch here is where we are actually performing validation. And when you run this part of the code, this part of the code, you will see the accuracy displayed as a function of epoch. So here you can see that. So my numbers are changing this fast, like 76 out of 400. If you do the same thing with GPU, by this time, only 1 or 2 batches would have been finished processing instead of 400. So that is how fast the A100 GPU is. And like this, it will run for 5 epochs. Okay. So this is the RCNN code. Now, today, I also want to discuss with you about one more model. So fast RCNN and faster RCNN, let's spend some more time and let's implement that in code. But before that, let us also know the historical significance of this paper. Nobody is using RCNN in today's lecture. But then why am I teaching you about RCNN, right? The reason why I'm teaching RCNN is I could dump YOLO in front of you right now, YOLO V8 or YOLO V11. But then what is the significance of these models if we don't know the struggle that we as humanity took to reach this stage? So RCNN has a historical significance in being one of the first models that showed that object detection from images, multi-object detection from images are actually possible using deep neural networks. So that was the significance of RCNN. Then in 2015, fast RCNN was introduced, but immediately after that, faster RCNN was also introduced. So now if you go to fast RCNN GitHub repo, you will see something interesting. So they have said that this has deprecated, meaning this is not under use anymore. Nobody uses fast RCNN also. People have moved on beyond fast RCNN. I will tell you what exactly is fast RCNN and what exactly is faster RCNN, but I just want to give you a historical context. These papers have anywhere between 45,000 to 50,000 citations. So RCNN has 44,000. Fast RCNN has something similar. This one has 55,000. Mask RCNN has 44,000. So these are highly cited papers in the computer vision literature. But I would say most of the modern, I would say, object detection techniques are a variant of faster RCNN. It's not a variant of RCNN. It's not a variant of fast RCNN. Then mask RCNN is used for image segmentation, which we will discuss in detail in the next lecture. But now let's come back and focus on fast RCNN and faster RCNN. So I have prepared this image just for to let us do that. So as I discussed before, the main innovation in fast RCNN were two things. I mean, softmax was not an innovation. It was just a change. And anyway, softmax is a better thing to perform multi-class classification than SVM. So this was the number one thing, which somebody mentioned in the comment that one inefficient part of the RCNN was having multiple SVMs to perform multi-class classification. So that was fixed by having a softmax. The second thing that fast RCNN do, which actually made things fast, was preventing the main, pre-trained neural CNN to be performing forward pass again and again and again 2000 times. So RCNN was doing that, but fast RCNN stopped doing that. It made only one forward pass of the entire image, not the individual regions. The entire image was made to forward pass through the pre-trained CNN like VGG16 to create a feature map. Now this feature map is what? Feature map is a higher dimensional representation of the features that are useful in the image. Now from this feature map, you can identify parts of that tensor. So this feature map will look like some tensor. So a subsection of that tensor may correspond to some selective search proposals. So selective search proposals are still being done here. The difference being proposing the 2000 regions in selective search proposal is not a difficult thing. Proposing those 2000 regions are fine, but passing those 2000 regions through CNN is the worst thing to do. So that we are avoiding. So we are still generating proposals of 2000 regions, but then instead of using a CNN to convert that into a feature vector, here those selective search proposal regions in two-dimensional image is converted into a higher dimensional region inside the feature map by performing a mapping. So if you have a tensor, which let's say using 2D, I am representing like this, although this may be multi-dimensional, then I might be able to say that, oh, this region in my feature tensor might correspond to this this proposed region. So you are bypassing now the pain of having to pass these 2000 proposals through CNN, and then you perform the rest of the things. So this is what fast RCNN was doing. Now, again, you might notice there is a pain here. Selective proposal is not a deep learning algorithm. It's like a handcrafted algorithm. There is no change to that algorithm. So why should we look at 2000 regions? Why not 100? Why not 10? Why not 300? Anything is possible, right? And to propose these 2000 regions, why are we using a handcrafted algorithm? Why can't we use a neural network? So that was the idea behind faster RCNN, where they entirely got rid of this selective search proposal handcrafted algorithm. Instead, they replaced it with something called as RPN, which is like a region proposal network. It's a neural network which will propose some regions. Propose some regions from where? Propose from some regions from the shared feature map. What is this shared feature map? Shared feature map is something that looks like this. The image converted into its features using a pre-trained CNN. So from this, to find the selective proposed regions, you don't look at the image again. You pass this whole thing through a region proposal network. And then you find that, oh, some sub-regions actually can be corresponding to a car, or it can be corresponding to a truck, or it can be corresponding to a background, something like that. So just look at the common things, okay? So this part is again common. You have a higher dimensional representation of the input, which you are converting, you are performing a classification on. You're also performing a regression, the bounding box regression and softmax classifier. So these two things are standard in faster RCNN. The input image being passed through a CNN backbone, it could be ResNet, it could be VGG, it could be LXNet, doesn't matter what we are using. So this is also common. So if you look at the fast RCNN, you have a convolutional neural network backbone to create a feature map. Here also, you have a convolutional neural network backbone to create a feature map. But in fast RCNN, so this is fast RCNN, you were using selective search to propose the 2000 regions, but here you use a region proposal network to get some proposed regions in the feature map, not in the image, in the feature map. And how many such regions? Only like, let's say 300 regions. So now you have a much better and much smaller set of regions to look at instead of 2000 samples. So you now have a much better representation of the features in the image because you have a CNN backbone, this guy, and you have a much better selection of your subset of regions where you might find your object of interest. You have 300 of them. And the good thing is this region proposal network is a learnable network. That neural network can be trained again and again and again through back propagation to make it much better. Here, the selective search algorithm, you don't make it better. It's already there. It's fixed. There is no back propagation to make this algorithm better. So that way, you now get rid of the rigidity of your selective search proposal algorithm. So this was the second innovation that people immediately figured out you could implement in faster RCNN. So the names are similar, but the idea is also very similar. And although the paper year in faster RCNN shows 2016 and this one shows 2015, my knowledge is that this faster RCNN was in fact proposed few months after fast RCNN, when people immediately recognize that, oh, now that we have a CNN backbone, we don't even need the selective proposal. We can simply have another neural network to find that. So this was faster RCNN. And let's do one thing. Before we move on to mask RCNN in the next lecture, today let's implement faster RCNN. And here I will show you one thing which you will find tremendously useful. So firstly, about dataset. Which dataset are we going to use? We are going to use like an aquatic animal dataset. So aquarium dataset from Roboflow. So just type this and this will open your Roboflow. It should ideally show this link. Then open that. Roboflow anyway, we'll be spending a lot of time on in the last part of this course, but I need aquarium dataset, Roboflow object detection. And here, just go to where is the dataset link? Yeah, so this is the link. So just go to this link. Yes, I will upload the file link in the dashboard. I will also share this fast RCNN code in the chat right now. So just, this is the Google Colab notebook. So just make a copy of that. But to get the data set, go to this link, this public.roboflow.com. This link I just pasted in the chat. Then go to this Coco JSON. So Coco I just mentioned in the last class. So Coco dataset was the benchmark dataset for object detection, image segmentation tasks. So common objects in context. So there was like a Coco competition going on, just like ImageNet competition for classification. So here, click on Coco JSON, and you might be prompted to log in. If yes, then just log in. And then here, click download zip to computer. So this file is not very big. I think it's only 76 megabytes or something. Yeah, 68 megabytes. So just download that. And once you download it, this is how the dataset will look like. Once you unzip the file, this is how the dataset will look like. So it will have a train, test and validation folder. Okay. Now in train folder, if you open, usually what do you see in a classification task? You may see 2 subfolders. If there are 2 categories or 6 categories, you will see 6 subfolders. But here you don't see any subfolder. you simply see a bunch of images, but you also see like a JSON file. So the subfolders are basic. I mean, these images are basically a bunch of aquatic animals from various aquariums. And there are, I think, 6 or 7 categories of these aquatic animals. And this JSON file is very interesting. Can anyone confirm if you can see the JSON file in my screen sharing? I'm just want to make sure this coco.json. Okay, thank you. So in this JSON file, just check this. There are 8 categories. I mean, fish, then I think ID 0 is none. I guess that is background. So fish, jellyfish, penguin, puffin, shark, starfish, and stingray. So those are the categories. And then every images have an ID and file name. So this file name, right? This image 249 JPEG.jpg, then some big thing.jpg. So those are the names of the images in these files. And then if you scroll down a little bit in this JSON, you will see that every image has an ID and every ID has a category ID. Category ID is the class, and they have a bbox, not ID, like a bbox 4 numbers associated with this, which is the bounding box width, height, and the starting point. And you have the area, then that's it basically. So this is the standard way in which the JSON-based notation for the COCO dataset looks like. So that's the reason why we downloaded it, because many models directly accept this kind of a data. So what I have done is I have uploaded this COCO dataset onto my Google Drive. So let's see if I can find the, actually I can just share the dataset itself. I'll find it anyways. So let me just first install these two, pip install selective search and pip, yeah, only selective search is needed. So this I'll install, and here also I am using A100 GPU. I don't want to use any other GPU. And connect to Google Drive. Can anyone mention in the chat if you managed to download the COCO dataset from Roboflow? So all you need to do is this: download it, unzip it, upload it to your Google Drive, and use that drive link. That's all you need to do. So that link you can just paste here in this part of the code. That's it. Okay, so once you connect your Google Drive, just okay, so that is loaded, and all you need to do is upload, and you should have this path ready, and then some transformations. And here is where rest of the things happen. So the architecture is fairly similar and straightforward compared to the previous one. Okay, data set is not defined. So yeah, so these are my IDs of the data set: fish, jellyfish, penguin, puffin, shark, etc. And here we are just extracting those names. And then loading the train data set. Then here is a sample data where draw bounding boxes. It's not defined. I guess. Yeah, matplotlib.pyplot will be needed for drawing. And so just let me know, guys, if you have managed to reach till here, or I think this might be part of the, yeah, it's not. Let me check. I don't think this needs any special function. Was used without being imported. Okay. Yeah, this was the import that was missing. All right. So now these are the bounding boxes, right? And the category I am not displaying here, but we could display it from the JSON file. Then there are 447 images in the training data. And here, I think we are using RESTnet, if I'm not wrong. Let me just go down and I'll confirm. Here we are using MobileNet, not RESTnet. Initially, I was playing with RESTnet a little bit. Then number of epochs is 10. Actually, this code is not that slow as the previous one. It's actually pretty fast. Okay, TQDM is not defined. Have you managed to run till certain point? Just let me know. Did you display this image yet? Because training might take a little bit of time, but did you manage to display a sample image from this, like this? Just let me know in the chat. Okay, got it. And while this is running, if my final image has not disappeared yet, I'll just show you what the output looks like. So basically the output will be similar to what we got from RCNN. There will be multiple bounding rectangles around multiple aquatic species, and it will also display the name of that species. So that is what we are looking at, right? So let me just make sure that. Yeah, so now we are able to run. So some in my code, some items were missing. So if you took a duplicate, just take duplicate once more now. So I was missing some imports, which is why the code was not working. So this TQDM was missing, and I was missing the matplotlib import. So just make sure that you have those, you have the latest version of the copy from now. And the 10 iterations should not take any time. And at the end, I'll show you the result. But I think we are almost there. We are pretty much done with the main part of the lecture. The remaining matter is just to display the result. Now, mask RCNN, although we will cover in detail in the next lecture, I will just tell you what is the extra thing it does. If you look at mask RCNN, it's exactly same as faster RCNN. It has a RESTnet or VGG or MobileNet, whatever is the background that is being used, right? Then the shared feature map is nothing but the higher dimensional feature map representing the features of interest. So this pre-trained neural network will convert the images into a higher dimensional representation. Then RPN, the region proposal network, will propose maybe 300 regions instead of 2000 regions. And those regions are now used for creating three things. One is a classification, another is a bounding box, and another is a segmentation. So this is the other main task, image segmentation, which we are in general interested in this bootcamp. So we are interested in object identification and image segmentation. And if you remember, we had implemented a image segmentation using YOLO V8 segmentation dot pre-trained. So this model we had used in the last lecture. So if the segmentation was not mentioned, we would have just gotten object detection. But when we mentioned segmentation, we got the contours of the people who are walking in the street. So just notice that that's what we'll be doing this time. So now this running has finished. Let me just check. Okay, so this is a random test data set. Okay, and here you can see the result. There is a shark here, shark, stingray, some random fish. I don't see the name. That's it. And if I change the number here, test data set 15 instead of 5, this should hopefully display another set of. So here you can see a starfish. This is a starfish. So this is the aquarium data set where you can play with. I mean, this is a toy data set. This is by no means an industrially useful data set, but this is like a toy data set which you can use to get familiarized with the actual object detection algorithm from scratch. So I think with that, we can wind up today's lecture. But what I want to ensure is that please message me after running the code if you have managed to get the result, or put it in the Discord if you haven't managed to run the code for some reason. The common issues that you may run into are mostly library importing issues. Other than that, the code I have spent huge time on to get it in a working shape. So I don't think you should ideally. Yeah, so updated code will be on the same link itself. You just need to make a copy once again. But anyways, I'll share the link once again. So this is the link for the faster RCN. So just to recap, there are 4 types of algorithms in similar category. First is the normal vanilla RCNN, then fast RCNN, faster RCNN, and mask RCNN. I forgot the year in which mask RCNN was introduced. Maybe it is 2017, if anyone can check. This was 2017, yeah. So mask RCNN was introduced later. So the timeline was, this is how it goes. Okay, and you can see that this one is smarter. So in RCNN, just to recap, you start with region proposals. You have 2000 regions. You pass each of the region through a pre-trained neural network like AlexNet or VGG. Then you extract features on a feature vector, and then use that feature vector to perform classification and perform bounding box regression. The classification was very bad. It was like a multi-class SVM, which later changed into softmax. Then for the rest of the models, they ended up using softmax only. Bounding box regression is common. It's used in all the models. Fast RCNN, what they did was they prevented you from passing the 2000 region proposals through the main neural network backbone. Instead, you move the backbone to before the proposal. So you use the backbone to extract features, then propose the regions, and you map the features. You map the proposed regions into the feature dimension, and then use that 2000 regions for performing classification or regression. But here also the problem was you are using selective search algorithm, which is not like a, it's not a smart algorithm. It's a hand engineered fixed algorithm. And faster RCNN, what they did was they nicely eliminated this selective search and they introduced RPN, region proposal network, which is another neural network. So this neural network will learn to propose better and better regions. The CNN backbone is anyway pre-trained, so it is already good at extracting features from the image. Then at the end, you have the feature vectors or feature representation, using which you perform softmax classification or bounding box regression. The only difference now the mask RCNN brings, which we will discuss in detail, is how the masking, the segmentation works using a mask. So with that, let's wind up today's lecture. I hope you understand the object detection part of this huge area of research and huge area of industrial interest very well. Of course, better than CNN, RCNN, you have YOLO. We will not, in industrial settings, we probably will be using YOLO V8 or later models, but it is very good to know where we started from. Like, it's very good to know how bad the initial models were before we even appreciating or before we even coming to the details of YOLO. So thank you so much. We will meet again on Thursday, same time. Take care until then. I hope you enjoyed the lecture. We will see in 3 days. Bye. Thank you. Okay, so welcome back to a new lecture, everyone. Today we'll be learning about image segmentation, specifically using mask RCNN. So this mask RCNN is a continuation of the other 3 CNN approaches, which we discussed in the last lecture. Specifically, we discussed about the vanilla RCNN. We discussed about fast RCNN. And also we discussed a little bit about faster RCNN. And mask RCNN is one more level above all these 3 in terms of what it can do. So we will first try to spend some time understanding how mask RCNN works. But before that, we'll also do a little bit of recap on the general approach of RCNN. And then towards the end of today's lecture, we will also implement RCNN for some specific data set. So there are mainly 4 objectives today. First is we will discuss a little bit about difference between detection and segmentation techniques. So as you all know, detection is where we draw a bounding box, but in segmentation, we just don't draw a bounding box. We try to understand the exact pixels that are contributing to a certain object. So we'll discuss about that a little bit. Then there are 2 segmentation techniques which you will hear about. One is semantic segmentation and another is instance segmentation. So let's discuss that about a little bit as well, because the next model which we will be covering, which is UNet, is relevant for one of these. And we will do a small recap of these 3 techniques which we discussed in the previous lecture: RCNN, fast RCNN, and faster RCNN. And finally, we'll come to the main topic of today's lecture, which is mask RCNN. So as I mentioned, the main difference between object detection and segmentation is nicely summed up in this picture. So in object detection, we are just trying to draw a bounding rectangle that as closely encapsulates the object of interest as possible. But in segmentation, you're doing one more level of implementing one more level of detail where you are looking at the exact pixels. So if you think about classification, detection, and segmentation, classification is applied to the overall image. You are trying to classify the entire image into one of the 2 or 3 or more classes. In object detection, you are going one more level deeper. You are saying, okay, I can classify this image as whether this is dog or cat, but I can also say exactly where the dog is in terms of a bounding box. In segmentation, you go one more level deeper and you say, not only I know where is the box that bounds this particular object, I also know exactly which pixels correspond to this object. So, and this is what we'll be spending some time on today, how exactly this is implemented. If you have questions during the lecture, feel free to add the questions in the chat. I'll try my best to answer the questions by looking at the chat time to time. Now, There are two segmentation techniques which you will hear about, especially in the context of mask RCNN. So this will perform one type of segmentation. And in the next module, when you learn about UNet, you will hear about another type of segmentation. So one type is called semantic segmentation and another is called instance segmentation. In instance segmentation, as you can see in this picture, there are 3 people and one object like a kite or something like that. And you can see that every single object has a unique ID denoted by its color. So this is person number 1, this is person number 2, and this is person number 3. And this is another object which we can call as whatever. So, but let's ignore this for a moment. Here you can see that although each of these 3 objects belong to the same class, the instance segmentation is able to distinguish them separately. However, in semantic segmentation, you won't be able to do that. As long as a particular object belongs to one particular class, all of them will be recognized as one single object, which is why here you can see that the color using which the object is denoted are the same, because these 3 belong to object class called person, class number 0 in YOLO, if you remember. So this is the main difference between semantic segmentation and instance segmentation. And there are applications in both cases. For example, if you were to detect cracks in a pipe, okay, so let's say you have a pipe and you have one small crack here, you have another small crack here. You don't want to detect, in many cases, you don't want to detect these two as 2 separate cracks. You probably just want to know how much of the area of this pipe is kind of defective or cracked. And in such a case, you would rather perform semantic segmentation because it's also pixel level accurate. You can perform pixel level classification in semantic segmentation. In instance segmentation, what you're doing is you perform selective search or you perform a region proposal neural network. And based on the selective regions that you are getting proposed, only those regions are under your consideration. In semantic segmentation, you are performing a pixel level classification. So for applications like this, semantic segmentation would make more sense, which we will learn in the next module, which is UNet. But in today's lecture, which is the primary focus is being mask RCNN, we will be spending most of time on instance segmentation. So that is the main difference. And now let's do a little bit of recap so that everybody is on the same page about how exactly RCNN works. If somebody remembers this really well, consider this as a refresher. So there are 4 sister models, so to say: RCNN, fast RCNN, faster RCNN, and mask RCNN. The timeline was something like this was 2014, I think. This was 2015, or maybe both were 2015, and first one was 2014. I'm forgetting the years. And the mask RCNN was 2017, if I'm not wrong. And basically, all of these models were proposed very close to each other in terms of timeline. So RCNN, what it does is you have an input image and you perform something called as selective search. Selective search is not a deep learning algorithm. It is a handcrafted algorithm which has no learning ability. But that selective search will propose 2000 regions, approximately 2000 regions, in which your object of interest might be there. Now, you only look at those 2000 rectangles to see whether your object is there or not. Then what you do is you reshape those rectangles into a fixed size like 224 by 224 pixels. Then you use a pre-trained CNN, for example, like AlexNet, so that AlexNet can convert your proposed region into a feature vector, maybe of dimension, let's say 4096, something like this. Then using the feature vector and using an SVM, support vector machine classifier, you can predict the class inside that particular region that you selected. And using a regression model for identifying where exactly is the bounding box, you can refine the coordinates of your bounding box defined by the X coordinate of the starting point, Y coordinate of the starting point, width of the rectangle, and height of the rectangle. Now, as we discussed in the previous lecture, if this was a classification for identifying 20 different type of objects, you have to train 20 different SVMs. and you also have to train 20 different regressors. So this was a problem. So there were two problems. First is the selective search is kind of like an issue, and SVM is not a great model because there are better models for performing multi-class classification like softmax. So in faster RCNN, what they did was something interesting. They moved this CNN to before this so that you don't have to run the convolution operation on all the 2000 regions because that will be so ineffective. So what is done instead is you pass the entire image through the CNN like VGG16. You could also use AlexNet, no problem. So the same neural network you could use here, no issue. But at the end of the day, it's a pre-trained neural network which can create a feature map. Feature map is a multi-dimensional representation of the features in your image. And then what you can do is you still run the selective search proposal algorithm to get 2000, let's say 2000 regions. And what you do is you map the rectangles which you get from the selective search proposal algorithm to the feature map. So feature map is multi-dimensional, but this one might be you can have 3 channels RGB and whatever is the region dimension, but you are mapping it to the feature map to get regions of interest. So you get regions of interest and then you convert that into like a fully connected layer, and then you do softmax classification or bounding box regressor. So you should notice that all the subsequent models use softmax starting from fast RCNN onwards because softmax became very popular by then. But there was again an issue. The issue was, first of all, you are using selective proposal again, which is not good. So this is not a good algorithm because you are not learning anything. And more importantly, you are also using something called ROI pooling. So this was a second issue. And that issue was not fixed in faster RCNN, but I will discuss that in detail. What is this ROI pooling? What is this ROI align, region of interest align? That we will discuss in detail today. But basically in faster RCNN, what they did was they had 2 neural networks. First neural network is this guy, which is a CNN backbone. It could be ResNet, it could be VGG, it could be AlexNet, but it's a pre-trained neural network which converts the image into a feature map. Now, from the feature map, you pass that through another neural network called RPN, Region Proposal Network. And this region proposal network can propose certain regions in which your object may lie. So here you are looking at 2000 regions to classify, but here you are looking at only around 300 regions. So you have 2 advantages here. One is your search is now limited to fewer number of regions. So your chances of finding the object in a much more accurate way is better. And more importantly, this region proposal network is not a fixed algorithm. It's learnable. So you can train this neural network to make better and better region proposals through back propagation. And finally, you do ROI pooling, where you map the region proposals to a feature space, and then you perform you perform both. In fact, you perform classification and you also perform regression to know the exact bounding box locations. So this is what we discussed until last lecture. So till here, we discussed properly. Now today we will see what is mask RCNN and how exactly it differs from, let's say, faster RCNN. One thing you should remember is that faster RCNN is the backbone upon which many segmentation models and many object detection models in the future was implemented. So RCNN is not at all used these days. This is very slow and it's almost obsolete. Fast RCNN is also not used very much these days. If I showed you the GitHub repository of fast RCNN last time, which literally says it's deprecated. And also the selective search is not a great algorithm because there is no deep learning involved in selective search. So these two are not really used these days, but many variants of faster RCNN still exist in different forms. So faster RCNN and mask RCNN are the 2 most important algorithms that you should take away from the RCNN family. Now let's see what exactly is mask RCNN and how can mask RCNN perform segmentation while faster RCNN can only perform object detection. It only does bounding box drawing. It cannot create a mask which tracks the contour of the object. So just look at the structure difference, right? So first of all, there is a CNN backbone here. There is no difference here. Basically, it's pretty much the same. I will show you in code also. Then it converts the input image into a feature map. So this part is also the same. There is a region proposal neural network. This part is also the same. You have a neural network which proposes regions. Then the number of regions that you're looking at might be close to 300. So this part is also pretty much the same. But now there is a difference. Here there is something called as ROI pooling. Okay. In faster RCNN, here there is something called ROI align. ROI for region of interest. I will discuss exactly what is the difference between these two. But just understand that ROI align is obviously better. And that for that reason only ROI align was selected. But let's discuss what exactly it means. And you should notice one more difference. In mask RCNN, the final features are passed through 3 parallel branches. Branch number 1 performs softmax classification. So the bounding box, inside the bounding box, is there a cat? Is there a dog? Is it something else? The bounding box regressor draws better and better bounding boxes, which encloses the object really, really well. And then there is one mask head, which creates segmentation mask. And this mask allows us to perform segmentation. So this mask is like a binary mask, which is, so let's say this is a car. The mask of this could look something like a binary image, where if the car is somewhere here, all those pixels could be in one color and everything else in the background will be in another color. So the mask is something that looks like this. So we will implement this on a data set today. But this is the main 2 differences between mask RCNN and faster RCNN. The ROI align, that is the difference number 1. The presence of this 3rd parallel branch, the masking branch, that is the second main difference. So let's see how do these 2 things work. How does masking work and how does ROI align work, and how is it different from ROI pooling? So let's discuss that before we go ahead and implement this architecture. So this we already discussed. Okay, so now let's discuss how does masking head work. So as I mentioned, the masking head takes features from a region. So the region proposal network RPN will propose bunch of regions. So let's say 300 regions. Okay. Now these 300 regions are kind of somehow mapped into corresponding features. So these 300 regions originally might be in 2-dimensional form with RGB channels, but in the feature vector, in the feature space, it's a tensor which may have many more dimensions. But basically, whatever regions that are proposed by the region proposal network, from that, you take the subspace of the features as the input into this mask head. So mask head is nothing but the 3rd parallel branch in the mask RCNN. Now, the output is nothing but a 28 by 28 pixel binary mask. Why do I call it as binary mask? Because I showed, as I showed you earlier, if the object that is supposed to be there is like a car, then everything inside this car pixel would be some white color or vice versa, and the background will be another color. And this mask is created for each possible class. What do I mean by that? So let's say there are 2 classes inside a data set. You have cars and trucks. Now, let's say in your image, you have only a car. There is no truck. And let's say your background is supposed to be black in color and the object is supposed to be white color. So this is mask number 1. And this corresponds to car class. For the same region proposed by the region proposal network, you construct mask for every possible class. So here, this is the mask 1 for the car class. And this mask 2 for the truck class. What should this look like? What will this mask look like? Can anyone mention in the chat? So I have an image. So my image, the region proposal network has, I would say it has proposed a region in which there is only a car. So that particular region that we are looking at right now is just a car, right? So, and the mask head is supposed to create masks for each class. There are two classes, car and truck. And because that particular region has a car, the mask corresponds to car, has a car mask, and the background is black. And since there is no truck in this particular region that we are currently talking about, its mask would simply be whatever is the background, something like this. Because in the current region, there is no truck. But let's say we are looking at another region proposed by the region proposal network where there is only a truck, there is no car. Then in that case, the mask would look something like this. The mask 1, which corresponds to car, will be just the whatever is the color we put for background, white or black. And the truck, which is mask 2, will be exactly enclosing the actual truck in the image. So let's say this is the truck. Okay. So this is how the mask number 2 will look like. And the exact location of this truck mask or the car mask would depend on where exactly is the truck or where exactly is the car inside the proposed region. So it won't, all the truck masks will not look like this. In some images, maybe part of the truck is visible. And in that case, let's say the back side of the truck is visible. Then all of this will be whatever color corresponds to background. And this will be the partial mask that denotes truck. So it depends on how the proposed region itself look like from the output of RPN. Now what happens? So let's say the feature maps from regions of interest. Usually they are of small size, like the feature map dimension will be like 14 by 14 or something like that. But the output that you are, okay, there is a question. These classes are predefined. Yes, exactly. So the classes has to be predefined. In RCNN, the training data would look something like this. So if you remember from the last lecture, we looked at an aquarium data set in which there were 7 categories of aquatic animals. And that particular faster RCNN could only detect those 7 categories of aquatic animals. If an 8th category comes, that particular neural network is not trained for that 8th category, just like any binary classification. So in a cat versus dog classification, if suddenly a penguin comes, you won't be able to get the right answer unless you train for it. And similarly, even for masks, you are only looking at the particular object that your neural network is trained. So if you look at the feature map, right? Just let me scroll up. So if you look at what this ResNet is good at doing, this ResNet is really, really good at converting the images into features. Now, this region proposal network is a trainable network. And trainable network means what? It will have, if it makes a very bad prediction. So let's say it creates a mask around a bicycle, where bicycle is not even a class that you are considering. Let's say there is a truck and a bicycle in an image. And let's say this region proposal network proposed a region around the bicycle. Then what will happen? Because it's not in any of the class, the predicted class will still be either truck or it will be close to truck or close to a car. But what you have is a bicycle, which means the loss will be very high. The softmax classifier will give you a very high loss. Your bounding box regressor will also give you a very high loss because your ground truth rectangles in your input data is not around bicycle. They are around trucks and cars. So even if the region proposal network somehow by chance creates proposed regions around other objects which are not part of your training data, because it increases the loss during your training in the softmax classifier or in the bounding box regressor, and that is 2 big parts of your loss, right? Your overall loss function. You will not eventually, after training, your RPN will only be trained to predict features around objects of interest. And because of that, this mask head is inherently only getting the proposed regions as the input. And what are the proposed regions? Either trucks or cars. You won't get bicycle as the proposed region. Is RPN a trainable network with pre-trained weights or randomly initialized? RPN, to my understanding, we initialize it randomly, and then we can, there are some pre-trained models which we can download where both of these, the CNN backbone and the RPN are pre-trained. But in the recent codes that I have been running, RPN was not pre-trained. RPN could be trained as part of this overall training process. Because regressor is anyway trained if you are training your network. This classifier is also being trained. So RPN is also being trained. Only this part is not being trained. ResNet, you take a pre-trained network. Okay, so this is how the masking works. It can only identify objects that are part of your training data. But here is the question, right? You have, let's say, feature maps that are generally small in size. So typical sizes of outputs you get from your ROI interest regions are like 14 by 14. There will be multiple channels, but typical size in XY direction is 14 by 14, let's say. And you have to perform some convolution during processing. And the final output, as I mentioned, from your mask is like a 28 by 28 pixel square image, something that looks like this. So this is 28, 28, this is 28, this is 28, this is 28, this is 28. But here is the question. Usually in convolutional neural network, when you go from input to output, right? So let's say input is like a 512 by 512 image. Eventually in CNN, the size only decreases. And how does the size decrease eventually in CNN? What causes the dimension to decrease, dimension of an image to decrease? The number of channels can increase. I'm not talking about that. I'm talking about the XY dimensions. Pooling. There could be max pooling with different strides. And because of that, the size 500 by 12 by 512 can decrease to, let's say, 32 by 32. This is normal in CNN. But right now, what we are talking about is some sort of operation where you go from 14 by 14, perform some sort of CNN operation, convolution operation, and you want to get to 28 by 28. Something like this. How is this possible? Also, there is a question, how are the pixels of an object identified during the mask? Is it from the feature map? Exactly. It is from the feature map. So, and also the weights in the convolution operations that are happening, although it's a small network, although it's a small neural network, this mask, right? There will be ground truth for this mask. So first of all, softmax has a ground truth. What is the ground truth? Whether the bounding boxes bound a car or a truck. Okay, so this, if car is 1, 0, either the ground truth is 1, 0 or 0, 1, right? For softmax. What is the ground truth for bounding box? The ground truth for bounding box is X1, Y1, W1, H1. What is this? These are the coordinates of my rectangle, 4 numbers which I require for my rectangle. Now, what is the ground truth for my mask head for during training? The ground truth will look something like this. So if my ground truth image is car, then it will look like a mask, literally a mask, something like a 28 by 28 mask with background being black and the object being white, or vice versa, depending on how the convention is. Now, if the mask head prediction is not like this, so let's say now this is the ground truth GT, and if my mask is predicting something like this prediction, then the loss because of the mask head will be so high because the prediction differs from the reality. And now, if you add the loss due to the prediction of class, due to the prediction of bounding box, and due to the prediction of mask together to combine that into one single loss, the mask eventually has to make better and better predictions as the training progresses. That's the way in which the loss function is structured. And that is the reason why ultimately the mask head will be able to make predictions which look like something that encloses the actual object boundaries, right? Okay, so now let's come back to my question. My question is this. Usually this is what you do in a convolution. You don't increase the size. Your size decreases during pooling operation. But here you can see that surprisingly your feature map could result in dimensions like this, but ultimate output you want from your mask is 28 by 28. How do you do this? How do you go from a small dimension to larger dimension? So Surya has mentioned interpolation. That is a good answer. Sure, you could do interpolation. the basic idea is the following. You try to, so let's say the neural network learns something like this. Let's say if there is a feature like this, okay. I'm considering a small portion here of 7 by 7 pixels. So let's say there is a feature that looks like X. Anyway, this is like an abstract space, right? There is no, this is not a directly like a picture, but this is more like a picture because this is like a mask, a binary mask. So this has meaning. This does not have meaning in our world. It has meaning in the world of tensors. But now let's say the neural network is learning something like this. Whenever you detect small features like X, then in the mask, you have to construct something like bunch of circles. Basically, what I'm saying is whenever in this abstract feature space, which has small dimensions, whenever there are small features like this, let's say the neural network could learn that through interpolation or through just simply by adding numbers meaning adding additional pixels, you have to construct certain shapes in a certain way. And if this can be learned, then what that means is in this space, in the feature space, you have a small region which has so much information density that it actually corresponds to some meaningful thing in the actual image mask. So you will see instances like this later in UNet also, where these abstractions are actually corresponding to something in our world of very profound meaning. So this can be done using various ways, but at the end of the day, what this is called is something called as deconvolution or transpose of a convolution. So let me just show you this. So you could have a regular convolution where you have a 3 by 3 kernel in the middle, 4 by 4 as the input, output is 2 by 2. And this can happen depending on the padding or stride, right? You can decrease the output dimension. Same thing you can do here. You can add padding. So for example, if your input image is something like this, 2 by 2, and let's say your filter is something like this, 1 by 1, and let's say you add a padding of, I would say maybe 1 by 1. So I'm adding 1 extra pixels at the boundary so that after padding the input of 2 by 2, so input was 2 by 2, but after padding this became what, 4 by 4. And after padding, you are passing through a 1 by 1 filter with stride equal to 1. And here padding is also 1. And what will the output of this be? What will be the output dimension in this case? Your stride equal to 1. Stride means the number of steps you take. Stride equal to 1, and you padded 1 pixel. So padding equal to 1. That's why 2 by 2 became 4 by 4. And if this is your convolution filter, which is moving along this padded input, what output can you expect in terms of dimensions? 4 by 4, because initially your filter would be here. Then you will multiply the value of the filter with the value of the pixel. Next, it will be here. Then next, it will be here. Next, it will be here. And each of those produce one unique output. And then you will move here, here. Then you will move here, move here, move here. Then you will move here, 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 here. Like that, there are total 16 pixels along which your filter will move. And why are we moving in step of 1? Because stride is 1. If stride was 2, you will start from here. Then you will jump to, you will have a gap of 1 pixel. Then you will start here. Then you will jump to this. Then you will go here. You will jump to this. You will go here, jump to this. In that case, if stride was equal to 2, the result here will be 2 by 2. Similarly, if padding was not there, if I remove this padding, let's say, and let's say my stride equal to 1, my filter is 1 by 1, my stride equal to 1, padding equal to 0. Okay. In this case, what would be the output? Stride equal to 1, padding equal to 0. Output will be 2 by 2 because you have 2 pixels to move horizontally and in the other direction also. But what if your stride was 2? What will happen to your output? Your output will become 1 by 1. So if stride was 2, padding is 0, instead of 2 by 2 output, you will have a 1 by 1 output, because you will start your filter over here, but then your stride is 2. 2 means you are out of the bounds. So you have only 1 pixel as the result in the first row. Similarly, in second row, you start from here, stride is 2, but then there is no pixel there. So output will be 1 by 1. So this is how convolution operation, depending on certain parameters, it can sometimes decrease the size of the output. It can sometimes increase. Now, usually in padding, we follow certain rules, right? In padding, we sometimes pad with the same values as that of the boundary pixels. Sometimes we pad with values of white pixels. Sometimes we pad with values of black pixels. Padding has many rules. But in our case, we can't do random padding. Padding has to follow certain rules such that it carries certain meaning in this feature space. But let's not go into the detail of that. But at the end of the day, you perform a convolution operation, which is almost like a transpose convolution operation, where you are going from a low feature map to low dimension feature mapped into a higher dimension output. At the end of the day, this is what's happening. So I have written a sentence here. This I found somewhere on the internet. Basically, I like this. So what it is saying is the convolution patterns learn that there is a car-like pattern here in low resolution space, which is that the feature map. And then the transpose convolution learned that whenever you see a car-like pattern in the low resolution space, which one is that? In the feature space, you should create a specific pixel pattern in your output. So this specific pixel pattern is in the 28 by 28 pixel space. This car pattern that we are talking about is in the feature space of 14 by 14 by multiple channels. So n number of channels could be there. And so this is what I talked about here. Whenever you see a particular pattern in the feature space, it could be like a shape of X. It's something that is abstract. But whenever you see a pattern in your abstract feature space, you basically has to construct some sort of specific geometric patterns in your final output mask. And this is exactly what the deconvolution or the transpose convolution learns. Now, let's discuss a little bit about the idea of ROI align versus ROI pooling, because we discussed that ROI align is what was used in faster RCNN, but ROI pooling is being used in mask RCNN. How exactly does that work? Opposite, I messed it up. ROI pooling is done in faster RCNN, my bad. And ROI align is done in mask RCNN. Okay, so this is the idea. Let's say you have, so first let's start from the faster RCNN, which was the last lecture thing, but we did not discuss ROI pooling in detail there. So let's say you have a proposed region with region of interest of dimension 10 by 15. There are many channels, so we are not considering the depth dimension, number of channels. Just look at the width and height. Let's say there are 10 pixels height and 15 pixels in the width. And let's say your desired output, which you need to pass into your softmax classifier or whatever you have next after your ROI, or into your fully connected network, because you have a fully connected network at the very end after pooling and fully connected, ROI align and fully connected. So before you pass into this, let's say you need a specific dimension as the input to that. And let's say that dimension is 2 by 3. What can you do? What can you do to convert your region of interest from a dimension of 10 by 15 into a dimension of 2 by 3? What you could do is something like this. You do a max pooling where you have a filter size of 5 by 5. Okay. So what you start with is you start with something like this. So this is the 5 by 5 filter. So and this is a set of 25 pixels. Okay. Please remember that. So from this 5 by 5 filter, let me just, you do something called as max pooling. What is max pooling? You pick whichever pixel has the highest intensity, whichever pixel has the highest value, you pick that. Then you move it here. Then you do one round of max pooling from these set of 25 pixels. You get another number. Then you move it here. You again do pooling. You get one more number. So right now, along the width, how many numbers you got? You got 3 numbers. And what is the desired output along the width? You need 3 pixels along the width. So that satisfies your criteria. Similarly, since this dimension is 5 by 5, along the height, so along the height, you can only move twice. My drawing is bad. Maybe I'll draw like this. So first you will go here. You have a pooling, and then you will be here. Yes, assuming the stride is also 5, exactly. And then you move here. You have again max pooling, which means along the height, you can get 2 numbers as the output. So this is how you can exactly go from an input of 10 by 15 to an output of 2 by 3 without, I would say, without neglecting any pixels. Here, all the pixels are somehow covered. You are not neglecting any group of pixels. But now imagine the case where your region of interest was actually not 10 by 15, it is 11 by 16. Then in that case, what would you do? And let's say, because this region of interest is not in your control, the region proposal network will propose whatever region it thinks is the region of interest, right? So you don't have control over what the ROI is. But this required output is something that you need in a certain format. So this is something, although not in your control, it's fixed, like it won't keep changing. Now imagine you want to construct a max pooling filter. If you were to divide 11 by 2, you are left with 5.5, and you can round it down to 5. Similarly, if you divide 16 by 3, you are left with 5. You have 5.33, which you can down round off to 5. But see, the problem with this approach is you have a max pooling here, okay? And if you do the stride of 5 in this max pooling, what's going to happen is this. You are left out with one last row at the bottom and one last row at the right side in this column. So basically, what I'm saying is, in the region of interest, you are kind of leaving out some set of pixels here. And this is because it's 11 and 16. What if I had something like, okay, 12 is not an issue here. What if we had 11 along the height and 17 along the width? Then how many pixels would be left? So let's say this was, instead of 16, this was 17. What would happen? You will lose one more row here because you will have, if you divide 17 by 3, yeah. So my question is, we want an output of 2 as the height and 3 as the width, okay? Our input dimension is 11 by 16 right now. And this, as we discussed, it results in a loss of one row of pixels, one column of pixels here. So this is lost. We are not max pooling from these pixels. Why? Because when we have a max pooling operation like this, let me just group it. When we have a max pooling operation like this, I start from here. So this is 5 pixels by 5 pixels. Then I jump once here. It's 5 pixels by 5 pixels. Then again I jump. It's 5 by 5. Then after that, I don't have enough pixels to pool because I have only one more column of pixels remaining. So my max pooling will stop. So it's as if I'm rounding off, where I'm only looking at totally 10 pixels along the width. And I'm using a max pooling of 5 by 5, and I'm having a stride of 5. So essentially what this means is this one column of pixels is lost. That information is not being used to construct this output. And now look at the height. Height wise, I'll start from here. I'll do max pooling. I can go here, I do max pooling, but I can do it only 2 times because by the time I do it 2 times, 10 pixels are already covered, but I have 11 pixels along the height. The remaining last row of pixels are now neglected. It's not part of max pooling now anymore. So what is happening as a result of this? As a result of this, I am losing out valuable information from my region of interest. Valuable information from where? Valuable information from this region and this region. It's lost. Now imagine, okay, imagine that this number was 17 instead of 16. How much information will I lose? what will happen if this was 17 pixels wide and this was 11, I don't want to change this, then what will happen is there will be 2 rows of pixels that are lost here. Because when you divide 17 by 3, you can have 15 and then you have a remainder of 2, right? So basically you have even more extra loss of information. So this loss of information from your region of interest, so your RPN, your region proposal network, is doing a lot of hard work to propose very, very good regions. But just because you have a very bad, pooling operation, you are basically not taking the hard work of your RPN into consideration, and you are losing a lot of information by the time you reach here. And what happens as a result of this is the mask or the region that is proposed, right, at the end of the day, using your faster RCNN will not be as good as what you would like it to be. So if people were using this one for mask RCNN, like if instead of ROI align, which we will come to in a moment, if people were using ROI pooling, which is a very quick and dirty approach, you will not have very, very nicely bounding masks around your images. So that was the problem that people who proposed ROI align wanted to solve. So ROI align is very interesting. It's simple and interesting. So let's say, yeah. So edge averaging, exactly. So this averaging sort of like interpolation technique is what exactly is used in ROI align. So basically you have, let's say 11 by 16 pixels. So it's an imperfect, you can't exactly divide 11 by 2 and you can't exactly divide 16 by 3, but that's okay. So you don't approximate 11 by 2 as 5 and 16 by 3 as 5, but you keep it as 5.5 and 5.33. Okay. Then what you do is, in every cell, so you will be dividing this by cell. So you have basically 11 divided by 2, you have 5.5 cells, and you have 5.33 cells. Okay. Then what you do is each cell is divided into 4. So you have one of them is 5.33 and this is 5.5. And what you do is you pick 4 points as a grid in this cell. So you have 1 point here, I mean exactly in the center, 1 here, 1 here, another here, and another here. And if you look at the coordinate of this will be 1.33, 1.375, which is what is written here. Point number 2 will be 4, 1.375, that is this. And then third point is this, and fourth point is this. So basically you construct a grid of these 4 points. Okay. Now, here is my question. Okay. Let's say you want to calculate. So usually what do you do in max pooling? Usually what happens is in max pooling, let's say your pooling filter is like 5 by 5. It will look like this. So this is 5, this is 5. And if this is your input, the output pixel, I mean output image, will be behind this, and you will have some pixels which have maximum value. So let's say this pixel has value as 233 and remaining ones are less than 233. Then there will be only one output coming out of this max pooling, which will be this number. This will be 233. But here the issue is you don't have 5 by 5. You have 5.5, 5.33. So it's like a weird cell. Now, how exactly will you do some sort of like a pooling operation using this kind of a filter? You can't do it. So what you do is you perform something like interpolation. So this is what the interpolation look like. So let's say you have these pixel values A, B, C, D. Okay. So these are the pixel values. And now what you are left with is you want to perform some operation at this point, 1.33 comma. So here I have put an example. So your point, however, the point that belongs to the mask is, let's say, at 1.3 comma 1.7, which is somewhere here. Usually what is the case? Usually the filter and the input are perfectly aligned. So you can do one-to-one multiplication. But here there is no perfect alignment. Your points are kind of
offset. So here what you do is, in the top row, here you do A multiplied by 0.7 plus B multiplied by 0.3. Basically, what you're saying is, because your point is here, the point corresponding to your filter is over here, you are including the whole part of A and a little bit more. So basically, A is getting multiplied by a bigger number, B is getting multiplied by a smaller number. So this will be the output from the top row. The bottom row will get converted to C multiplied by 0.7 plus D multiplied by 0.3. Okay. And then what you do is you interpolate once vertically also. So right now it was a horizontal interpolation. Then you interpolate once vertically. So let's say I call this as TI for top interpolation, and I call this as BI for bottom interpolation. Then you do an interpolation through these, and this time the point is, instead of 1.3, it was at 1.7, right? So it will be somewhere here, and then the calculation would be 0.7 multiplied by TI plus 0.3 multiplied by BI. So ultimately, this is what you will get. So what will this look like? 0.7 multiplied by A multiplied by 0.7 plus 0.7 multiplied by 0.3 multiplied by B. So this is 0.49A plus 0.21B plus 0.21C plus 0.12 D. So this will be the final output that comes out of these 4 pixel values when we are using a filter like this. But normally, if we were to use a filter which looks like this, let's say the filter values were 1001, what would be the output if I apply this filter to this image? Can anyone mention? This is the filter, and this is the image. What would be the output? A plus D, because 1 times A plus 0 times B. So this will be like A plus D. But here you look at it, you are having a weird expression because you are not looking at the filter perfectly aligning with your image. But this is also called as sort of like double interpolation, because you are interpolating horizontally and interpolating vertically as well to get the final result. But think about what is happening as a result. As a result of this, even if your dimensions are not perfectly divisible by your final output that you are required to have, you are not omitting any pixels. Pixels are there, it is getting partly considered. Here it was more like pixels are either considered or not considered, but here all pixels are partly considered. So this is the basic idea behind ROI align. And because of this, you can have more information from your region proposal network. So region proposal network is already giving you a lot of good information in the form of this ROI, in region of interest. But you can extract maximum information out of this ROI by using this ROI align technique. Here, on the other hand, you have a region of interest proposed by your region proposal network, but you are losing a bunch of information because you are doing like a quick and dirty approach of just, it's as if you are snapping into one part of the ROI so that this much part is kind of neglected. This is neglected. So it's a quick and dirty approach, but ROI align is a much better approach. So that is the difference that you see over here in this image, where in faster RCNN, it was ROI pooling, which is the quick and dirty approach. But in mask RCNN, you are using ROI align, which is the much better approach. Okay. Now there is one more thing which I want to discuss, which is the region proposal network itself, because our discussion won't be complete without discussing how exactly does the region proposal network itself work. So the region proposal network was a replacement for something, right? What is that? Anyone please answer if you remember. Region proposal network was introduced to replace dash. it was introduced to replace selective search, right? Selective search was the hand engineered algorithm, which was proposing 2000 regions. It was not good because it was not a learnable algorithm. It was proposing mainly based on pixel values, the geometry of the cluster of pixels, the texture of the cluster of pixels. It was good whenever machine learning was dominating computer vision, but the moment deep learning started dominating computer vision, it was not good enough. So that's the main reason why region proposal network was introduced. So the RPN on an average, not RPN, the selective search on an average was taking 2 to 3 seconds per image to propose the regions. So please remember, these proposed regions are first of all not the answer. From the proposed regions, you have to pass it through your rest of the network to get your final answer, which is the bounding rectangles. But to even get to the proposed regions, it was taking 2 to 3 seconds per image. And for this reason, it was very slow. Whichever models use whichever models use selective search was very slow. But this is how region proposal network works internally. Okay. So first you start with a feature map. So basically you convert your image into bunch of features using a CNN backbone. Let me just copy paste our main image so that we have some reference. So maybe I'll paste this image. Okay, so here you see this the CNN backbone, or this one with ResNet or with VGG, whichever model. It converts your input image entirely into a feature map. This feature map, how will it look like? It will look something like this, not exactly this, something like this. It will have multiple channels, but basically it will be like a color distribution or pixel value distribution or number distribution, which very nicely captures the most essential features from these images based on the pre-trained weights of the backbone CNN. Okay, so this is the input that goes into what? That goes into your RPN. So this is your RPN in faster RCNN. This is your RPN in mask RCNN. There is no difference. So I'm just saying, but at the end of the day, it's just a region proposal network. Now, what the RPN has is it passes a 3x3 filter through every positions. So the position can look in the original image, the position may look something like this. So you have a bunch of these points called as anchor points. So your RPN will pass a 3x3 filter through these points one by one. But at every position or every anchor point, you are considering 9 potential bounding boxes. So if you take this as your anchor point, you construct different rectangles or different bounding boxes of varying sizes and varying aspect ratio as potential candidates. So now this overall image, what you see is basically a collection of 9 bounding rectangles drawn on top of each other. Okay. But the central pixel, the anchor point, is this red dot. Okay. Yeah, it's almost like brute force, but much more efficient. Then what the RPN basically predicts for each anchor point is there are 9 rectangles, right? At each anchor point, there are 9 rectangles. Each rectangle is converted into ones or zeros. So if that rectangle is enclosing the object, if the RPN, if the region proposal network thinks that this rectangle encloses a object, it will be denoted as 1. Otherwise, it will be denoted as 0. So that is one thing. Another thing is the bounding box itself, the position of bounding box itself can be refined by shifting the center, by multiplying by changing the width by a little, changing the height by a little, so that even though you are starting from these anchor points, finally the rectangles may end up in slightly offset regions with a different center point and with a different height and different aspect ratio, different width, etc. So in the region proposal network, it's trying to make 2 predictions. One is the class of that particular anchor rectangle. Second is the bounding box, BB, bounding box position. But instead of directly trying to predict the bounding box position, you are trying to modify the center, which is the anchor point of the rectangle, and the height and width of the rectangle. Now, the rectangle has, as I mentioned, it's a positive anchor if the target is 1, meaning IOU is greater than 0.7. What do I mean by IOU here? IOU of that rectangle with respect to what? Can anyone answer? IOU is intersection over union. So the rectangle is positive if IOU is greater than 0.7, IOU with respect to ground truth. What is the ground truth here? In this example, what is the ground truth? The ground truth will be whatever is the bounding box that belongs to that actually encloses the camel. So maybe this yellow one is the ground truth. There are two ground truths, two yellow boxes around the camel. So there are many anchor points. As you can see, there are anchor points here. So there would have been many rectangles here. There are anchor points here. There would have been many rectangles, but finally, only two types of rectangles are considered. Rectangles which are very negative, meaning IOU is very, very bad. There is absolutely no intersection with the ground truth. And those rectangles with very high IOU, those are also finally considered. So what ultimately happens is you will get a bunch of rectangles like from this list. From these 9 rectangles at each anchor points, you look at it, you look at such rectangles at every anchor point. Every rectangle you are converting into prediction. Either the class is 1 or 0. 1 meaning there is an object, 0 means it's a background. And many other rectangles are completely ignored because it has very bad, it's neither properly a background, it's nor properly an object. So that is what this means. Because very bad IOU is good. Because if a rectangle has 0 intersection with the object, everything other than the object is background according to object detection framework in computer vision. So a very small IOU is good for us. A very high IOU is also good for us. Some intermediate IOU is very useless because a rectangle that looks like something like this is very useless. It's partly touching the camel, partly it is in the background. But something like this is very good for us. Something like this is also very good because this rectangle has no intersection with the camel. Then it is as if we are teaching the model to understand what is not a camel, right? So those rectangles are good, but anything in between is useless. So we are ignoring these intermediate IOU rectangles. And then we convert. So at the end of the day, this is what the RPN looks like. And there are learnable features here, right? So there is the feature map. Through that, we have a 3x3 convolution. And there is objectness, which is class 0 or 1. This is learned. Box regression, this one. How much each rectangle should be shifted. This is also learned. And at the end of the day, region proposal network will look something like this. Okay. So this is what the region proposal network is doing to, and the image that you see here, please note, we are not in the camel space. We are not in this image space anymore. We are in the feature space. So ideally, these rectangles are not drawn in this image. It's drawn in our feature space. So please remember that. But then why does it look like I'm drawing it here in this camel space? Because we have transformed the points in the feature space back into this image space just for visualization purpose. But all of these operations are not happening on the original image. It is all happening on our feature map. Why? Because the input that goes into our region proposal network is the feature map. Feature map does not look anything like your input image. It is like a tensor with a bunch of numbers, and you are constructing your anchors and rectangles, everything in that space. Okay. But you can backtrack that space into your input image. And that is what you see here. But at the end of the day, the region proposal network will propose certain regions, which will also look like something like a feature map. It may say that, oh, this and XYZ channels in the feature map may belong to camel. And then you can perform a softmax classifier, bounding box regressor, etc., where you convert back the feature map into your original image so that you can nicely see a bounding box around a camel. So this is overall what happens in the region proposal network. Okay. There is a question. Bounding box refinement helps us learn the pixels that are important for our feature filter. What do you mean by feature filter? Which filter are you talking about? You mean this filter? Yeah, correct. So yeah, exactly. So basically regression, at the end of the day, it has to teach something, right? It will teach the the weights associated with the filters that are used in the regression branch. Okay, so now enough of theory. Let's now go to implementation. I will first share. So this time also we'll be running on Google Colab for the simple reason that we need GPU for fast implementation. So I will do one thing. Let me first show you the data set, how it looks like. It looks like a pedestrian, bunch of people walking. So what I should do is first, let me share the code with all of you. Okay, so please make a duplicate of the this Colab notebook. There is one question. I'm confused with the way masks are generated. The way you explained seems like the masks are generated on the fly. Does that mean mask head uses the ground truth to learn how to generate a mask against the class? The mask head uses a different ground truth. That ground truth that is used by mask head is different from the ground truth that is used by the classifier or the bounding box drawer. The ground truth for the mask is like a binary image. So how do I show that? I have a code here somewhere. Let me just mask RCNN ground truth images. It will basically look like a binary image of the original class. Original shape. So for example, yeah, it will look something like this. The ground truth for the mask will look something like this. So the mask head is trying to make a prediction that somewhat looks like this. And the worse the prediction is compared to this, the higher the loss, that loss will get added to your overall loss of your entire RCNN network. These masks are initially, let's say, matrix of zeros and the shape of image. Yeah, just that these masks are initially matrix of zeros of the shape of image, and then eventually gets the mask of the actual object. Yeah, so how the mask would look like initially when will depend on what are the weights, what input is coming into the mask head and what are the weights in the mask head, right? And eventually, by the end of training, it will be making predictions such that it will look like objects that are part of the training data. So if objects like car and truck are part of the training data, the masks would start to look more and more like that. If, let's say, walking people are part of the training data, the masks will start to look more and more like that. All right. And you will also see at the very end, we will draw something like this. So in mask RCNN, we literally draw a mask. So for example, see this. So here you see like a light color around these people, like a blue color, red color, green color. So those are actually the masks that are separately constructed, and we are just overlapping it on top of the image, right? And so basically that the prediction from the mask head corresponding to that particular person, which was hopefully like a region proposed by the RPN, that mask would have looked like just this outline of this person, and rest of the things will be like black, but we are just overlapping it on top of the image, right? Okay. Yeah, and the person is occluded seems, yeah, kind of, yeah, it seems like it's working somehow very nicely. And also this is like training data, so it's very easy to make it match closer and closer to the ground truth. But anyways, please, let's start running the code. I am reconnecting to my GPU, A100 GPU. So I highly recommend you to just take at least one like $11 subscription for the GPU just for the next few lectures as well. After that, I don't think you will need it. This is just for running it on the go very fast. But at the end of the day, what we'll get is input image would look something like this. I'm not going to go through the entire code because that will take us another 2 hours if we want to implement from scratch. But input image will look something like this. Output from the mask RCNN will have 3 things. What are those 3 things? Can you tell me what are the 3 things? The output from the RCNN, mask RCNN. There are 3 heads, right? Finally, there are 3 parallel heads. One is the class, another is the bounding box, another is the mask. So here you can see all the 3. Class is person, bounding box around each person, and mask, as you can see, around the exact pixels that correspond to that person, right? So all the three are happening here simultaneously. We can actually also implement, like modify the code. Maybe that could be an assignment for all of you. You modify the code such that you are implementing this to frames, continuous frames of a video. So you take MP4 video as the input, you apply mask RCNN to that video, each frames, and then you save the video back, the frames back into an MP4, so that if you have an input video, something like people walking, it should get converted to something like this. So that could be an assignment. But here I'm just considering images. So let's just run this mask RCNN code. And I actually have a code here which is supposed to work for a video. So where is my video? I have uploaded a video to my drive. I will share the video also with you. First, let me run this and show you, and then I can do the rest after that. Okay, let's just look at the head, right? So the main backbone neural network is pre-trained ResNet 50. And the rest of the things are standard. RPN does not have a specific name, but we use the same architecture that is discussed in the paper. And I just want to show you this is kind of reasonably fast. You have already processed 50 frames. But actually, I tried this on my VS Code because it's easier to connect to my webcam camera in VS Code. On Google Colab, it's like a pain. So, but the problem was each frame was taking a long time to process. So I had my hand like this, and I moved my hand like this, but still the frame that was being processed was the one with my hand like this. So it was too slow. So that's the reason why in the lecture, I cannot show any real-time processing using mask RCNN. But that's why I thought I'll show you this MP4 input output. So let me just show you, it'll almost be done in 1 second. Let me just show you the output. So here in this code, basically the annotated output will show up here. And this is like a temporary folder. If you refresh the, it'll be gone. So you just download it from here. And the original video was something that I downloaded from pexels.com. It's like a, stock image, stock footage platform. Okay. Yeah, so this was this is not the original video. This is the annotated video. Can you see the video? Like, can you see this pop up? Yeah. So here I have deliberately eliminated the bounding box. I mean, you can choose to do that. You can choose not to add the person class. It's up to you, right? What you want to annotate. But here I'm just annotating the mask, and you can see that it's not a very, very good mask. It's okay. I mean, it's not as great as it could be. It's imperfect. So if you pause, you can see that the mask is recognizing even some regions which are part of the background. So these are like technically this small region is part of the background. So mask is recognizing that as the person, but it's okay. It's not too bad. And sometimes this person, depending on the person's actual orientation, you can see that there is a bit of flickering. What that means is because each frame is treated separately. So each one is an image. So here, for example, that same person, if the orientation is somewhat like this, in this particular frame, that person is not being recognized. Maybe because there is no visible head or arm or anything, but in another frame, it's a little bit more clear. So maybe that is the reason. But other people who are visibly people with their entire torso and entire face, everything visible, there is no flickering in every single frame. They are being detected as people. So very cool, right? So let me also share this video with you. And yes, collab file. Oh yes, I'll share the collab file here. So this you can already run right now in the class itself. I don't think this will take too much time to execute. You could run using TPU if you don't have a A100 GPU. So just here is the code. What you will have to change is there is a Google Drive folder. Let me just open that. One second. Let me just share the Google Drive folder with you so that it'll be easier for you to get this file. Okay, I got the link. So this is the link to the Google Drive folder. So just do one thing, make a copy for that this folder in your Google Drive. And all you need to do is you import your collab node. I mean, you connect your drive and collab. And here in the input video, just change the path. So all you can do is navigate to drive, go to my drive, and the folder name is RCNN data or something like that. So this will open once you connect your Google Drive. And the name here, you can navigate to that RCNN, this one. Yeah, mask RCNN input videos. So inside that, there are a bunch of videos. So all these videos are the ones which we used in the previous lecture. So here, then click. Oh, actually, you have to click the actual video. The actual video was, I think it was called people.mp4, this one. Just click this, copy path, and then paste it here. So mostly your path will also be similar. Just make sure that this is taken care of. Output video, you can write it back into Google Drive, but I'm just writing it here temporarily. So it will be a temporary file. That's it. That's the only change that you have to make. Otherwise, this code should run perfectly for you. Can anyone let me know in the comment if you were to run either this code or the previous code? Just I'm just curious whether the code is finishing running. And I just want to see cases where this is utterly failing because last week I was trying an experiment on UNet, a decent model, and it was on like a pet dog data set, and it was utterly failing on on some stock footages that I downloaded. Very, very, very bad segmentation. So I just want to know what you guys find, whether you can break this algorithm by, I mean, take a decent video, but see whether you can break this. And one more thing which I will recommend you to try yourself is use the same code. And if you remember, all you need to do for changing this to input video being your live stream, I mean, your camera live stream is this video capture. Yeah, see, instead of this path, what should you put if you want your camera input? This one. 0, right? So if you want the input to be your camera, just put this as 0. So all you need to do is like copy paste the same thing into your VS Code so that your OS is taking care of your camera and everything, and just run the code and just let me know how well it works. And if any of you have a good GPU for yourself, like for in your computer or something, I think it should run good for you. In my case, that is not the case. So for me, the camera input is working really, really slowly. It's very annoying. So that's pretty much it. So I'll share one assignment about RCNN, specifically faster RCNN and mask RCNN with you. One assignment that I thought will be worth doing was quantifying the speed difference for pre-trained models for RCNN, fast RCNN, faster and mask. But then I thought anyway, RCNN and fast RCNN are kind of obsolete. There is no point in spending time on that. So I won't be asking you to do that assignment anymore. It's because it's not too much fun. But I'll be posting an assignment for the pro people in the assignment section for something related to faster RCNN and mask RCNN. So just try that out. So in the next lecture, we'll be starting UNet. The next 2 lectures will be about UNet, and UNet is so important. You will, in any generative AI image generation model, you will almost always end up seeing UNet. It has like an encoder and decoder type of architecture, and it will be so fun because I think if you can truly understand the philosophy of how the UNet works, you are initially downsampling and then you are upsampling, and then some concepts from ResNet will also come into picture of residual connections. So it's like a fascinating concept that mixes a bunch of things that you should know. So UNet you will absolutely enjoy from a theoretical point of view. From implementation point of view also, I'll try to get my segmentation into really good shape by the time of the lecture. Right now it's not very good, but we'll see. And after that, we will move to YOLO. And at the very end, we will move to Roboflow. Roboflow is so interesting because one of the industry projects that we worked on, for that to create annotated data set, we did not have an annotated data anywhere to train our model. And we had to create it using Roboflow. So for an actual industry pipeline, you will learn how to, how to make use of these tools. There is a question, is DSA important for ML? I can't speak with respect to how other companies hire, but I can speak with respect to how we hire at Vizuara. We don't care about anybody's DSA knowledge. I don't know what colleges most of our people come from. Like, I don't personally look at any of that. What I mainly look at is, do you know fundamentals of machine learning, deep learning, linear algebra? What is important for MLDL, not outside things. From a foundation standpoint, and do you have ability to solve some actual problems which we have defined? So that is what we mostly look at. But that being said, I know that many companies also look at DSA knowledge for ML, which in my opinion is like a bit of an overkill. I think there are very, very good ML engineers who are not as good as some software engineers in DSA. So I hope more and more companies will focus more on ML knowledge rather than some lead code problem solving, right? So that's my take on it. But yeah, it's somewhat, I would say it's 30-40% important still in many companies. I think it's a good time for us to wind up today's lecture. So just to recap, we looked at so far OpenCV, started with OpenCV, foundations of OpenCV. We built some interesting applications using OpenCV. We processed images, we processed video. There we used YOLO V8 pre-trained model, but we did not go into details of how exactly YOLO works, right? Then after that, we moved into RCNN. And in RCNN, we covered RCNN, mask RCNN, fast and faster RCNN. It's fascinating concept, but only the latter two ones, faster and mask, only those two are beneficial for you. Next, we'll be moving to one module with 2 lectures into UNet, which is very fascinating and very, very relevant in today's times. And after that, something that is even more relevant, I would say, for real-time processing, which is YOLO. And then finally, Roboflow for entire pipeline. So with that, I think we'll wind up. So I'll meet you again next Monday, same time. And for pro people, if you have any questions and any specific comments, feel free to put it in the Discord. See you soon. Take care until then. Bye. So welcome back to Computer Vision Bootcamp. So what we are going to do today is we will get ourselves introduced to UNet. And UNet is an amazing architecture, which you will also come across in generative AI, especially in image generation applications. It's a broader architecture which originally started its application in biomedical imaging, and later it completely transitioned to being one of the backbones of something like diffusion models. So we will get into UNet. Today we'll discuss in detail about the theory of how exactly does it work. And at the end, as usual, we will implement UNet for a particular data set. And we'll train it and we'll try to perform inference also on UNet. So UNet is meant for semantic segmentation. So I will also initially discuss a little bit about what's the difference between semantic segmentation that we are talking about in this lecture versus instance segmentation that we were looking at previously when we were working on mask RCNN. So with that, let's get into the lecture. So in semantic segmentation, the basic idea is that every single image, every single pixel in an image has a class. So if an image has 224 by 224 pixels, every single pixel is assigned a class. If it is just detection of one object, let's say you have a car in an image, and if it's just about detecting the car, then every single pixel has a probability to be car or a probability to be background. So then it'll be like a binary classification. The output we get at the end of semantic segmentation has a lot of similarities with the mask that we discussed in mask RCNN. So for example, if we have a car as the object that we are looking at, we will be having a mask that looks like mask 1. This is mask 1 and mask 2. So it's like a 2 channels. At the output, you will have 2 channels, where the first channel will be mask 1, second channel will be mask 2. And in this mask 1, you will have the object, everything other than the object in white color. So the object itself will be dark in color, something like this. In mask 2, you will have a mask for the object itself, which means background will not be highlighted, but rather the object will be highlighted. And we will also discuss how exactly are we going to calculate the loss in this case, because in semantic segmentation, the basic idea is that you construct a mask such that this mask has the exact same shape of the object of interest, right? So we will discuss about UNet architecture, but before that, the word semantic simply means that if you are looking at this text of Apple, or if you are actually seeing the picture of an apple or actually looking at an apple, or if you are imagining an apple, at the end of the day, all these things mean the same thing, right? It's just that they are represented in different ways. In one case, it's a text. In other case, it's an image. In the other case, it's some other representation inside your brain. So semantic segmentation means you look at the object from the perspective of its meaning, like this, all these pixels might be belonging to the object of car, and you don't distinguish between car 1, car 2, etc. As long as a pixel is a car, it will be assigned one class, or it will be assigned one color when we are superimposing the mask. So let's kind of bifurcate the segmentation into instance segmentation and semantic segmentation. So this picture very nicely captures it. So just look at instance segmentation, which we were doing in the last lecture. So if this is the input image, you have basically 4 objects here, 3 sheep and 1 dog. But only 2 classes are there, dog and sheep. Ignore the cat and horse that is mentioned in this image. Let's not take that into account. So 2 classes, 4 objects. In instance segmentation, we try to draw bounding boxes around every single instance of the object, and we can define a unique instance ID. And if we are using mask RCNN, we will also be producing masks like this. And here what happens is every single object is determined separately, but they will be belonging to same object. So this will be like sheep 1. So this will be of the sheep class, but its ID will be different. So this is sheep 1, sheep 2, sheep 3. So the 3 different colors that we have showed here is representing that idea that although these 3 objects are of the same class, those are 3 separate instances of that class. And this is an entirely different class. And it's obviously an entirely different instance, the dog one. In semantic segmentation, it's very different. You don't care about different instances. You just care about whether it's in a class A or class B. Now, you might be wondering, where is this useful? So before I show you the use cases, I hope you haven't read it fully, but where do you think the semantic segmentation actually might be useful? Because it seems like, oh, instance segmentation is better because not only it can distinguish the classes, it can also distinguish different instances within the same class. So why do you think semantic segmentation might be useful? Where, in what kind of applications? Feel free to put in the chat. Traffic counting, you mean? So in traffic counting, okay, let's see. You're saying in traffic counting, we don't care about the kind of vehicle itself. People count, traffic count. Okay. So I'll tell you one. So I'm asking about semantic segmentation right now, not instant segmentation. My question is, where exactly is semantic segmentation helpful? I'm not talking about instant segmentation because instance segmentation, which we already did in the previous lecture, looks like a better thing. So why are we discussing about semantic segmentation? So think about a case where you have an MRI image of a brain or some other organ, and you would like to distinguish all the tissues which are cancerous. You don't care about whether it's tissue number 1, tissue number 2, etc. You just want all the tissues that are cancerous in one image, in one color, segmented in one color, all the other normal tissues to be in another color. You don't care about separating those instances. You just care about whether it is cancerous or not. So that is one example where semantic segmentation is useful. Another example is, let's say we have a pipe, and in this pipe there are cracks or defects, or any manufactured products where there are defects, and you don't care about separating out these defects instance by instance. You just want to know overall on X percentage of area how much defect is present. In that case also, semantic segmentation is much more useful. So here I have written some use cases in semantic segmentation. If we have a aerial map or satellite map, as somebody posted in the chat, if we are trying to just survey the land and we only care about segmenting river area versus agricultural area versus, let's say, area where people are living, all these into different color in the map, then semantic segmentation is useful. You don't care about identifying individual houses. You don't care about identifying individual, let's say, farmlands. You just care about mapping the entire farmland into one single class, right? So semantic segmentation has its own uses. Even in agriculture, if you want to simply distinguish crop versus weed, and this is very relevant for many companies, including the one which I showed you, the Blue River company. They were spraying when weed was detected. They were not spraying when crop was detected. So there also, if it's an image-based segmentation, you don't care about the individual weeds being ID'd out separately. You just want to know how much weed is there. So there are many, many different use cases for both. It's not that one is superior over other. It's just that if the use cases are entirely different, right? So that's what I have written here, like two examples. One is from about the tumor detection, where it's not critical to separate the tumor into different IDs, but you want it overall, or in aerial or satellite imaging. Now, the whole purpose of UNet is to perform semantic segmentation. By default, it does not perform instance segmentation. So it is in that sense very different from what mask RCNN does. And in my opinion, it's just my personal opinion, I think the UNet architecture is much more elegant, and you will see soon why it is so. It's much more elegant, it's much more simple, and it has the exact same architecture, which you will also see in various Gen AI models. So what I'm showing you right now in this picture is the UNet architecture, and we are going to dive deep into this, okay? So I'll be asking you a few questions so that I can be sure that you know in and out. So just keep a pen and paper or whatever which can help you perform some calculations ready. So firstly, UNet is called so because this shape, as you can see, it's like a U. Now, this can be split into two parts. If I draw a line like this, everything here is called an encoder. Everything here is called a decoder. And this part, this bottommost part, is called the bottleneck. Okay, I'm initially just showing you different parts. We can go into the details of that soon. So encoder, decoder, bottleneck, and one more, are these skip connections. So see these connections going from this layer of the encoder to this layer of decoder, this level of encoder to this level of decoder, like that. So just notice these 4 things. I have just written it somewhere here. Just notice encoder, decoder, bottleneck, and skip connections. Now this paper is extremely famous. The original paper currently has 118,000 citations. The papers that we discussed until now, until the previous lecture, it had around 40,000, 50,000 citations. So this is super, super popular. And I believe half of its popularity was because of its biomedical applications and applications purely in image segmentation domain. Remaining half was maybe because of the application in generative AI. I don't know the split in when these citations happened, but it's very, very famous paper. It's truly like a seminal work. Now let's get into encoder-decoder architecture. So you might also notice the same encoder-decoder architecture in transformers, like transformer, encoder, decoder. So if you go to this one, you see this is like a encoder-decoder architecture of transformer, where left-hand side is one encoder, right-hand side is decoder. So similarly, we have something exactly like that here. But let's discuss what is happening conceptually in this architecture. I'm just going to create a copy of this for a clean board. So let's start with the input. Okay, what is our input into a UNet or into any image segmentation model? What is the input? Yes, Ajiketa, I'll be discussing skip connection. Everything in this architecture I'll be discussing, but let's start sequentially. We will be inputting something. What exactly is the input? Input is an image, right? In this case, just look at the dimensions of the image. This is just the default numbers. Of course, it can be different, but by default, the original 2015 UNet architecture had these numbers, 572 by 572. And there is a 1 here. Can anyone explain what is this? What are these numbers? What is this? What is this? What is this? What are these 3 numbers? 572, 572, 1. I need more specific answer. So 572, I understand that it's dimensions, of course, but what dimensions? What exactly is it? 572 is the number of pixels along the width. The other 572 is the number of pixels along the height. And 1 is what? What is 1? 1 is the number of channels. So this is not a color image. This is a black and white, like a grayscale image. So number of channels means for a normal color image, you will have red, green, and blue, right? RGB channels. Here it's only having 1 channel, which means it's like a normal grayscale image. Now just notice this blue arrow, which is shown in the paper architecture. This blue arrow denotes some convolution operation happening with a 3x3 filter. Okay. And just notice what is happening here to the dimension of the spatial dimension of the image, and what is happening to the number of channels of the image. What is happening to the spatial dimension? Is it increasing in size or decreasing in size spatially? And what's happening to the number of channels? Is it increasing or decreasing? So spatial dimension is decreasing, correct? It's going from 572 to 570, and number of channels are increasing from 1 to 64, right? Now, we will come to the number of channels increase in a moment. But before that, can anyone think about why exactly did the spatial dimension grow from 572 to 570? Why did it reduce by 2? Why not by 3? Why not by 4? Or why is it decreasing at all? What's happening? I'll just show you the definition of this blue arrow. This blue arrow is defined here at the bottom. Basically, what this blue arrow indicates is 3x3 convolution and ReLU activation. Okay. So the spatial dimension is decreasing because of 3x3 convolution. And this is exactly how. Let's say you have an image of dimension something like 10 by 10. So this is 10 pixels. This is 10 pixels. Okay, something like this. and you have a filter. Filter size is 3 by 3 convolution filter. Now, when you apply this filter on this image without padding, and if the stride is equal to 2, what does all of these things mean? Stride means the number of steps you are taking in each time. This filter jumps 1 pixel at a time. So initially the filter will be here, then it will jump here, then it will jump here, like that. Okay. So that is what we mean by stride. And padding equal to 0 means you are not adding extra pixels to the image. So when we perform a convolution operation on this input image using this filter, what will be the resultant dimension and why? Will the resultant dimension be 10 by 10 or will it be something else? The input is 10 by 10, filter is 3 by 3, output is what? Output will be 8 by 8. And the reason is this filter cannot occupy, it can only occupy 8 positions horizontally. This is the first position, right? This is the second position, third position. Like that, it has only 8 positions to occupy because the filter has a width. If you want to make the filter occupy 10 positions such that you can have 10 along the width in the output and 10 along the height, then you have to add extra layer of pixels. This is called padding. So there is 1 extra layer of pixel at the left, 1 extra layer at the top, 1 extra layer at the right, so that horizontally you have two additional pixel layers. So this 8 by 8 will be compensated by an additional 2. So it will become 10 by 10. But here in the original UNet paper architecture, they did not introduce padding for whatever reason. And because of that, and because they are using a 3 by 3 filter and stride equal to 1, you are getting an output of 570 by 570. The same thing repeats once more, then 570 will become 568. Okay, so that is happening with respect to convolution. However, you notice the number of channels have increased. It means if you have n number of channels at the output, it means you have n number of filters. So here you have 64 channels, which means you have 64 filters. So what that means is, let me just delete all of these. You don't have just one filter like this. You have 64 filters like this green filter. And then this entire image, this first filter will process the entire image. Then you will get the output. The output will be what? 570 by 570. That will be the output in the first channel. Then the second filter. So second filter will also have the dimension of 3 by 3, but you can imagine it to be arranged in like a stack of vertical, like, its dimensions could be something like 3 by 3 by 64. So your input dimension is 572, right? What was it? Yeah, 572 by 572 by 1. So this is the input dimension. Your filter dimension is 3 by 3 by 64. And the output dimension is 570 by 570 by 64. So basically what happened is the spatial dimension decreased. Spatially, this thing shrank a little bit, but the number of filters was 64, which means there are more features each of this filter could learn. That is what is happening. And you repeat this 2 times, but this time you will keep the channel number 64. You are not increasing the channels anymore. And then you have, by the end of this first level, so this we can call as level 1 of encoder. Level 1, by the end of level 1, you have a dimension of 568 by 568 by 64. Now you go to level 2 of the encoder. But by the time you bring your output from the level 1 to this level 2, what has happened is you have done something called as max pooling. So here, this red arrow indicates 2 by 2 max pooling. What does that mean? You will have a filter like this, 2 by 2. And if the pixel value corresponding to, this filter will be overlapping. If you imagine the filter to be overlapping on top of an image, the maximum value of the pixel only is picked, right? So that is called max pooling. You are pooling from a value of 4 pixels, the maximum value. And when you do this max pooling, obviously you can imagine that the size along the width gets divided by half. The size along the height also gets divided by half. So what happens here is 568 will get divided by 2. So 568 divided by 2 will be 284. So this 284 square is nothing but 284 by 284. But here the number of channels is not changing. It is 64 only. So number of channels remain unchanged, but you are performing a max pooling. Then you do again the same convolution operation. So from 284, you go to 282, the 3x3 convolution. So this is 3x3 convolution. Then again, you do the same thing, 280. But this time you have 128 filters at the output. So input will be something like 284 by 284 by 64. This is the input. Which input? This guy. This guy will be like that. Input. The filter will be can you tell me the filter dimension in this case? Can anyone tell me the filter dimension? 3x3 by what? 3x3 by 128, but are we missing something? 128 is obvious because the output has 128 channels, which means there are 128 pixels. But there are 128 channels, which means there are 128 filters. Sure, 128 filters are there, but what is the dimension of each filter? Here, the dimension of each filter was 3x3. In this case, in the previous case, it was 3x3. Like that, there were 64 filters. In this case, the dimension of the filter is what? We all agree that there are 128 filters. The dimension of each filter has to be 64 by 3x3 because each filter is getting, we can write this number 64 wherever we want, but essentially every input has to pass through all 128 filters to get 128 outputs. That much is sure. So of course we need 128 filters. But if you look at the number of channels at the input, there are 64 channels. So the filter itself, at each point in the filter, you have 64 by 3x3. So spatially, it will look like this 3x3 each filter. But then this depth dimension will be 64. And then like that, there will be 128 filters. So first, this entire input 284 by 284 by 64 will be processed by this guy to get the output for the first channel. Then again, the same input will be passed through the second filter, which has this same dimension 3x3 by 64 to get the second output. Like that, you have to do go through 128 filters to get the 128 channel output. And same thing repeats here. So here the number of channels are not changing, but the spatial dimension is changing. So this is level 2. Now it's simple because now it's just a repetition of what we just discussed. Now in level 3, when you go from level 2 to level 3, 280 will become 140. 140 will become 138 and 136. Here it would be 128, but then you have 256 channel output. So then that is what's happening here. Here it continues. And then again, from level 3, you go to level 4 of encoder. 136 will become 68. 68 will become 66. It will become 64. Here it will be 256, which becomes 512, 512. Okay. Then, so now all the 4 levels of encoder are done. Now let's come back to before going to decoder, let's come to this bottleneck. Bottleneck is the part where encoder transforms into decoder. So here, again, we are performing the same max pooling operation. So 64 will become 32. Okay. The filter size this time will be still 512. But here, what is happening is we are getting 1024 channel output. But the dimension spatially has now become 30 by 30. So just look at what has happened to our image. Our input image was a giant image, something like this, 572. This was our input image, 572 by 572. Then this image representation, by the time it reaches this bottleneck, is just 28 by 28. Maybe I can draw it like this. It's only this much spatially. So spatially, it has shrunk so much, but it doesn't mean that we are losing a lot of information because there are 1024 such channels. So something like this. So 1024 channels like this. So initially, the input image, which were just represented by these many number of pixels in one channel, now became a representation like this. And so spatially, if you look at this representation, it's much more compressed. It's encoded. Coding means you are representing something which takes longer number of characters to usually represent in shorter format. So here encoder does something very similar. And the beauty of encoder is that by the time you do the training, you train all these layers, what the encoder learns is the very essential patterns that you have to know from the input image. Now let's come to decoder. So encoder, basically what it does, if you see what's happening is input image is a giant image with one channel. At every layer, the spatial dimension of image is decreasing, but the number of channels are increasing. By the time you reach the bottleneck, you will have like a 30 by 30 or even 28 by 28 spatial dimension, but along different channels, you'll have 1024 channels. And then here, what we are doing is we have something called up convolution. This is the up convolution. So let's see what this up convolution is doing. Just think about this. So can you tell me spatially now what is happening to the image? Spatially, is the image becoming bigger or smaller, or what's happening? Spatially, the image is becoming bigger, right? Because 28 by 28 is becoming 56 by 56. And also think about, why are we doing this? What is the output that we want? Let's just keep that in our mind. The output that we want is dash. What is that? Input is an image. Output is, we are performing UNet. We are performing segmentation. So we want the mask, right? Which kind of represents the boundaries of the object. So we are trying to construct a mask which looks like the image only, but it'll be binary wherever there is an object. So mask is this, as we discussed. Let me zoom out and go back. So this is the mask. Something like this is what we want, right? So ideally, the mask should be pretty much the same size as the image. So we have shrunk the image so much spatially. Now we have to, grow it back. So let's go back to the diagram. So here, what is happening is the image, which was 1024, it is getting, 28 by 28, it's getting upscaled. But how does upscaling work? Because downscaling, you can imagine how it is happening. This 2 pixel downscaling is happening because of 3 by 3 convolution. This divided by 2 downscaling is happening because of max pooling. But how do you do this upscaling? What is this? How does 52 become 104, the dimension? Or how does 28 become 54? What might be the operation that results in higher number of pixels? It's called bilinear. It's not padding, it's bilinear interpolation. So here is an example of how it looks like. So let's say our input is 1, 2, 3, 4. Okay, this is our input. I would say spatial representation, 2 by 2. And say we want a 3 by 3 representation now. We want to upscale this 3 by 3. The simplest thing which we can do is put 1, 2, 3, 4 here. And then you have some empty regions here, right? There are these empty ones. And what you simply do is you perform interpolation. So this will become 1.5. This will become 3.5. This will become 2. This will become 3. And here, this will become 2.5, right? So this is called bilinear interpolation because you are interpolating along the horizontal direction as well as the vertical direction. But you might be wondering, why is this useful? Because these new numbers that we have in these pixels are not something that is giving us any extra information, because these numbers are at the end of the day derived from the existing numbers. That is true. But if you look at what is happening after that, there is another layer of convolution. There is another layer of convolution. So these convolutions ensure that meaning can be extracted out of this bigger dimensional image. And this is also helping the spatially shrunk image to grow back in size so that ultimately it can be almost as close to the original image size as possible. But there is one more thing which is fascinating here, and this is, without this, it would not have been possible to have, UNet construct the feature representation so well. There is something called skip connection. So see this. So what is happening here is you are concatenating the values from this layer, from this level 4 of encoder into the level 4 of decoder. What do I mean by that? So in the encoder, for example, we have, or in the decoder, here we have 56 by 56 by, I guess it is 1024 only. So the number of channels is 1024, right? To this, and to this, we are concatenating some numbers, and concatenating some numbers means we are adding the extra channels to increase the number of channels. So here, if you look at the level 4 of encoder, it's not 56 by 56. It's actually 64 by 64, right? It's 64 square. So it is something like 64 by 64 by 512. The number of channels being different does not matter because you are anyway stacking it up along the Z direction. So number of channels need not match, but the spatial dimension should match. Otherwise, how will you concatenate? So that is why here an extra operation is done, which is cropping. So here in this, you can see copy and crop. So here what this dotted blue line indicates, you are cropping the spatial dimension. So here spatial dimension is 136 in the level 3 of encoder, but in level 4 of decoder, level 3 of decoder, it's 104. So 136 needs to be cropped out so that this cropped region is 104 by 104 by 256. So 256 is the number of channels, and that is concatenated on top of the original input that you have at this level of decoder. Now, you could ask, why are we concatenating? Why not just add? Because you could simply add the numbers, right, by somehow matching the number of channels. So in ResNet, that is what they actually do. So the ResNet architecture, which also introduced the skip connection, let me just show you. This was also another revolution in deep learning. So here they have something called as skip connection. These are the skip connections, where effectively what they are doing is, if the neural network depth is so much, the amount of influence the initial layers have on the output is so minimal. In normal neural networks, in normal extremely deep neural networks, the initial shallow layers, which are here, have very minimal influence over the output, which means when you are performing backpropagation, these initial layers will barely get modified. So it's so painful to modify the initial layers. And this was a problem famously known as vanishing gradient problem. The gradient, the effect of the gradient by the time you backpropagate and reach the initial layer is almost negligible. And because of this, deep neural networks found it extremely hard to train on big data sets. So what ResNet guys did was they introduced these skip connections where the input value is directly passed here. The value here is directly passed here. Value here is directly passed here. And these layers will only learn the difference that it's supposed to learn. And because of this, now when we do backpropagation, or now when we look at the influence of the initial layers at the output, there is a huge influence that even the initial layers have at the output, because if something changes here slightly, it is directly passed through these skip connections to the output layer. And you will also see this in the transformer architecture called residues. So if you look at this diagram, you see this guy is like a skip connection. This guy is like a skip connection. This one is like a skip connection. This is also like a skip connection. So it's called residuals. So you can pass it from previous layer to the next layer so that when we are training the network, it's much better. The vanishing gradient issue is not there. And more importantly, here there is one more interesting way to think about it, which is the information here, right? Information at level 1 of the encoder is so rich. Why? Because it's very close to the input. the level 1 is not too far from the input. It is just 2 convolution layers away from the original input image. So this is so information rich. Now, if we are completely ignoring this, if let's say these skip connections were not there, then by the time this multiple convolutions happen, by the time you reach here and by the time you go up the decoder and reach here, yes, you learn a very abstract representation of your image. You abstracted it so much that spatially you can represent it in just 30 by 30 or 28 by 28 pixels. And by the time you go through the decoder, you have grown it back. But the problem is all the information that is there in this initial part of the architecture is not taken into consideration. Now, if this was RESTnet, you could have drawn it also like this. So this convolution could be something like this. Next convolution could be something like this, something like this. So I could simply draw blocks, and this is the next set of blocks. And then in between these two, there could be the bottleneck part, right? And then here, if I were to draw this like a RESTnet, I have a skip connection going from here to here all the way till here. I have a skip connection going from here to here. I think my number of blocks are wrong or something. I think it's correct. Yeah. So this is essentially the architecture. Basically, in RESTnet, what they were doing was skip connection. Instead of you concatenating the values, you were adding the values. Here you are concatenating the values. So RESTnet, there is a nice image which, yeah, this one. So in RESTnet, the skip connection value input is X. Skip connection value is X. What this network learns is f of X, but to f of X, you are adding X. So it's f of X plus X. In here, we are not adding, we are simply concatenating. So that's the main difference. But then I think the people who came up with the UNet architecture, they might have drawn, I'm not sure, but they might have drawn a diagram like this, similar to RESTnet. Then they thought, okay, I could actually draw it like in the shape of a U. It might look better, and I can explain it as an encoder decoder block. But otherwise, we could also draw something like this. I can just annotate a box like this, say that, oh, this is the encoder block, this is the bottleneck, and this is the decoder block, and then connections go like this. So same UNet architecture, we could draw like this. Maybe it looks more ugly or whatever, but for whatever reason, they choose to represent it in this format. Both are the same. So are interpolation and concatenation adding the same information? What is the difference? No, concatenation is bringing the information from its true source. What is the true source of information? The input image. So level 1 has very high level of information available. Level 2 is one more level of abstraction. So abstractions are also important, right? Because otherwise it will be like this network is brute forcing its way to learn what features are there in the image. So you need abstractions, but you also need the actual true representation of the image, which as you are closer and closer to original levels, you will have it. So interpolation is different. In the interpolation which I showed, I just showed you how you go from a dimension of 52 by 52 to 104 by 104. That's it. But this 104 dimension is untouched by concatenation. You are not concatenating to go from 52 to 104. Concatenation happens along the channel dimension. Which is the channel dimension? This guy. This is the channel dimension. So that is why you see that this is the input from the, concatenation input from the encoder part. This is the original before concatenation part in the decoder part. So you are just adding it along the Z dimension. So you can imagine it like this. So X and Y dimension are untouched. X and Y dimension only change either by 3 by 3 convolution or by max pooling, or by this up convolution denoted by the green arrows. So these 3 arrows, this blue arrow operations, green arrow operations, and this guy, this max pooling, and even this last layer has a 1 by 1 convolution. These arrows result in change of dimension primarily along X dimension. Of course, some of them also change the channel number. So here you can see that 512 is becoming 256. But the biggest changes in X and Y dimensions, which is the spatial dimension, is brought by these convolution operations. But concatenation only touches the Z dimension, which is the channel dimension. Okay. And which means the number of channels will be doubling. So here 256 is coming here. From the encoder, this 256 channel dimension is coming here. I know that I have drawn like a very cluttered diagram here, but I hope sequentially when I'm going, it's easier to understand. Now see what's happening. This 104 again will become 102. It will become 100. Why? Because 3 by 3 convolution, it's reducing the channel size by 5. And here it is 256 channel output. Here also it is 256 channels. And by the time you go here, this 100 will become 200. You are doing the upscaling. Here is where the interpolation. So interpolation does this 100 to 200 transformation. Concatenation only affects the channel size. I have one doubt which I need to clarify for myself is whether this guy is becoming 255, whether this 256 is becoming 128 here, or whether this 256 is staying as 256 itself. And then when you concatenate this guy, another 128 is added or not. That one I'm not 100% sure. I have to check it. Basically, my thing is this now 128 along the channel dimension or not? So that I can clarify and let you guys know. But other than that, effectively what's happening is concatenation happens along the channel dimension. Is the concatenation making the feature more prominent? A better way to say would be when you concatenate, now in along the channel dimension, which is the Z direction, you have two types of features. The first half of it would be abstract representations coming from your bottleneck area. So by the time your image got transformed and became, feature representation into this abstract 1020, this 30 by 30 by 1024 format, it's very, very abstract. It's not at all related to the original input image, but it has a lot of generalizable knowledge. Now, when you add something on top of it, that addition is coming from closer to your knowledge source, which is the initial layers of the encoder. So effectively, concatenation ensures that you have both the abstractions of the image as well as the original, much more well-defined features in the image, which was there in the input regions. So that is essentially what concatenation is doing. Here, for example, in ResNet, this addition is making sure that whatever features are already available or whatever knowledge is already available at the input, it's directly being made available at the output, so that then the network or this block needs to only learn the residual or the difference between output and input. So there is another question. Why do UNet skip connections add cropped instead of adding downsampled? Instead of adding downsampled input via skips, does the skip transfers all channels? That's a great question. Yes, skip connection transfers all the channels, but cropping is because, as I mentioned earlier, just look at the XY dimension here. So here the XY dimension is 104 by 104. Here the XY dimension is 136 by 136. So you can't directly overlay like a 136 by 136 image and 104 by 104 image on top of each other. So that is why you are cropping this such that this is also 104 by 104. And that is happening at all layers. You can see that this dotted blue line is basically making the crop operation. And then finally, by the time you reach, yes. So cropping operation, let me explain once again. You guys all agree that when I'm concatenating, my XY dimension should match, right? The Z dimension can be different because I am concatenating along the Z dimension, but XY dimension should match, right? There is no doubt about it. Now look at the XY dimension here. XY dimension in my level, let's take this one, level 2 of encoder. XY dimension is 280 by 280. Z is 128. So let's forget about Z because anyway we are concatenating along Z, but XY is 280. But here, by the time you went to the bottleneck and then you came back, this guy did not grow back to 280 by 280. Our goal is to grow back the size of the mask to the original input image size, but because of the losses happening during 3 by 3 convolution in the absence of padding, the size here only became 200 by 200. So now how will you concatenate 280 by 280 on top of 200 by 200? You have to crop the 280 to become 200. So that is the reason why here cropping is done before, concatenating it through the skip connection. So I hope that makes it clear, right? Now, just look at the last thing. Finally, so just count the number of convolution operations. So 3 by 3, 3 by 3. So there are 2 convolutions happening here. There are 2 happening here, 2 happening here, 2 here, 2 here, 2 here, 2 here. So basically, you can easily mathematically calculate the amount of pixels that you are losing meaning because of absence of padding. So it is very easy to calculate that the final output at the end of all of this will not match the initial input. Initial input was 572 by 572, right? So this was the initial input. Then you shrunk this all the way till something like 28 by 28, but with 1000 channels, 1024 channels. Now you have converted it back. So the original input had 572 by 572 by 1. It was a grayscale image. But here you have 388 by 388 by 2. What is this 2? The final output has two channels. What is this 2 channels? What are these? Cropping happens from the center of the image. Yes. So basically boundary pixels will be eliminated. So what is this 2 channels? So 2 channels are nothing but, initially, if you remember, I had mentioned about 2 masks. One mask corresponding to background, another mask corresponding to image. So the 2 is like, so it's almost like a, I would say, if yes has a probability of 0.9, no has a probability of 0.1, right? So if we have an output like this, 0.9 and 0.1, we pass this through sigmoid. We pass this through softmax to convert this into a probability distribution. Or if this is like 3.9 and this is like 2.1, this final set of 2 numbers we can convert into probability distribution using softmax. But at the end of the day, we are just making prediction of one class. Here, basically, we are making prediction about the background and prediction about the object. And here is our, where is my diagram? Yeah. Here is our final dimension, which is 388 by 388 by 2. So these 2 channels, one corresponding to the background, another corresponds to the object. So this is, in a nutshell, how UNet architecture works. So 4 things to remember: encoder encodes the original information in the image into a much more abstract way. And the abstraction is reaching at its maximum at the bottleneck region, where the spatial dimension is so small, but loss of information is prevented because you have so many different channels, and each channel will learn one particular type of feature in the input image. But then decoder tries to push it back to the original dimension, although it does not reach the exact original dimension. So finally, you can convert this into, there are other operations happening. This is just the core part of UNet. There are other operations happening in the UNet to make sure that 388 by 380 it's matching the exact image, because otherwise when you put the mask on top of the image, it will not match if both of them are of different dimensions. So the overall dimension should be the same. So it's easy to rescale this into actual image dimension. But basically, this is how the UNet architecture works. Now, this has many different applications in diffusion model, which we will briefly discuss in today's lecture. There was one more thing which I wanted to talk about, which is, oh yes, the loss. So let's think about the loss function. Okay, so my input is an image. So I have an image like this. And let's say I want to detect circles in my image. So I have a circle in my image. So image is, or let's say I have an image of an apple, something like this. So this is my input image. Okay. Now I will have 2 ground truths. One is the fact that inside this image, the object that is available is apple. So the class, name of the class will be one ground truth. The other ground truth is what? What is the second ground truth? Second ground truth is the mask itself. So the mask would be something like this. It will look like the exact shape of this apple, something like this. Okay. So a mask like this will be the, ignore the color, like just remember this background, that background will have one color and object will have another color. Yeah, so ignore the color. I'm just coloring it because this is easy for me. But there are 2 ground truths. One ground truth is the class itself. Another ground truth is the the fact that this is the this is our mask. Now just tell me, when I make a prediction, right? So I'll have a prediction of these 2 channels One channel will correspond to background, another channel will correspond to object, and it will basically be a mask. So now how will I construct a loss function? What should be my loss function? When do you say that the loss is very high in this case? Let's think about it logically once. Okay, let's say my image was something like this. The actual object is very small. Let's say the actual object is this, the object that we are supposed to predict. Everything else is the background. Okay. Now let's say my prediction is such that the mask, the prediction is that, so object is black, this is the object, everything in the white is the background. So this is the ground truth GT, and this is the prediction. Now we said that every single pixel now has a prediction. Every single pixel is either background or object. In this case, if there are, let's say 30 by 30 pixels, just for ease of calculation, 30 by 30 pixels. This is 30 by 30 pixels. And let's say this object consists of 100 pixels, okay, or maybe 50 pixels. Now let's say my loss metric is something like, I will look at every single pixel and I will create a metric based on was this pixel accurately classified or inaccurately classified. Let's take a step back. I have a ground truth where the object is just spanning 50 pixels total. The actual image is 30 by 30, which is 900 pixels. And the prediction was that every single pixel was marked as background. So binary cross entropy loss is what Moni is saying. So let's say we take binary cross entropy loss. Okay. Effectively, what we are saying, how many pixels for how many pixels we'll have made a mistake? Kind of out of 900 pixels, for 850 pixels, we did not make a mistake, although the prediction was really bad, right? Although the prediction was like saying this is entirely a background, technically the mistake was made only for 850, only for 50 pixels, because wherever the pixels were actually an object, only for that area the mistake was made. So if we were to make a measure of the loss based on the just comparing the pixel values, then in the cases where the object is very small, we may end up predicting that, oh, the model is very good. But in fact, the model is very bad because the model did not even by a single pixel, the model did not recognize the object. So while the model being very bad, just because the object was small, it is kind of, we are kind of thinking that it's a good model. So which is why we need one more metric based on IOU score. So basically, let me show you that in the code. So there is some area. So just let's do one thing. Let's try to derive it. So if you were to also penalize the model for not, let's say, not at all recognizing these pixels, what metric would you think about? You would think about the number of pixels that were predicted as the object. So let's say this mask was saying that the object is here, right? And let's say this was pixel number of pixels here was 50. Then for how many pixels did the mistake happen in this case? So this is the ground truth. This is the prediction. Okay. Now for how many pixels out of 900 there is a mistake? 100 pixels, because these 50 pixels were supposed to be black, but here it has predicted it to be white. These 50 over here, this imaginary pixels here were supposed to be black, supposed to be white, but here it has predicted as black. So 100 pixels out of 900 are wrong, but 800 are correct. 800 out of 900 are correct. So we might feel like, oh, this is a good model, but think about this. So now let us look at just the object pixels. We have 50 pixels ground truth object GTO. I'm just making up some so that I don't have to write it. Ground truth object pixels are 50. Predicted object pixels are 50. Now, how many of them are true positives? Among the 50 predicted, how many of them are true positive predictions? 0 because none of them are actually objects, right? So the true positives are equal to 0. How many are false positives? False positives are 50, right? All of these are false positives. So we can construct a matrix, construct a parameter based on totally how many pixels were predicted as positive, right? Totally 100 unique pixels were predicted as positive, out of which only 50 are correct. I mean, only 50 were actually the ground truth. Remaining 50 are completely wrong. So we can construct a matrix based on this, which I will show you in the code. And what we do is the total score for loss is equal to the loss due to pixel to pixel values. I don't know what we should call that, but basically loss due to pixel values and loss due to object, I would say alignment. Of course, there are better names for this, but I'm just coming up with random names, then divided by 2. So basically the loss should be loss due to pixel level predictions being wrong, and loss due to object level prediction being wrong. You combine those two and divide by 2. So the average, the total loss is the average of these two. And with this, we can ensure that pixel level, the predictions will become better, because otherwise this will contribute to a significant loss. And at object level also, the prediction will be high, because prediction will be good, because otherwise this object loss due to object in alignment or misalignment will also be very high. So this ensures that the UNet model overall can make really good predictions at the pixel level as well as at the object level. Now, let's do one more thing before we just run the code, which is where exactly does UNet come into picture in Gen AI? I won't be spending too much time on this, but I'll give you the gist of it. So basically, the concepts like diffusion model, where you can convert, you can generate an image, it heavily relies on the similar ideas of UNet. So here in the stable diffusion model, you can see that this part, this is a denoising UNet. And here actually they have written the structure of the UNet in a linear way, where this is the bottleneck, this part is the encoder, this part is the decoder, but it might also could be written in like a U shape. But effectively, this is the, I would say, one of the biggest aspects of stable diffusion. We will not go into the details of it today. Now, what we will do is, let us go and train a model. We won't be doing it from scratch, because this actually, unlike the mask RCNN or any of the RCNN models, implementing UNet is not that hard if you think about it, because we just need to add sequentially some layers. We just need to ensure there is forward propagation function, backward propagation. And these are like standard operations. Like there is nothing fancy here. It's just convolution in between ReLU, just defining proper dimensions of the channels, defining concatenation. So this architecture is not, I would say, it's not as crazy as mask RCNN, but in my opinion, this is much more elegant. Now, let me share this code with all of you so that all of us can run this almost at the same time. Okay. Yeah, so there is a question where are pixels and object alignment correlated? So not necessarily, right, Ajiket? So see, if we are just looking at how many pixels were aligned correctly, then we saw that 800 out of 900 were correct. Not aligned, I mean predicted, because a pixel is either a background or it's an object. So 800 out of 900 pixels were predicted correctly. So if we were to just look at how many pixels were predicted correctly? 80 out of 90. I mean, 8 out of 9 pixels were predicted correctly. So we might be tempted to say that, oh, this sounds like a good model, but in fact, it's like the worst model. Why? Because not even a single pixel that was predicted was the object. I mean, there were 50. I mean, the second example, we took 50 pixels that we predicted was the object pixel, but all of those 50 pixels were wrong. Because our interest is primarily, yes, of course, we are interested in classifying all pixels, including background, but we also care about identifying the object correctly, not just background correctly. Because the correlation was very good if we were only caring about the background, but if we cared about object, which is the case in most applications, it was doing a very bad job. So the reason why object alignment is needed is because you only care about true object pixels and predicted object pixels and see how much they are matching. You ignore all the background pixels and see how much of the true predicted pixels are matching with, how much of the true object pixels are matching the predicted object pixels. If that matching is really, really good, you will have a score of 1, which means the loss corresponding to that could be 0. So that is the difference between looking at the overall pixels and just looking at the object pixels. Now let's do one thing. Just take this image. Sorry, take this Google Colab. I'll show you the image dataset. It's called Oxford Triple IT dataset. So they have a website. I think this is also from the same VGG group who proposed the VGG 16 architecture. Yeah, so this I can see a VGG here. I don't know if this is the same VGG as that of the VGG 16 architecture, but they were also from Oxford. So I think this might be the same people. But basically, this data set has a bunch of pet images. It has both segment, the mask as well as the object annotation in the form of bounding rectangle. And I don't know how many categories are there. They have 37 category pets and 200 images in each class. So 37 multiplied by 200, 7,400 total images. So you could download it from here, but in the code itself, we could extract it automatically. So yeah, so these are the statistics, almost 200 in each category. And some of them are dog breeds. These are dog breeds. These are cat breeds. So they have only cat and dog. And the cats, half of the images are cats. Not half, I would say 1/3 are cats, 2/3 are dog, and total is around 7,300. So this is the pet data set. It's like a very good toy data set for working on our UNet model. So initially, we'll be importing the required libraries, specifically PyTorch. This is for augmenting images, Albumentation. Sometimes this might throw an error. Just check it out. If it's saying it does not exist, you will have to do pip install, like pip install whatever is missing, right? So just check that. But most of you will not find an issue, but sometimes some of these packages might not be there by default in your system. Then nothing here needs to change because the data we are fetching not from our Google Drive. It's already it's available to be fetched from this data set, torchvision.datasets. And I'll just show you the main part. So here the operations that are happening are we create the data set in training and validation. We define some dataset transformations like flipping, random rotation and cropping, etc. Those are standard image pre-processing techniques used in any deep learning pipeline. And it also ensures that if your dataset had some bias with respect to orientation, those things will be taken care of. So it doesn't matter in what orientation your validation dataset is, it will still work. Then we just have a class for constructing the data set and getting the masks. So this part should not take you any time to run. These parts are standard. So data loader is a way in which you can construct the data set in batches for training and validation. So I have one question here. Let's say you have an image, something, let's say your training data set has 8,000 images, okay? And every image is an RGB image. So usually we know that images are represented by image width or image height, image width times number of channels, right? This is how we usually represent. But there is one more additional fourth dimension here, usually in deep learning. What is this fourth dimension? These 3 dimensions you are familiar with. This you already know, but one more is there. What is that? This is very, very common when we are dealing with TensorFlow datasets for training. We will not process images one by one. We process image in batches so that training happens faster, parallelly in batches. So here, if our batch size is 8, this number will be 8. And if image size is 224, this will be 8 by 224 by 224 by, let's say, number of channels 3 RGB, then this will be your each individual input data. Now, just look at where the batch size is mentioned. So here the batch size is mentioned as 8. It could be 8 or 16 or whatever, does not matter. Okay. And in fact, batch size is one of the hyperparameters that you play with. So number of data taken in one round. Correct. So number of data, not number of data, each input data will look like something, a tensor of 4 dimension. Like that, how many batches will be there in my training data? How many batches in this case? 1000 batches, because there are 8000 images. One batch is 8 image. So like this, there will be 1000 tensors. 1000 tensors will be there. And how will this tensor look like? So let's say my image is like this. I have a 2x2 image, okay, for simplicity. And the pixel values are 1, 2, 3, 4. Now this is my red channel. If I have green and blue channels, I will have, let's say, 60, 45, 70, 13. This is my blue channel. And then green channel will be, this is green. Now this is one image. This is the 3-dimensional tensor, where this is the width dimension, this is the height dimension, this is the channel dimension. This is a 3-dimensional tensor for one image, but my batch will be, I will have a collection of this repeating 8 times because my batch size is 8. So it will be a 4-dimensional tensor like this 8 times. Now, like this, I will have 1000 of them because my total training data set is 8000, right? So that is the batch size idea. Now let's run the code. Here we define the UNet. So just look at the individual definitions of functions inside the UNet. There are 2D convolution. Which one is this? One thing which I forgot to mention is between the 3x3 convolution and ReLU activation, there is batch normalization. Batch normalization, I am not 100% sure if this is actually done in the original paper, but in most implementations of actual UNet, which I found on the internet, batch normalization was done. Batch normalization is a way to prevent overfitting from happening. So I don't think it's hurting in any way. If anything, it's good, but I'm not 100% sure if this was there in the original paper or not. That I have to check. But this is the con2D followed by batch normalization ReLU, con2D, batch normalization ReLU. What is this? If you look at it, it's the first block. In the UNet architecture, you have 2 convolutions and 2 ReLUs, and I say 2 batch normalizations, right? So that is what is happening here. So that is this one block. So because of defining this one block like this, we don't have to repeatedly write it. We just need to call it. And in the downsampling block, so or rather upsampling block, in the downsampling block, one more thing we need to define, which is the max pooling. That is this. And this way, I don't have to write this again and again and again. I just need to call it. Similarly, in upsampling, there will be the double convolution, bilinear interpolation. And then this forward is nothing but the forward pass happening through that module. So this the good thing about using TensorFlow is that we can define these functions for classes, and within that we can define functions for forward pass, backward pass, etc. It's very easy to define the whole neural network architecture. So now this entire UNet architecture is only this much. So just look at the individual modules. You will easily understand. Down one is you are going down in the encoder, first layer, going down in the encoder, second layer, third layer, fourth layer. And then in the decoder, in between, I don't think we have to explicitly call out the bottleneck because it's taken care of when you pass from this to the next. Upward in the first layer, upward in the layer 2, layer 3, layer 4. Yes, the number of layers are, as far as I have seen in the original UNet architecture, it's fixed. But there are many other variants. Like I want to discuss that a little bit in the next lecture. There is an architecture called UNet++. There is another architecture called residual UNet. There is attention UNet. So there are different variants of UNet, which we will touch upon in the next lecture, where the number of layers are not, the structure is not exactly this. Also, there is no, there is nothing that prevents us from adding more layers, right? We could add more layer. It's just that people, maybe they realize that with respect to cost benefit ratio, maybe these many layers are better. So many things which you will notice in computer vision in general are understood in retrospect. Of course, people are doing a lot of empirical experiments, but it's very hard to predict 10 years down the line, oh, that architecture makes sense. It's very hard to foresee that far. You will try out a lot of things, some things will work, and then in retrospect, you can explain, oh, this is the reason why this model works better than the other. But I'm sure there are some geniuses out there who can come up with architectures that are completely novel, that will work in one shot. But majority of the computer vision research hub happens in the other way. You try out many things, and things happen in incremental manner, and some things work, and then you explain it how it works. So yeah, so this part I ran. So this dice loss is the loss that I wanted to mention earlier. So this binary cross entropy loss is the loss due to pixel values not matching with the actual ground truth pixel values. The other loss is based on the IOU score. IOU score is intersection over union. Intersection over union of what? Intersection over union of predicted object pixels and actual object pixels. So you only care about those two patches, and you construct a IOU score based on that. Then you construct the dice loss by taking the average of those two. So dice loss is the term that is used to denote these averaging of these two losses. I'm using Adam. Learning rate and all are hyperparameters. So of course you can play with it. One thing that I'm going to change here is the number of epochs. Maybe this I can, or not here. Number of epochs I'll keep as 2 for now, so that the code will run faster. By the way, I hope the code is running for most of you, right? Can you confirm if the code is running properly? If it is taking time, just stop and try with 2 epochs, then it should run. Then the output I'll show you from my earlier run. The output is already here. Yeah. So this is how my output looks like. So there are pet images, dogs and cats. Images like this. Ground truth is like this. So ground truth is literally the mask. Okay. Now don't worry about the white and black color. It's ultimately up to the convention, like whatever you wish to use. Here the convention is that white color is the background, black color is the object. And you see the prediction here. The prediction is all the things in the background is looking in that green color mask. So here a mask is forming to just annotate the background. Rest of the things are not annotated. So this is how the UNet looks like. And here the loss, it will print the loss once this block of code is finished running. But the only way in which you can make sense of the loss is if you look at it from the point of view of dice loss. So obviously it will depend on not just the total number of pixels that are available, but also the size of the object. Because if the cat was only occupying 10% of the area, then even if you are making very bad predictions, maybe your loss won't be very high, because there is only so many pixels that you are occupying for the object. But I think with that, we can kind of wind up, but I'll be happy to take some questions if you have any questions with respect to UNet or mask RCNN or any architecture below. Meanwhile, let the code keep running. In the next lecture, I want to actually pick up so when we are cropping, can't we lose the information in the encoder part? That is true. So if I were to design UNet today, 2 things I will ensure is, one is cropping is totally unnecessary if we do padding. So if padding is there, this kind of a loss won't happen. Here it will be 572, 572, 572. Then you will divide by 2, divide by 2, divide by 2. So because of this loss not happening, when you upscale, you will be upscaling to the exact same dimension, 64 and 64, 136 and 136. But here, because that padding is not added, the losses happening during the convolution is getting divided by 2, right? And then you are again incurring losses. And then when you are multiplying by 2 by basically performing the up convolution, it's not helping you. So cropping, if I were to design the UNet architecture today with my current knowledge, I would definitely just add a padding layer so that I can avoid cropping later to prevent the information loss. So that is a very good question. Any other points? Any other observations or questions or points? one thing that I want all of you to try is try UNet for some data set, like something that is more industry relevant. Either it could be a satellite data for segmenting different regions in that aerial image, or it could be like an industrial pipeline data set or something where we are annotating the crops, or it could be a medical data set. So I can think of 3 segments in which this might come useful to you. And I'll be very happy if you can try either one of this, not everything. So satellite data set. Of course, you should have the ground truth available with you, or biomedical. Or third one is industrial, like pipeline or something like that. All right. So I might post this as an assignment, but one of these use cases at least we will discuss in the next lecture. But the other 2 would be an assignment for you. So I think today's lecture, we can wind up a little bit early. So there is one more update which I want to provide you. So next week, this week is fine, but next week there might be a chance that I have to reschedule at least one of the lectures due to some family events happening for which I'm traveling. But since it's during the weekday, I can also sometimes manage, but depends on the situation. So I will just text you if we are pushing one lecture to the week after, so that I'll text in the Discord. Can't access the note on the website. Oh, is that problem? Everybody's facing that problem, the notes not being accessible, the Miro notes, the pro people, by the way. It's supposed to be, it will load as a Miro infinite board notebook, like exactly how you see right now. It's supposed to load. In case if the note is not loading for some reason, maybe because I did not enable the viewing setting or something, just put it in the Discord. I'll fix it immediately. But thank you so much, everyone. I hope you enjoyed the architecture part of UNet. This encoder decoder you will almost always come across as you look at the models which were developed further ahead. Like after 2020, most of the models were, transformer based. Even recently, there was this new model which came out from Meta AI, Dino V3. So this is one of the state-of-the-art self-supervised learning for images. So I am yet to read the paper, but I think they have a, yeah, so just check this. So this same model can do all of this: object detection, depth estimation, semantic segmentation, and apparently it's the state of the art. So I'm yet to implement this or read the paper myself, but so many things are happening. This was just released, I think, a few days back. It's not even months. So just check out this. I think it's all relevant for people who are interested in computer vision. So with that, let's wind up the lecture. I'll meet you all again on Thursday. On Thursday, we will continue with some applications of UNet, and we'll also discuss about some other variants of UNet, which came out after the original UNet paper, like UNet++, and residual UNet, attention UNet, etc. So take care until then. See you soon in 2 days. Bye. New lecture from Computer Vision Bootcamp. Today we'll be spending some more time on UNet and some of the variants of UNet. And basically the task that we'll be still working on in today's lecture will be image segmentation. But in addition to what we did in the last lecture, which was predominantly dedicated to understanding the architecture of UNet in detail, this time we'll be coding a UNet for 2 different data sets. And one additional thing that I decided we could do is host a pre-trained UNet model weights on Hugging Face so that anybody could inference from the model. Basically, anybody could use the model for their segmentation task for this specific type of task. So I'll be also be introducing you to Hugging Face a little bit in case you are not aware of the platform itself. So we'll start as if we are complete beginners. So starting with the variants that we are briefly going to look at today. UNet we already discussed in detail in the last lecture. I will be providing a very brief recap on what we learned. But today we'll be discussing briefly about 3 architectures: UNet++, attention UNet, and residual UNet. But looking at the citations that these papers have, the UNet paper has almost 2 orders of magnitude higher number of citations. This has 118K plus, but the other papers have in the range of 1K, 10K-ish. So
from a popularity point of view and from a, I would say, scientific breakthrough point of view, nothing beats UNet yet. But we'll be looking at what people did in addition to the vanilla UNet architecture, which was introduced in 2015, and how did it change the overall, utility of UNet. So just to have a brief recap in UNet, as we discussed last time, UNet has mainly 4 parts to pay attention to. First is encoder. Encoder is everything to the left of this line. So it's like a very symmetric architecture. This is encoder. And this, everything on this right side, is decoder. Then what happens in UNet is, in the encoder part, the input image, which is originally a grayscale image, it will go through certain transformations. Many of them are convolution operations. So all these are convolution operations. Because there is no padding, the convolution operation reduces the size of the image spatially by a factor of 2 pixels at a time. And then these are max pooling operations, which will directly halve the dimension spatially. And by the time you reach the bottom, and this part is called bottleneck, the last layer, you will have an image of 30 by 30 dimensions. You had started from 572 by 572, but you will have 1024 channels. And then you will go up along the decoder. So encoder tries to make the information as abstract as possible, try to reduce the spatial width and height, but decoder tries to bring it back to the original dimension. But to avoid the valuable information from the encoder section to be lost, you also have these things called as skip connections. So these skip connections directly concatenate the encoded features from the encoder part directly to the same layer in the decoder. So totally there are 4 layers or 4 levels. This is level 1, level 2, level 3, level 4, level 3, level 4, and last one is bottleneck. So this was the encoder decoder architecture of UNet. We also discussed that a similar type of architecture is utilized in stable diffusion in generative AI, which we won't be going into detail today. Now let's discuss briefly what is the difference between UNet and UNet++. So the only difference in UNet and UNet++ is in the way you propagate the skip connection. In UNet++, you have some intermediate convolution operations shown by these circles. So this architecture, what you see, is a simplified version of UNet. This is nothing different. It's just that you are not providing as many details, but this is UNet and this is UNet++. And here the only difference is the intermediate convolution layers, which perform additional operations during the skip connection process, so that you are not directly passing the encoded features, but you are passing them through certain convolution operations before it finally reaches the decoder. So this is the difference between one of the differences between UNet and UNet++. And there are several advantages. The main disadvantage is that training will be slower because now you have more number of parameters to take care of. But the advantage is that when you are performing backpropagation, you have much more detailed connections from your final output to the previous layers. So here you can see that in the final output, so this final output is where you add the features from every single layer. So the first level of the encoder, last level, fourth level of the decoder. Level 1 and level 2, level 1 of the encoder and decoder. I mean to say, this is level 1 of encoder. This is also level 1 of decoder. So you can see that in the output, there are features coming from both of these levels, but also from these intermediate connections in the skip connection region, you are having some outputs. But you might be wondering, okay, if there are 5 outputs like this, how do we perform classification? How do we perform segmentation? Because we just want 1 mask ideally, right? Or 2 masks, 1 for background and 1 for object. So how exactly is it done here? So the way it is done is, in the training part of the UNet++, we will be considering the outputs from all these nodes, and a combined loss function will be created where all these outputs are compared with the ground truth mask. But during the inferencing, you might only look at the output from this node, so that whatever mask this node is predicting is being used for the final segmentation process on the input image.
So that's the main difference between UNet and UNet++. And so for certain tasks like biomedical image segmentation, apparently UNet++ have a better accuracy, but I'm sure it's also confined for specific data sets. We can't make blanket statements, but you can see that UNet++ is much more well-connected architecture, much more complex. Of course, inference might be slower. Training is definitely slower. So that's the difference between UNet and UNet++. Now in residual UNet, before I even show you the image, just by the name, we can imagine that there has to be some residual connections. Residual connections like what? Residual connections like those in ResNet. So in ResNet, as we had discussed in the last lecture, the residual connection was like this. You have an input. The input will go through some convolution operations, and there will be an output. And if this, whatever is coming out here as the output can be called as f of x and input as x, you are having something called residual, where you add this f of x plus x. So the final output from this ResNet block is f of x plus x. So although the output is this, the residual block in the ResNet is not learning f of x plus x. It's only learning f of x. Remaining x is already part of the input. And the advantage of this is that when you put this multiple times as in a series, you can eliminate the problem of vanishing gradient, because you will have direct connections. I mean, the inputs are directly propagated to the output. And because of that, even the earlier layers of the neural network has significant influence on the output. So back propagation will not cause vanishing gradient, because even this layer, even if this is the first layer of a 101 layer neural network, this layer also will influence the neural network output significantly, as we had showed in the previous lecture. So if we look at the ResNet 101 architecture, we can take any random ResNet architecture actually. So just take a look at this, or let's take a look at this. So in this architecture, you can see that there are residuals going all the way till the output. So whatever changes are happening at the input is having an almost direct influence at the output. And because of this, the loss is not just influenced by the later layers, loss is also influenced by initial shallow layers. So just based on this knowledge, we can already imagine that some residual connections where some addition will happen in the residual UNet. In normal UNet, we were not adding the input from encoder into the decoder output. We were actually concatenating. So we will have width times height times number of channels, let's say channels in encoder. And if this is the situation at a particular layer in the encoder, decoder may have a different width, W1, height 1 times number of channels in decoder. So let's say this is level 3. And this is also level 3. And this is decoder. This is encoder, right? Then what was done was you were cropping so that this W1 and H1 are matching this W and H. So this is first copied and cropped so that this becomes W by H by CD. CD is the number of channels in decoder. And then you will concatenate these two such that the final output will be W times H times CD plus C encoder. So something like this. So width and height will remain same as what is there in the encoder, but the number of channels will be sum of the number of channels in encoder plus decoder. So this is what was happening in the UNet architecture. This will also happen in the UNet, residual UNet, but in addition to that, there is a separate operation which is plus, which is not concatenation. You are adding the values. So the structure basically looks like this. So in every block of the encoder and in every block of the decoder, you can see that there is a residual block. So this guy, this purple dotted box is called as a residual block. And if you look at what is happening in the residual block, you can see that inputs are being propagated from one layer to after the next layer. And then whatever output comes out of that is being added with the input from the previous layer. This plus symbol shows that you are not concatenating, you are adding, similar to ResNet. And this has some level of influence on how much the back propagation can be better during gradient descent process. And this particular architecture, you might notice that this does not have 4 levels. It has only 2 levels. And then finally, there is a bottleneck. And then it has 2 levels in the decoder also, because this particular architecture was used for a smaller biomedical data set. But the residual UNet basic idea is almost same as UNet, except you introduce these residual blocks. These residual blocks ensure that at least within the blocks, there is some good amount of not skip connections, residual connections similar to ResNet. But there is no change in the skip connection. This skip connection will remain the same. So whatever we were doing in the UNet++, we are not doing that in residual UNet. Then there is one more architecture of UNet, which is somewhat popular. There are many other variants also. There are variants where both of these are mixed, where you have dense connections in the skip part of the network, plus you have residuals. So you can have that. But this one is called attention UNet. So don't worry by looking at this, I would say, a bit intimidating diagram. I'll explain it module by module. Let's focus on the part of the UNet first. So this is the encoder, bottleneck, decoder. Don't worry about this FHWD. It's like filters, height, width, dimension, depth of number of channels, right? So all of these things are the same. The only difference is now you will see these attention blocks or attention gates. So the purpose of these attention gates is that in normal vanilla UNet, you were passing the encoded features from the encoder. You were not really paying attention to whether those features are actually useful for image segmentation or not. You were directly passing it. The idea of this attention gate is that you will sort of modify the feature, whatever is coming from the encoder, whatever is coming from here, you will modify it a little bit based on what the decoder thinks at the moment is useful. So how do you do that? Just look at the inputs that are going into this attention gate. There is one input coming from the decoder. There is one input coming from the encoder of the same level of this, whatever this is. And then something happens to these inputs such that final output is a much more refined versions of this skip connection. So this is the skip connection plus this is decoder input. Something happens to the skip connection so that it becomes more useful to the decoder, right? Now let's see what is happening. So here, this is whatever input is coming from the skip connection. This is whatever input is coming from the decoder block. Then both of these are added. So here you can see a plus sign. They are being added to create just one single representation of input coming from the skip connection and the current inputs that are encoded in the, or embedded in the decoder part. And then they pass through a ReLU activation function. And then they are passed through a 1x1 convolution layer. And following by that, they will pass through a sigmoid. So I'm sure this part of however people figured out why this is useful is very empirical. So from a first principles, I am not sure how much we can explain the utility of, why here ReLU, why not maybe GLU or some other activation function? Why did we use ReLU? It's hard to, we can only explain it in retrospect. But at the end of the day, what is happening is just look at what's happening to this skip connection. Skip connection is also directly propagated here to the output. So this is still the skip connection. And if this attention gate was absent, so what is attention gate? This whole thing is the attention gate. If this was absent, whatever input comes from the skip connection would have directly went here into this is the input going into the encoder to be concatenated. This is what would have happened. And see, this part is like a zoomed in visual of this one attention gate, okay? So in the absence of attention gate, the input from the skip connection would have directly went to the, sorry, this is not encoder, my bad, decoder. Would have directly gone to the decoder from the encoder. But here, something is being concatenated to the skip connection. And what is that? Basically, the skip connection plus decoder inputs are added. And then it passes through ReLU, it passes through 1x1 convolution, it passes through sigmoid. And finally, what we are left with is something like a attention mask. And this attention mask is such that the values of this mask is between 0 and 1. So you add them, you add the two channels, skip connection channel and decoder channel, pass through a ReLU activation function. Then you have a 1-by-1 convolution followed by sigmoid activation. This produces a mask which has numbers like alpha between 0 and 1. So for example, a mask can look like this. 0.1, 0.2, 0.9, 0.3. And this name attention might ring some bell when you compare it with the attention head in the transformer. So attention, if you look at this, or let's say, if you look at the values that are there in the attention matrix in the transformer head, it will also look like they are numbers between 0 and 1. Just wanted to show you this. I don't know how many of you have seen this website. It's like a very nice visualization of transformer in GPT. So just I'm pasting it in the chat. Just check this out. I don't want you to spend too much time right now, but just you can have a look at it later. But let me show you these numbers after normalizing. So here the numbers, it's like a matrix of n by n, and the numbers in each row will sum up to 1, and they are all between 0 and 1. So this is like the way in which transformer will notice how query and key are correlated with each other. That attention is, the name sounds similar, but the attention matrix structure is very different here. Here, what we have is a matrix of, let's say, numbers like 0.4, 0.5, etc. And what this mask, alpha mask, what this says is how much does this region from the encoder, how much does that region, how much is it useful for final segmentation? So if the value is closer to 0, it means whatever pixels correspond to this particular region from the skip connection, they are not very useful. That is what it means. If the values are, let's say, above 0.5, it means those regions have more utility in final segmentation. So basically, this mask produces a set of numbers for important features and unimportant features. So if alpha is close to 0, the features corresponding to those pixels from the skip connection input are kind of suppressed. If alpha is close to 1, those features are retained. So this way, you are not directly passing the values of the skip connection from encoder to decoder. You are making it pass through an attention mask, and this attention mask either suppresses or keeps whatever features are relevant as such. As such meaning almost as such. You are multiplying with a number close to 1. So now these resampled weighted features, why do we call it as weighted features? Because we are multiplying with these numbers between 0 and 1. They are now passed into the final decoder for concatenation. So this is the primary difference between vanilla UNet and attention UNet. Now, I don't want to spend too much time on the variants of UNet. I want to directly now jump into implementation of the UNet architecture itself. And in the last lecture, we were discussing about 4 use cases. First one was industrial, like pipe crack detection or detection of some kind of structural damage happening. We were discussing about biomedical. We were also discussing about aerial image. And I don't know if we discussed any other self-driving car application or something like that, but you can imagine many other industrial applications for segmentation. So today we'll be looking at one industrial application with a small toy data set, because big data sets will take more time for us to train. We will also look at one use case from this aerial images, again with a smaller data set, but we will try to train the model to the best possible given the time constraint, and we'll try to perform validation on the data set. And after we do these things, one of this, probably this, we will try to host on Hugging Face. So all of us will do this together. And don't worry if you don't know how to use Hugging Face. We will all learn that together today. So with that, let's get started. I will share the Google Colab notebook with you, but please first get started with your Colab notebooks. I'm going to share the code here and I'll explain you it block by block. It's very easy, by the way. It's not a
the UNet architecture is anyway kind of easy architecture. Okay, so please first have this collab notebook. One more thing I will do is I will share the Google Drive link with all of you. Okay, so this is the Google Drive link for the crack detection on concrete. And for the next exercise that we are going to do, I'll also share that link. So please keep it handy, this aerial segmentation. So do one thing, just make a copy of both of these folders in your Google Drive so that you can run the code yourself. So as usual, first thing is, if you have a GPU access, just try to connect with a GPU or TPU, whichever you have. I have connected with the A100 GPU. As you know, I have purchased the GPU credits on Collab. And here the dataset path for me is this content/drive/my/drive/concrete crack. So this path might vary for you depending on what exactly is the name of your folder in which your data is there. But if you don't change anything with respect to the folder name, you should be able to keep this as such. So I will ask you, so can anyone confirm that once you have the copy of the data set in your Google Drive, is this block of code running for you? Importing the data set. So basically, I will just mention how exactly the data set looked like. So the concrete data set looks something like this. It has two folders, images and masks. Images are bunch of images of concrete surfaces that looks like this. Can you see the my folder in which these concrete surface images are shown? I'm not sure if I just shared my window or if I am sharing my entire screen. Can anyone confirm if you can see this concrete image? Okay, yeah, thanks. So these are the surfaces, and you can see that there are some surface undulations. Sometimes you will see crack, for example, yeah, like this. So here you can see that there is a crack that has formed, and the corresponding mask is something that looks like this. So if cracks are not there, it will be like a black color thing because there is nothing to annotate. But if cracks are there, here you can see that wherever that crack is there, there is some whitish/grayish color annotation. So this is the data set. And the naming is such that the first file is crack01.png. Image is also crack01.png. Basically, the name of the file, I mean, this is JPG, the other one is PNG. So all the images are of JPG format. All the masks are of PNG format, but the file name is the same. So that's the way in which you can, which mask is corresponding to which image. Then the other data set, I will just describe that briefly as well, is the aerial view data set. And that data set has 8 subsets in which images would look something like this. So these are the images which are almost like, it doesn't look like satellite image. Maybe it's a zoomed in satellite image, but almost like that, of different regions, cities. There are some desert areas. There are some areas with greenery, water, etc. And then masks are exactly the masked representations of those same satellite image shots. And different colors have different meaning. And the meaning is shown in this JSON file. So this JSON file has the description of classes. There is water. Then there is, I don't know if you can read this. This font size is a bit small. There is water. There is land. Then there is a road. There is building. So there are, I think, 7 or 8 different classes in this classes.json, actually 8 classes. So this will be the second data set that we'll be working on. So first, let's do one thing. Let's start running this code. You first import the libraries that we need. These are standard libraries for PyTorch for plotting. Then data loader for creating training and validation data. So nothing fancy here. Then next thing is preparing the data set. So in the data set, we have to define the directory because we have 2 directories, one for images and one for masks. And we have to define those 2. And then finally, we convert image into the tensor format. So we discussed this last time, right? If we have tensorial representation of data, it's better than NumPy representation, and NumPy is better than just the Python list. So NumPy better than list, tensorial representation better than NumPy. So this particular function, functions inside the class is just doing that. So just run the code. Let me know if you're able to run the code, or if you have already finished running the code, just let me know. And we are splitting the training and testing, 80% for training, 20% for testing. Batch size is, in every batch of images, there will be 8 images. Like that, there are 640 images in the training, 160 in the validation. And here we are just displaying one random batch, and you should see that the images and masks are as shown here. So these are some images, these are some masks. And as you can see, when there is no crack, mask is just black. So black corresponds to background, white corresponds to object. Here our object is simply the crack. You might also wonder, do we actually need image segmentation here in this case? Why can't we maybe do some thresholding, something like Otsu's thresholding or something, where we generally suppress those pixels with high pixel values and retain those pixels with low pixel values, because whenever there is a crack, those cracks will appear dark in color. It is probably possible to do, but the thing is, in such an algorithm, there is no learning involved. We are just keeping a hard defined criteria to say what is a crack and what is not a crack. But here, because we are providing a mask, the mask will serve as a way in which the neural network can learn that in this case, for example, there are actually a lot of black color dots, as you can see here. But the mask is showing nothing, which means none of these undulations on the surface is being considered as a crack by the definition of mask. So, and because of that, hopefully, when we feed an image that looks like this in the validation data set, it will again give us an output which looks like black color. It will not annotate every single black pixel as a crack, because that's not true. Black pixels, undulations are not cracks. So this is the sample data set. And then we define the UNet architecture. Definition is super simple. We have the convolution block in which one convolution, one ReLU, then again another convolution and another ReLU. One difference here is that in the previous lecture, we had also done a block normalization inside this. So convolution, ReLU, block normalization, batch normalization, which we are not doing this time. We can do it, we cannot do it. So in the original 2015 paper, they did not do it, but in the case where many people were implementing it, they were generally implementing batch normalization also. And then you have 4 levels in the encoder, and then 4 levels in the decoder. Decoder 4, 3, 2, 1. Okay. So I'm not going to explain the UNet architecture now because we have spent sufficient amount of time. Then we define the forward propagation, which is going from level 4 to level 1 to bottleneck through encoder, and then in decoder level 4 all the way till level 1. Then in the training setup, I had originally played a little bit with the learning rate, and I saw that if I was keeping the learning rate as 10 to the power of -4, I was not getting convergence. My output was very, very bad. I had also tried with 10 to the power of -2. That was also bad. So for me, the sweet spot, I just manually found out. I did not run any hyperparameter tuning, but just manually found this to be the best learning rate for me. But feel free to try different learning rate, whatever works for you. And then number of epochs 20. So the reason why I want to run here 20 is because we will be uploading the same model to Hugging Face. So please make sure that you are running this for 20 epochs so that you have a good model. Okay. So once you have finished running the code, just let me know if you have reached this part. The final thing which is of interest is this line, saving the model weights. So can anyone confirm if you have finished running the model and if you have these weights, this line also executed? Once this is executed, you should see a file called UNet weights v2.path over here. Right now, I don't have it because I haven't finished running this. So just let me know. Can anyone let me know if you are managing to run this halfway through or something? Then I can proceed to the next step. Oh, you did not. Okay, here is the collab link. Just take a copy, and there were two Google Drive files. First one is the concrete crack dataset file folder. This is the folder for concrete crack. So please make a copy of that. For the next code, it's aerial segmentation, but that I will share later. I already shared it once, but I'll share it once more. So just let me know if you have been able to run this. Now, what we will do is once this finishes, right? We will just take some random 4 images as the input for evaluating the model, and then we will try to make a prediction. And for those data sets, since we already have the ground truth, we can compare again. So these are some outputs that I have. So here input is this, ground truth is this. Prediction is not so great. I mean, it's good, but not so great. I have just run for 20 epochs. I could run for a bit more to make sure that the model is not under-trained. But here you can see that in some cases, when the ground truth is purely like a black image, in the prediction, there are some white spots coming. So you can see that there is some white spot being predicted here. Here also, there is some white spot being predicted here. And at those locations, you can see that in the input image, there is some small black color undulation here, which is detected as a crack in the prediction, but not in the ground truth. So according to ground truth, it is not a crack. Here also, this small black color dot, according to the ground truth, it's not a crack, but according to prediction, it is a crack. So this is what we have. Now, what we are going to do is, please open Hugging Face. So just go to Hugging Face, just Google Hugging Face, and just go here. And then let me share an account where I don't have, okay, maybe I can show it here itself. Just go to Hugging Face and create an account using your email. Doesn't matter whether you provide it as a company email or personal email, does not matter. If you already have an account, just let me know that. Then what are we going to do here? We will upload, I mean, we'll upload 3 things, but all of them are not used here. We will upload the data set. We will upload the trained model. Then we will upload another code, which is for hosting the Hugging Face application. The application would look something like this. I have already posted it here. If I go to Vizuara and this UNet crack detection, this is a hosted application where you have a nice user interface. In this user interface, I can upload a random image with crack. So here I could upload this. So this is an internet image. I did not even get this from my data set. I randomly went to Google, asked for concrete crack. And here, if I submit this, automatically the evaluation will happen using a pre-trained UNet, which was trained by me. Then I uploaded the weights of the UNet, and then here it's detecting the crack. So this is what we are going to do. But what is Hugging Face, first of all? Hugging Face is a platform where many different types of models are hosted. There are also data sets hosted. So for example, if you search GPT OSS, the open source model of GPT, you have this 120 billion parameter model hosted. You can actually inference the model. So there are people who have hosted the model such that you can play with it. So here we can say, hey, what are your capabilities? So this is as if you are chatting with ChatGPT, but you have a open source model hosted using, I would say, Fireworks provider, right? And then you can chat with the model here. Similarly, in segmentation also, if you just go to models, then if you click tasks, click image segmentation, here bunch of models will appear, which are already existing models, which are pre-trained with huge number of downloads meant for segmentation. And here, if you sort it based on, let's say, most likes, then you will see some amazing models which can be used for segmentation. But if you want to try out a model for segmentation, you can go to Hugging Face Spaces, in which you will see posted applications which are ready to run. And here, if you search image segmentation, so there is a model which was called as mass generator segment anything. Okay, let's try this segment anything web. And here I can upload some random image. Okay, not this. Okay, this is an image of myself. And here it's processing the image to detect different regions. And yeah, let's wait for some few seconds. And meanwhile, I want to show you one more Hugging Face model. So let's say in the last lecture, we discussed about this Dino V3. So in the Dino V3, so in this link, you can get inference on Dino V3. It was actually available till yesterday. Let me just check once more. Yeah, I think this one. Okay, you are getting an error saying list out of index range error when running the code. Can you tell me in which line are you facing the error? It might show like in which block are you facing the error? Is it somewhere in this one? Perhaps in the dataset creation part, because that may happen if you're duplicating the Google Drive folder is not fully done. I was getting some error similar to this. Yeah, get one batch. Okay, can you go to the Google Drive folder and see if the data set is actually there and it has two folders, images and masks. If those two folders are there and if those folders are not empty, I think it should be fine. Okay, meanwhile, our segmenting is done here. So here, if I move my mouse on different parts, see it has nicely segmented person, these glass panes, this background, then this wall. So I'm just moving my mouse pointer to select those segmented regions. Super cool, right? So this is like how we can make use of hosted models on Hugging Face for quick inferencing. This Dino V3 also is supposed to work. I'm not exactly sure. We can try an example. Maybe that is better. Anyways, meanwhile, this is loading. I'm not sure if this particular application is right now active or not. It seems active, but it's not working for me. Anyways, now what we are going to do is we will, once you have created the account on Hugging Face, we will see how to push the data set into Hugging Face, right? So we have this concrete data set. So we will create a repo on Hugging Face itself. And into that repo, we will push the data set. So first, you will have to install these two things. This data sets is from Hugging Face and Hugging Face Hub. So I'm going to copy paste these two lines. Just run this on Collab so that these two libraries are installed. Okay. And once that is done, you can mount your Google Drive folder with the concrete crack data set. I don't know if your folder name is this concrete crack or something else, but whatever it is, change the name appropriately. This name to whatever is your folder name. It should be concrete crack dataset unless you do something with the folder. So just run that. Then the third thing is we have to log into Hugging Face using a certain API. So I will tell you where to get the API from. But before that, let me connect the Google Drive folder. And to get the API, go here, go to Hugging Face, click on your profile account, and there is a section called Access Tokens. So click that. And then here you can create a new token. So click Create New Token, name it as something, Hugging Face _ token. And then in the permissions, I usually provide all these repository and inference permissions. And here in the organization, if your Hugging Face organization has a name, just select that name. In the repo, since this is for creating the repo, I guess you don't need this, but otherwise you will have to select the repo in which you are going to make the change and just give the repository permission to this organization, Inference. Or if you simply want to just provide read or write permission, if you want to just provide write permission, just click write instead of fine grain. That might be easier. Then create a token. Then whatever your token is, copy that. Once it is done, I'll be deleting this, of course, but copy that and then go back to your Google Colab code, run the login. And here it will ask you for a token. So just paste it here. So I will share this code also with you. Just so do this on a different Google account so that the previous UNet training is not getting interrupted. So I'm just going to share the Google Drive link with you. Google Colab link with you. So just use that and here paste the Hugging Face token. And now you are connected with Hugging Face. And then you're going to create a repo. So in the repo, two things you have to notice. One is your Hugging Face username you should use here. And the data set, if you are uploading the data set, just whatever name you want to upload. So here I already have a folder called Concrete Crack dataset on Hugging Face because I had done this before. But here I will put it as version 2, V2. And I will set it as a public dataset instead of private dataset. So you can also see it. So when I run this code now, it will take some time because there are some images in this data set and it will take some time for me to run the code. Okay, so here it's throwing an issue. Issue is that it does not have all the permissions that it requires. So let me just go back to my Hugging Face and maybe create a token. I'm using another token, which I had created earlier, and login. Or maybe I'll just restart my session so that everything is starting from clean. So what we are going to do now is we will create the data sets in Hugging Face. It has three things: data sets, spaces, and models. So model, we will upload the trained UNet model, the model weights. In the space, we will host the application where anyone can come and upload a cracked data set and infer from it. So this was my application which was hosted earlier. So I'll share the link with you. It should be a publicly accessible app. So just check out this app. And if you go to Google, download any, just in Google, go and search concrete crack. And if you upload that crack image here, and if you submit, ideally, you should be able to get the segmentation. Just let me know what's happening. So this is what we are going to do. And we'll run the Hugging Face login, paste the access token. Oh. Is anyone at this stage where they have finished running the UNet training part? Also, just let me know once you run the crack detection Hugging Face app, the one which I just pasted now, whether it's working for you or not. Just let me know. But at the end of the day, it should be a hosted app that's working perfectly fine for you. Meanwhile, I'm just trying to figure out what is the issue with respect to these permissions. So I'm creating a data set manually called V2 private publicly, and then I just want to try with this. So I just created the data set, and it will look like a GitHub repo, but empty. So this the way this is managed is using Git for version control. So right now it's empty, it has nothing. But what we can do is now go to the access tokens, and in the access tokens, just let's invalidate this, or let's just edit the permissions of this. And here I can change the repo to dataset v2. And here I'm giving all the permissions, read, write, everything. And now hopefully, if I create a new access token, copy it and paste it in my login, I should be able to access that. Anyone facing similar issue, fine grain to write? Let me just try. Okay, I think there is still an issue. I'm just checking if there is any spelling issue or something. So my repo name is, just let me know if any one of you are facing a similar issue. Basically, I have this dataset repo called Vizuara / concrete crack dataset v2. And I just want to connect to it to upload the dataset, right? So this is the data repo ID, Vizuara / concrete / crack dataset v2. And I'm logging in using the right permission, but for some reason it's not working. To all your orgs resources and can make, okay. So creating the token, it has right permissions, just copy it. And disconnect runtime. Wow, this is still not working. Let me just check if I need to do something which I'm not doing correctly. And meanwhile, let me know if for you also this code is showing the same error. Basically, the error that I'm getting is I don't have permission to write to this repo. Incorrect username. I don't think username is wrong. Okay, for a moment, I'm just giving all permissions. I don't think that's the best practice, but just want to get this to work. So here in the orgs, I have these. Okay, so now that I have all permissions, hopefully this should work. This is a weird error. I have not noticed this error before, other than just making a spelling mistake. If any of you know how to fix this error, that'll be great. Basically, the error that I'm getting is I don't have permission to my own repo, but I do have clearly. Okay, now it seems to be working. So what I did was I replaced this code, repo ID and create repo. So instead of asking to create a repo, because that repo already exists, I don't know why this error was happening. So I'm just going to comment this out so that not causing an issue later. What I did was I copied this particular code from Hugging Face itself. So in the dataset card, Hugging Face provides command line interface, Python code, or other forms of codes for you to push items into your existing repo. So here it gave this code and I just copy pasted that in. Okay, let's see what prediction. Yes, I was also getting the similar error, Anita. So what is your learning rate right now? That is clearly wrong. The prediction is clearly wrong. My learning rate is 10 to the power of minus 3. And my loss is reaching 0.0114. So, and because of that, my prediction is good. But if this is something like 0.2 or 0.4 or something, then I was getting a prediction like completely black mask. So just let me know what is your loss. Just try playing with this learning rate a little bit. It might, okay, loss is 0.45, yeah. And how many epochs? You also ran 20 epochs, right? Yeah, yeah, I think you should definitely run for more epochs. I was getting the same error like when, can you do one thing? Can you try increasing the learning rate? If it is 10 to the power of minus 3, try 5 times 10 to the power of minus 3 or something as the learning rate and see if the convergence is better. Then we can see. Anyways, my Hugging Face is now working, thankfully. And currently it's uploading the data set. So one thing that I found to be weird is the dataset folder size is actually very small. It's just 7 megabytes. But still, it takes a little bit of time for us to upload the dataset. And once we upload the dataset, it will look something like this. So go here, go to this dataset. So this is the one which I uploaded previously. And it has, so once you have uploaded it, it will nicely create it to something like this. First of all, it's not classes. Okay, so this part is anyway wrong, but the data set will look like, if you go to files and versions, there are two folders. One is images, other one is masks. In the images folder, there are a bunch of images. In the mask folder, there are corresponding images which are masks. Okay, so this is ultimately what we wanted. But this data set, we are not going to directly use for inferencing. I just wanted to upload it here just to show you a good practice of creating the pipeline in Hugging Face. Next, what we will do is, while I'm running to upload in this dataset V2, this is anyway like for showing you as an example, we don't need it. What we will do is, if any one of you have managed to train the model and get the model to a decent loss, like something like 0.01 something, then just run this block of code, which is to save the model. Okay, so when you run this code, you will get this UNet weights underscore v2 dot path over here. So just click the 3 dots and download it into your desktop. So just let me know where you are till now, and then I'll tell you what to do next. So while your training is going on, let's do one more thing. Go to Hugging Face and let's create a spaces. So click your profile icon and click new space. And this new space is something that we are going to be hosting publicly. So we can name it as, I would say, UNet for crack detection in concrete. Okay, and then upload a cracked concrete image for segmentation. And license, I can pick MIT license, and I'll be using Gradio. So Gradio is the, we can convert Google Colab or Python code into a nice interface using Gradio. So we'll be using Gradio, and I'll start with the blank template. And this inference engine, which we are publicly hosting, if we want people to be able to use it in a fast way, we can pay for it ourselves and use these. But here I'll just use CPU basic, and then keep it public, and then create space. So when you create the space, it will be initially empty, nothing is there. We'll have to create the files ourselves, and there are 3 files that we have to create. Okay, so first is, so go to the UNet for crack detection in concrete, click files. So go here, and it should be currently empty. Here, click contribute, create new file, and we will name this file as app.python, app.py. And I will share the app.py code with you from my previous Hugging Face space, the one which I had hosted earlier. So this app.py code, just paste it in your app.py. So here, please notice what we are doing is we are defining the user interface elements. So first we are saying the saved weights, the weights is in a certain path. The path is Vizuara / UNet crack segmentation. But this path you will have to change with your path, and I will tell you where exactly to change it. For now, just paste this code in the app.py. Okay, just sharing the code with you. So we need 3 folders here. One is the model itself. Actually, I'm not able to save this in the chat, so I'll just download it and I'll share the download link. Just try this. Okay, so for Anita, learning rate 10 to the power of -5 worked, is it? Okay, very nice. So increasing the learning rate did not work for you, decreasing it. Okay, very, very nice. Okay, I think this is very good. Excellent. So Anita, what you should do is just save your model by running this block of code, and then download the saved model from here. So here, if you refresh, it will appear, and just download it. Okay. And meanwhile, this link which I have shared is the app.py code. Just download that code also, and then you can paste it in your app.py. Next is, the next file you will need is, so in my app.py, I'm going to paste this code. and commit. So when we commit, each time when a change is made to this repository, automatically the app will start building, just like in web app for continuous deployment and continuous integration. This is how it works. Then the next file that we need is the model itself. So the model folder can be named as something like UNet_model.py. So to create a file, UNet_model.py. So what we are essentially doing is we have to define the front end so that when we host the app, there are provisions like buttons to click and upload, etc. We need a place to store the actual model, not the weights, but the model architecture itself as a function. So that is what we are doing here. And that function is looking like the unit definition. So this unit class was defined in our code, in our training code. Same thing we are copy pasting here. So just let's paste it here, UNet_model.py, and just commit that. The third is you will need the weights, basically the model parameters. Which model parameters? The one which you trained. So the one which Anita you have trained right now, you can download it and upload it in this space. So in the spaces, if you go to the files, currently you should have only two files. One is app.py and one is UNet_model.py. These two are default files, so ignore readme and git attributes. But these two, app.py and UNet_model.py should already be there. And then on top of it, you'd say upload files. And in the upload files, just upload from your computer, the one which you had downloaded from Google Colab. For me, it is this UNet_weights_v2.path.pth. Then just upload it also. So now once this model is uploaded, this app will again start rebuilding and it should be hopefully ready for deployment. So just to reiterate what we have been doing in Hugging Face is, first is we go to Hugging Face and create an account. So in this, there are three things which we will be doing or we are doing. One is uploading the data set. Second is uploading the model. And third is creating a space. In the data set, we are simply uploading the concrete crack data set. We are not using it, but it's just for a good practice of creating a Hugging Face data set. In the model, we are uploading the UNet pre-trained. And what is this pre-trained on? It's pre-trained on concrete crack images. In the spaces, we are uploading three files. One is app.py. This is where the Gradio code is defined. Gradio for creating the user interface for uploading the image, etc., like an app. Second is the UNet model itself. So UNet_model.py. And the third is the weights, the UNet pre-trained weights.pth. So these three things we upload in the space, and in the model, we have UNet_pre-trained. But while we are hosting the space, these two things are not being directly used. I just showed you how to create the data set in Hugging Face and how to upload a model in Hugging Face just as a practice. But for creating spaces, we are anyway only looking at these three files. Okay. The Python model for UNet was already predefined here in our code. This guy. This UNet code is what is being used, this class UNet. So that code we copy pasted along with the torch library, import torch.nn as nn. So those two things we uploaded. I think there was a requirements.txt. I'm not sure if I had to upload this here or not. But anyways, then the second thing was in the app.py, in your case, you will have to define two things differently. One is the path to the model. For me, it will be whatever is the path to this guy. And second is you will have to custom define path to your pre-trained weights. pre-trained weights. For me, the pre-trained weights are this. So whatever is the path to this file is what I need to provide. So for you, the only place where you will make changes in this app.py, go to this repo ID, and whatever is your repo ID, you should use that. And the file name, whatever is your file name here, you should use that. The other thing is the UNet underscore model, right? The file name that I have used for my .py file is called UNet underscore model.py. So if you are using that name, then you can say from UNet underscore model import UNet. So import UNet means that class name is UNet, but the file name is UNet underscore model. But if your file name is different, you will have to make that modification here. Okay. So now let's see if our app is ready to just check, ready to infer. So I have two apps. This was the earlier one. I think this is the current one. It has a runtime error. Okay, no module name torch. So I have to add a requirements.txt in my repo. So I can add torch, and I can add, because when this is added automatically, those libraries will be installed. And I will also need maybe Gradio, I guess. So this requirement.txt is one way to tell your Python code that, okay, these are the packages that you will have to pre-install. So just do that as well. So just let me know if anyone managed to create this Gradio app yet, or if you are facing any error while creating this. So here you see, this is showing building. And the reason why this is being shown is because I just changed that. I just introduced that new file, requirements.txt, which is why it's currently building. So whenever a change is made, just like when you make a change in the GitHub repo, if it's connected to Vercel or something, that change will trigger a deployment, right? Same thing is happening here. But if everything is fine, if all the packages are properly installed, hopefully you should see things working. But let me check the log to see what package is missing. And meanwhile, let's also run the other code for running the aerial image. So I'm going to share the aerial image. I had shared it earlier. So somebody has shared the aerial segmentation Google Drive link right now. So please check that. That is the Google Drive link. And aerial image, for that, I'll have to install this segmentation underscore models underscore torch. So please uncomment this line and run this once if you have not run it yet. So this will install this this particular segmentation model, PyTorch segmentation model. And then just run the code. And at the inferencing, what I'll show you something. If you are running only for 2 epochs, this will be a very, very bad output. I'll just show you how my output looks like because I just ran for 2 epochs compared to ground truth. And meanwhile, the Hugging Face space is being built. I think one more error might happen because I'm not sure if I have added all the required packages in the requirements.txt. So I'll have to check that. And So in both of these codes, please note, we are not running UNet++ or residual UNet or attention UNet. We are still running UNet, the vanilla UNet model. So please don't get confused. Yeah, so here, this is another part where you will have to make some change. I've run for only 2 epochs, but I would say it's better to run for like 20 epochs or something, but I did not want to wait. So I just want to show you what the output looks like with just 2 epochs. It's not very good. I also tried one more thing, which was using this exact same model for segmenting from videos. So the videos that I was looking was this pixels. Aerial view, something like this. So I tried for a video that looked like this, an aerial view video, but the segmentation was very, very bad. It's probably because in this case, the segmentation data set, right? It's extremely small. If you look at the folder structure, I have only around 50 or 60 images. This is not at all a big data set. I deliberately chose a small data set simply because I did not want to spend too much time during the lecture for training. But here, if you look at it, there are like 1, 2, 3, 4, 5, 6, 7, 8, 9, some 9 images and 8 folders. So totally like something like 50 or 60 images max. So in any case, we should not expect very good accuracy. But what I recommend you do is there are some aerial segmented images, big data sets with thousands or tens of thousands of data points, perhaps on Kaggle or other places. So if you train your UNet model with that data set with sufficient number of images, so here I'm not sure how many. I think this is also the same data set, this Dubai data set. Exactly, this is the one that I'm using. But we need something better for using for a general purpose aerial segmentation. So whichever data set you find, maybe from Hugging Face or elsewhere, just try training your UNet and let me know what kind of result you get. That could be your next assignment. So let me just note down what is that you're supposed to do. First is find more extensive data set for aerial images. Then construct vanilla UNet. Then train this model. Yeah. So collab link, I just shared, right? I thought I already shared, but I'll share it with you anyways. This is the collab link. So just do this, train the model, then save the weights, then convert to a public, public Hugging Face space. So there you will be using 3 things. app.py for just defining the Gradio interface, the pre-trained weights, and this will be the model itself, whatever UNet model you are using, .py. This will be like .pth, and this will be .py as well. So these 3 are the files that you will need, and of course you will need a requirements.txt file for mentioning your packages which are required. And then share the link. I'll host an assignment, but you share the link in the assignment. And what I will be doing to test your model is I'll be picking random aerial images like satellite image or big drone images from the internet. And I will be putting it in this inference engine hosted on Hugging Face to see how good the segmentation is, right? it'll be a very nice exercise for you to build this whole pipeline. But here, yeah, so this is my output, right? You see the quality is kind of not very good. All these things, whichever is black pixel is being segmented nicely. Some of them are these blue roads. Some of them are being identified nicely, but prediction is not at all good. Mainly because my epochs are just 2, and you can see that I'm still under training significantly. You could bring this down by a lot. So I'll just keep running this for 20 epochs on the side, and I will try to make this better. But please note, if you just paste a Hugging Face, I mean this code from your current aerial image dataset base code, it will not work because the dataset size is very, very small. It's just what, as I said, 50-60 images. Ideally, in my opinion, there should be maybe 5,000 images, because the number of classes we are segmenting are maybe 8 classes, right? So 1,000 images per class, or 1,000. There should be 8,000 images, hoping that predominantly each image belongs to one class, although in every image there are multiple classes. So something like 5,000 to 10,000 images might be good to have in the data set. But obviously that will mean that your training will take time. You may have to run the training overnight. So just do that. And to make sure that your screen is not dying, as I showed in the last lecture, I have installed this plugin, this extension called Wake Up or something. What is this called? Keep Awake. So this just install this Chrome extension so that it's on this screen awake mode. But once this is finished, I just want to show you the result. I might be posting it on Discord. But I think this is a good time to wind up the lecture. But I just want to take a brief recap of what we learned in UNet. So UNet is a fantastic architecture for semantic segmentation. In the last lecture, we discussed the difference between instance segmentation and semantic segmentation. Semantic segmentation is you look at every pixel and you ask a question, hey, is this pixel belonging to class A or class B or something else? So you are only looking at the class. You're not caring about whether this is the 50th instance of the class or second instance or first instance. You don't care about number of times that class is appearing. So that is called semantic segmentation. We also discussed that it's useful in the case of, let's say, tissue classification into cancerous or non-cancerous. You don't want to draw boundaries between 2 cancerous tissues. You don't care about that. As long as the tissue is cancerous, you want that pixel segmentation, right? So that was the main idea behind semantic segmentation. And UNet is extremely good for that because of its unique encoder-decoder architecture. So it's called U because of its shape. This is UNet. And this whole thing is encoder, and this whole thing is decoder, and this bottom part is the bottleneck, and these are skip connections. So encoder will bring down the spatial resolution of the image but increase the number of channels. Here it was 572 by 572 by 1 channel, but this was the spatial dimension. By the time you reach the bottleneck, it will become 30 by 30 by 1024. So spatially much smaller, but channel number wise much deeper. And then, so this will allow you to create many different abstract feature representations in the image in different channels. Then there were these up convolutions. We discussed in detail how exactly does the up convolution work. It works through bilinear interpolation. And then you can replace, you can restore some of the lost dimension by this up convolution. But this skip connection will also ensure that you are concatenating values which are more richer in features closer to your original input data from the encoder into the decoder. So this was the most powerful thing about this encoder-decoder architecture, very different from ResNet, because in ResNet you are adding, here you are concatenating. Then in this lecture, we discussed about some other architectures like UNet++, where there are additional convolution layers in between in the skip layer. And this allows the neural network to learn much more deeper patterns rather than just directly passing the encoded features over here. You're also making it perform multiple convolution operations. You're also, if you look at the up convolution, there are layers from this being passed here, this being passed here, this being passed here. So it's like a much complex convolutional neural network architecture. But this also allowed to have all those slower training and slower inference, allowed to have much more better gradient propagation or back propagation. Then we also discussed briefly about the residual unit. Residual unit is nothing but inside this block of each layer of encoder and decoder, you have these residual connections which are adding. So plus means you are adding whatever is input is coming from here to here. So spatial resolution does not change. See, this is 64 here, this is 64 here. This 64 is not becoming 62 because you are probably adding padding. And here you see 128 is remaining as 128. Otherwise, you can't add. How will you add two different filters? I mean, two different features of different spatial dimension. You can't. Otherwise, you'll have to crop and add, which was being done in the skip connection. Then after that, we finally also discussed about attention unit, just from a theoretical level, not from an implementation level. Just the concept that people were doing were here, they were filtering out the features coming from the skip connection for relevance. And how did they find this relevance? They constructed as something like an attention map, like using alpha. So the map was something like this, where there are numbers of alpha ranging from 0 to 1. So if alpha value in let's say this cell is close to 0.9, it will, the feature corresponding to that cell will have high relevance. If it is close to 0, it will have very low relevance. So this was the idea behind kind of refining the skip connections using this attention gate. And this resulted in slightly better segmentation. But at the end of the day, if you look at popularity, if you look at the massive adoption, the vanilla unit is still massively adopted. And one last thing is, as I showed you in the last lecture, UNet is also used tremendously in diffusion models. So if you search UNet diffusion model, you will simply see this architecture where you can see that this denoising part here is basically a UNet. So UNet was literally, I would say, revived, and maybe 1/2 of the citations that came for the UNet paper, it has 118,000 citations. Half of them might have come because of its relevance in stable diffusion. And then today we implemented the UNet model for these two data sets. One is the concrete crack data set. Another is aerial image data set. Both were technically like a toy data set, mainly because of the size. Data set size is not very high. One of them has around 700 and something images. The other one has only 60 images. But because of the sheer size of the data, the in terms of megabytes, see here 20 epochs are just finishing, right? It's taking time for us to perform the training part. Inferencing is fast. So see here, now this is the new inference after my 20 epochs, slightly better, but not as good as it could be. But this is what we have from the UNet segmentation. And we don't deserve any better because the data set is very small, which is why I want you to try out on much bigger data set. The last thing is we discussed how to create Hugging Face spaces, data set, and models. In the spaces, in the Hugging Face, we'll be uploading a grad.io app.py. We will be uploading the UNet architecture itself. So app.py has the definition of the front end for our application. This UNet model.py has literally the class that defines the UNet. So the way we will be importing this into our app is just like how we import any other library. Just check this. From UNet _ model, import UNet, right? This is exactly how we import any library into our Python code. And then the last one is our pre-trained weights. So these are the pre-trained weights of our UNet, which we trained using the concrete crack data set. And at the end of this, when we post it, we should be able to see that here. Okay, so here there is another runtime error, which is because I think, yeah, so torch vision is also missing. So I have to modify my requirements.txt by adding torch vision. So whichever modules this code is supposed to have access to, we should add all of that in the requirements.txt. So torch is needed, torch vision is needed, maybe Gradio is needed, maybe NumPy is needed. So I have to check which all Python libraries I need to add in the requirements.txt, and then it will work. I was facing the same error before hosting this. And once you host it, it should be a publicly accessible link like this. So this link, when I paste it in the chat, hopefully this should be accessible to you publicly. I think I hosted this publicly only, not privately. And this is what the application will look like. So you can go to internet. So go to internet and search any concrete track image and find any random image. Just download it. So save image as, and then go to our app, click to upload this downloaded image. Yeah, this one, I think. And if you submit this, our UNet pre-trained model, which is hosted on Hugging Face, will perform the inference. And after inference, you see it is showing us the segmented region. So it's amazing. I mean, it's a very good model. The only thing is all the images are looking like either black or white. But this will also work, I think, for pipes in which there are cracks. So one of the companies that I'm very familiar with, their business model was partnering with big industries like oil and gas industries and passing like small drones through their pipes. And these drones will image the insides of the pipes, and then it will detect cracks or any defects that are there in those pipelines and will give us feedback. So there are many ways in which this feedback can be collected, but visual feedback is one of them. So there are very interesting industrial use cases for detecting defects or cracks in these massive installations. So with that, we can wind up today's lecture. So please work on the assignment. I think it will be a very good exercise for you to build it yourself rather than just watching me build it. And please, once you submit the assignment, just post your Gradio link on the Discord also, so others can try out your app. It'll be cool, right? And if you can build any other app for other than aerial images, maybe let's say for natural images like outdoor images, segmentation, because you can train this on any data set, on Coco data set or any data set. So it'll be great if you can train this on data set, post it as a Gradio, Hugging Face space link, and others can work on it, right? So thank you so much. We will meet again. Oh, so there is one update which I want to share with you. So next week, I'm traveling for 2 weddings. So there is a small chance that we won't be able to host the lecture next week. So the next module is supposed to be YOLO. So we'll have to push it by 1 week. So there are 2 more modules remaining, 4 more lectures, 2 lectures on YOLO, 2 lectures on Roboflow, on how to create pipelines. So in Roboflow, I'm planning something interesting where all of us can together work on annotating a data set, creating an actual industry use case solution. So, but there we will most likely use YOLO. So I have to first cover YOLO before covering Roboflow. So I'll communicate this through email to all of you, plus also on Discord. So please just notice that there is a small chance that next week we won't have lectures. So thank you so much. We will meet again whenever next lecture will happen. I will keep you all posted. So thank you so much. If you have any doubts, just post it in the Discord. See you. Bye. Thank you. Welcome back to a new lecture. Today we'll be having an introduction to YOLO. YOLO stands for You Only Look Once. Personally, for me, it's one of my favorite models for object detection. In this computer vision bootcamp in the past, we have already covered few models, including RCNN, variants of RCNN. And we have discussed about object detection versus instance segmentation versus semantic segmentation. So we had implemented segmentation using UNet. YOLO is very different. It's, in my opinion, a much simpler architecture, and it can process objects in real time, almost real time, and at pretty good accuracy. We had, if you remember, implemented YOLO in one of the earlier lectures where we were trying to implement OpenCV, but we had implemented a YOLO V8 pre-trained model, nano model, right? So today what we'll be doing is we'll be going into the depth of theory of how exactly YOLO works and how can we implement it for a specific application. So what do we mean by real-time object detection? So if we have 24 to 30 frames per second, if whatever model we have is able to process around these many frames in every single second and detect the objects in those frames, we can call them as kind of real-time object detection models. And different versions of YOLO exist. The version which we had used was the version 8, V8. Today, we'll be discussing about the structure of the original YOLO architecture, right? So, of course, there are variations in the YOLO model architecture itself. There are some models which cannot process 24 to 30 frames. They can only process like 15 frames per second. But there are models which can process, I think, around 155 frames per second. So these are models which can do real-time object detection. And it can be used for video surveillance. You may have seen videos from different companies on physical security systems on the internet, where they detect if people are coming and sleeping at a private property where they are not supposed to enter, and giving real-time feedback to a computer system and some speakers making sounds. You can use part of YOLO for self-driving car. Of course, YOLO is not the only thing that is going on in a self-driving car. We all know that, but YOLO can be used for some basic object detection and annotation. And during pandemic, there were news articles that I had read where people had implemented real-time crowd monitoring system, which primarily work based on YOLO. There are certain limitations also for YOLO when it comes to detecting a lot of people in a crowded image or in a crowded frame. We will also discuss that in today's lecture. So one of the questions that you may naturally have is, here we say you only look once. So does it mean that other architectures are looking more than once in the image? Yes, they are. And we will also briefly touch upon that, which we had discussed earlier in the RCNN lectures. So the basic objective of YOLO is annotating objects in an image with these things called as bounding rectangles. So these bounding rectangles give you a localized position of the image in position of the object inside the entire image. The object themselves will have class, person class, dog class, horse class, and there will be a confidence score associated with it. So how exactly does YOLO construct this rectangle? How does it decide whether something is a person or a dog or a horse? How exactly does it construct the confidence score? We will go through that also in detail. So the original YOLO paper, I would say it's a legendary paper. It's been cited more than 65,000 times now. And the first author of the paper is this person, Joseph Redmond. And this paper, I would say, has entirely transformed the way in which object detection has been implemented ever since YOLO was introduced. Now, there are even more modern versions of YOLO. We have YOLO V11. I think V12 also has come out, but there are no official papers associated with some of the latest YOLO models. But there is a company called Ultralytics, which we had briefly discussed in one of the earlier lectures. So this company has many different pre-trained YOLO models, which you can use for object detection. And I'm sure there are other unofficial models of YOLO, which are pre-trained on various annotated image classes. Now, this table just shows you how the speed of the YOLO and accuracy of YOLO compares with some of the other models. So first, let us look at these two things, MAP and FPS. FPS is simply frames per second. How many frames in a video can this particular model process in 1 second? So if FPS is anything greater than, I would say, 24, you can call them as real time. So all of these models, which are denoted as less than real time, have a frames per second, typically less than 24. So all of these are smaller frames per second models. And all of these models, which are listed here, have higher frames per second processing capability. MAP stands for mean average precision. You might wonder, if the word average is there, why do we need mean? So average precision is nothing but the precision which you get for different recall values. So I don't want to go into the details of MAP. I'm just saying this in 2 sentences for anybody who's curious. So you can calculate precision of your model at different recall values, and you can take an average of that.
that is the average precision called as AP. And if you have multiple classes in an image, like dog, cat, horse, person, you can take the mean of the average precision for all the different classes, and that value is called mean average precision, or MAP. And this is a number which indicates how good your model is in detecting various objects on average at a good accuracy. So you can see that YOLO has pretty good accuracy, 63.4. This screenshot I took from the original YOLO paper. You can also compare it against some other models. So here you can see that RCNN, fast RCNN, faster RCNN, these are the models which we discussed earlier. And you will see that fast RCNN and faster RCNN have, in fact, better accuracy, slightly better accuracy compared to YOLO, but they are both extremely slow. You can see that they can only process 0.5 or 7 frames per second. So the main advantage of YOLO is that you get almost real-time speed in processing without compromising too much on the accuracy. So just keep this in mind. Like when somebody thinks about the use case of YOLO, this is the use case. You need speed without compromising too much on the accuracy. So before implementing YOLO, which stands for you only look once, people were looking not once, but more than once, right? How exactly was that? So there were two different types of techniques. The most primitive technique is using something called as sliding window detectors. So let's say we have a person and our goal is to build a detector or a filter which can identify people in a photo, right? Humans in a photo. What we can do is we can construct different type of filters, which when we plot in the form of an image can look at various abstractions of the shape of a person. And by moving this filter across an entire area of an image, you can highlight certain regions where you have very high probability of the presence or absence of a person. And this is one way in which in olden days, people were constructing handcrafted these feature maps for extracting the localized regions where you would find a person, or you would find a cat, or you would find some other object. And obviously, this does not involve any deep learning. This is not a deep learning based technique. This is more like a hand engineered technique. But RCNN, which we have discussed in detail in the past lectures, is very different. So I'll just remind you, in RCNN, or let's take the example of faster RCNN. What we do is one of the neural networks in this entire architecture, so this RPN, which is called as region proposal network, will propose around 300 rectangles. So 300 rectangles could be like, one could be here, one could be here. It will propose different rectangles as proposed regions where you might find the image. Now, the purpose of RCNN, faster RCNN model is to classify these rectangles such that finally it may predict 1 or 2 or 3 rectangles or a few number of rectangles, which may enclose this car object inside the rectangle. And it will also classify the object that is present inside the rectangle, which is the bounding box. So if the class is a car, it will show that it's a car. If it's a dog, it will show that it's a dog. But you can already see why this is not looking only once. This is looking at the image multiple times. How? Because every single sub-rectangle inside this region proposal network output, each of them have to be inspected separately. So if there are 300 such rectangles, which is the approximate number of rectangles that are proposed by this RPN, you are effectively looking at a subsection of the image 300 times. Similarly, in RCNN, you were looking at around 2000 such proposed regions. So 2000 rectangles will be proposed. Each of them will be of different aspect ratio and different dimension. But you are effectively looking at the image, not the entire image though, the different parts of the image, you are effectively looking at 2000 times. So this entire process of object detection does not happen in one single forward pass. You need multiple iterations to go through different proposed regions to finally identify whichever region is the best one. So this was how RCNN was working. But in YOLO, as the name suggests, you are going to look at the image only once, meaning just one forward pass is enough. Okay, this is the basic idea of YOLO. Now, before we come to the actual architecture of YOLO, I would want to ask you a question. If we were to design YOLO, what would we think about, right? So firstly, the idea behind YOLO is very simple. You have input image. You have some kind of neural network architecture in between. And the output is these annotations, these bounding boxes with the class name and the confidence score. And if you look at the timeline, the deformable parts model was one of the filter-based models. Like it was something similar to this, something similar to sliding window detectors. And that model was introduced in 2018. Then the RCNN-based model, RCNN, faster RCNN, all came in the span of 2 years, from 2014 to 15. So till that point, there were no models that were looking at the image only once. They were all looking at the image multiple times, either in the form of a sliding window or in the form of a proposed region from the region proposal network. But YOLO, which was also introduced in 2015, changed this. Now, let's take a step back. I will discuss the CNN, the neural network architecture used in YOLO a bit later. So I'll come back to this image a little bit later. Now, let me ask you a question. If we were to implement the idea of looking at the image only once, what would we be doing? Just think about what is the input and what is the output. What is the input that goes into whatever neural network we develop? So let's say we are developing a brand new looking at once model. Okay. So we just want one forward pass to be implemented. And in that one forward pass, this is after training I'm talking about. I'm not talking about during the training. I'm talking about inferencing. During the inference, I will implement just one forward pass. In that forward pass, I need to get the output. So let's think about this. What exactly is the input? And what exactly is the output? Can you comment? What is the input and what is the output? It's a fairly simple question. No trick. Just input is image, right? Obviously, image of a consistent size. And output is whatever is the bounding box, the class corresponding to that bounding box, and the confidence score, correct? So input is simply the image. And I would say output is bounding box parameters. When I say parameters, it's height, width, location, etc. And the class, everything. Now, usually, and let's also think about the other problem which all of us are familiar with. We know the image classification problem. If we want to classify this whole image as a cat or dog image, what would be the input? Input will again be the image. Okay. Input is image. And let's say it's a binary classification. In that case, what is the output? If this was an image classification problem of two classes, dog versus cat classification, in that case, what does the output look like? So I don't want a qualitative description. I want a mathematical description. Mathematically, what does this output look like? It kind of looks like this, right? So there will be two numbers. And if this is 0.1 and this is 0.9, this will correspond to, let's say, cat, and this is corresponding to dog. So output is probability distribution, showing the probability for the output to be all of these present classes. So if we input a dog image, maybe the output will look like 0.1%. It's a, 10% it's a cat, 90% it's a dog. So this is like the softmax probability distribution. So output essentially looks like a vector with of length 2, correct? So we know that, and for this, what kind of network do we use? We simply use a convolutional neural network, and something that many of us are familiar with. So if we have an input image, if we have a CNN, we can predict a vector, and this vector, or when I say vector, I simply mean just something with one dimension, but length is 2. And this vector denotes whether something is highly likely a cat or something is highly likely a dog. Similarly, can you guys imagine this output, right, in our object segmentation problem, object detection problem? What kind of vector can we imagine? Let's say for simplicity, I have only one object in my image. So in all the images, either I have one dog or one cat. So input is this, output is this bounding box. So if I were to represent this output as a vector, what are the different things I need inside this vector? So Jayadeep has mentioned X, Y, W, and height. What are those X, Y, W? Can anyone expand? What do you mean by X, Y, W, H? So firstly, we can have some type of coordinates of the box. The coordinates could be the coordinates of this corner. It could be the coordinates of the center, right? But we need an XY coordinate. So let's say X we need, Y also we need. We also need to know the width and height of the box, correct? So we need to get the width of the box as the output. We need the height of the box as the output. Is this enough? Do we need anything else? This is simply the box coordinate. We don't know the class yet. So maybe we need a probability for a dog, probability for cat. So how many ever number of classes are there? We need those to be displayed here, right? So let me just delete this. I'll redraw this. So we need a probability distribution. Anything else? We also need one more parameter, which will be useful in case there is no object present in the image. What if there is neither cat nor dog? What if it's just a background? Then we have to have a score or a number that denotes the fact that some object exists inside this box, right? So something like I would say, probability for object to be present, POBJ. This can be thought of like a confidence score. But basically, if there is neither cat nor dog, if it's like a, let's say, if it's like a background, then the value of this can be 0, right? Otherwise, if there is some object present, irrespective of cat or dog, the value of this can be 1. And now let's say the coordinate of the center point is, let's say 120, 120. Then the value of X will be 120. Value of Y will be 120. Width will be whatever is the width of this. Let's say it is 150. Height is 150, right? Then probability for this to be dog, it can look like 0.95. And cat will be 0.05, something like this. So at the end of the day, what we are predicting or what we are trying to predict is simply a vector with some number of parameters. Now, what is this vector compared against? This vector is compared against some ground truth vector, correct? So a ground truth can look like if the image actually contains, let's say, an object, then this value will be 1. If the actual center of the bounding box is 115, if the actual center Y coordinate is 115, if actual width of the bounding box is, let's say, 175, if actual height is 145, and if the actual class is dog, this will be 1 and this will be 0. So this is the prediction. And prediction, which we usually denote as Y cap. And this is the ground truth, GT, ground truth equal to Y, right? Then we construct some kind of loss function by comparing how close the prediction is compared to the reality. And this loss, the value of this loss is what we use for performing back propagation, so that the weights and biases of our convolutional neural network changes, right? This is one of the simple ways to, so X and Y can denote anything, doesn't matter. So it depends on our convention. In some cases, like in one of the OpenCV lectures, which we conducted earlier, X and Y was this corner and height was this, width was this. But if we denote by saying X and Y is the center instead of the corner, we can do that. So it depends on the rest of the logic, right? If the entire logic is written as if treating the XY as the corner, it can be like that. If it's about the center, it can be like that. According to the algorithm that we are discussing right now. Right now, we are not discussing YOLO yet. Right now, we are simply discussing if we were to construct something that looks at the image only once, which is technically YOLO, you look only once, then this can be that algorithm where our input is an image. In between, you have a CNN, convolutional neural network, right? With convolution filters, and output looks like this vector. And this vector is compared against the ground truth. And it constructs some loss, and that loss is tried to be minimized for you to have a very good prediction of the bounding box as well as objectness score. So this can be called as the objectness score, the class probabilities, and what else? The 4 parameters that you require for the bounding box, X, Y, width, and height. But this simple logic that we just discussed has a problem. The problem is this. What if I had, let's say, 2 dogs in one image? Something that looks like this. What if my image looked like this? Either 1 cat and 1 dog, or I had 2 dogs. In that case, what should we do with this output vector? What should the dimension of the output vector be? Currently, the dimension is nothing but 1, 2, 3, 4, 5, 6, 7. This is 7 by 1, right? My current dimension is 7 by 1, where only one object is being tracked at once. What if I had 2 objects? What could be the dimension? There could be multiple columns. Yes, that's one approach. So what if I have 15 objects? Then I need something like 7 by 15. I might construct something like this. So the first column corresponds to the first object that being tracked. So here I'm saying from this image, maximum I'll track only 15 objects. And for each object, I will tell what is the objectness score. I will give you the rectangle coordinates. I'll give you the class probability distribution, right? And what if there are suddenly another class called horse? So what do we do? Maybe we'll have to then expand the size of this column itself. Maybe we'll have to add one more set of these numbers which correspond to a bounding rectangle for that particular class. So it's very tricky to think about because we have no guarantee that our image will have only 1 object, 2 objects, 300 objects, that too of different classes. So the main issue with this simple approach, which will of course work if we have just one image, and in each image, in each image we have 1 object, and that too of one particular class, then it will work. If that's the case, it will work. And we can all try to develop this. Maybe I'll give that as an assignment. It's very easy to do. Use a pre-trained, maybe ImageNet or AlexNet or any CNN, and use that CNN to make this kind of a prediction. And input could be annotated boxes. Input could be the images. The ground truth is boxes with the known annotations. And then we can easily construct a neural network which can identify 1 object at a time. But in YOLO, we do something different. And why do we introduce the YOLO architecture? To solve the problem of the above simple model. The problem of above simple model is that if there are multiple objects in an image, it's a problem. There is no standardization with respect to the dimensions. If there are multiple classes in an image, that is also a problem, right? Multiple meaning more than the number of defined classes. What if there is another 3rd class? What if another 4th class? So are we going to then define a gigantic output matrix that says, okay, maximum I can detect 5 classes and 15 objects? Are we going to do that? Because if that's what we are doing, then in cases where there are only few objects, we are wasting a lot of, it's a lot of wasted computation. So in YOLO, we try to very smartly take care of these issues. Now, any problem in deep learning, we can think about this problem or the architecture in just thinking 5 things. What is the input? What is the architecture of the neural network? What is the output? What is the ground truth? And what is the loss? If anybody is explaining you about a deep learning architecture, the easiest thing to check whether they understand what they are talking about or not is to ask them simple questions. can you explain me what exactly is the input? Can you explain me what exactly is the loss function here? If they cannot answer what are these 5 things, they probably don't understand the problem well enough, right? So today what we are going to be focusing on while learning YOLO is 5 things that concerns the YOLO. How exactly does the input look like? How exactly does the CNN backbone of YOLO look like? What exactly does the output look like? Is it like that 7x1 vector, or is it slightly different? In YOLO, what exactly is the ground truth? Is it 7x1 vector, or is it different? And in the loss function, what exactly are we going to do? Because we know that in classification problems, the loss function is simply cross entropy loss. Are we going to use that, or is it something else? Once you know the answer to these 5 questions, you can confidently say you fully understand the YOLO architecture, right? So let's go step by step. So firstly, the main idea in YOLO is that you divide the image into certain number of grids. So here it's an S by S grid. This screenshot I took from the original 2015 YOLO paper. And here they have divided the image into a grid of 7x7. So there are 7 grid cells along the height and 7 grid cells along the width. Then you treat every single grid cell. You perform certain calculation for every single grid cell. However, it's not done sequentially. It's all done at once. And I'll tell you exactly how, because otherwise it wouldn't be YOLO, right? If you are doing it sequentially, it will be like as if you are looking at different proposed regions in the region proposal network. In that case, there won't be much difference between YOLO and RCNN. Here, now focus on every individual cell. When I say grid cell, this is what I mean. This is an example of a grid cell, one cell. For every cell, we predict 2 things. One is we predict something called as the class probability. So what do I mean by that? Let's say in this image, we are interested in only 3 objects, dog, bike, and car. Then every grid cell will have a probability distribution to be a bike or to be a car. And of course, the 4th case is the background, but let's not talk about it, right? So every grid cell has a class probability. Similarly, every grid cell also generates the bounding boxes that can bound the object of interest plus a confidence score, right? I understand that I have to repeat what I just said, but I will do that. So to repeat once again, an image is divided into grid cells. So in the original paper, they divided into grid cells of 7x7. So there are totally 49 grid cells per image. And every grid cell makes two types of predictions. One is the class probability. So let's take this grid cell as an example. This grid cell will have something like P class equal to P dog, comma, P bike, comma, P, this is car, P car. That's it. Background is not needed. And for the same grid cell, we will have one more thing, which is the coordinates of the rectangle. So we will have X coordinate, Y coordinate, then width, height, confidence score. So this we can call as bounding box coordinates. Okay. These things are predicted. Now there are some nuances here, like instead of width, we are taking the square root of width. Instead of height, we are taking the square root of height. But I'll come to that. For simplicity, let's say for every single grid cell, these 2 things are predicted. Okay. And finally, only using this prediction, we will be able to construct the bounding boxes, which also I will explain how. But just understand this, for every single grid cell of the 49 grid cells, we are predicting 2 things, the class probability distribution and the bounding box parameters. Okay. There is no constraint that for every grid cell, you can only predict 1 bounding box. No, you can predict multiple bounding boxes. So if I were to draw a prediction, so if I'm considering this grid cell, let's say I'm considering this grid cell for now. then I will have a bounding box prediction, which may predict that, okay, here is a bounding box that encloses like a dog with a confidence score of 0.1. So for this bounding box, this grid cell will predict the center of the bounding box. It will predict the height of the bounding box. It will predict the width of the bounding box. Now, the bounding box itself can have a height and width greater than the size of the grid cell itself. So I will repeat this once I come to the part where I explain how exactly this calculation is done. So just one more point I want you to remember. If there are 3 objects in an image, there are only 3 grid cells responsible for taking care of the bounding box for that particular object. So if this is a dog, and let's say this is the ground truth bounding box for the dog, okay? And let's say this is the bike, and this is the bounding box, ground truth bounding box for bike. And let's say this is the ground truth bounding box for the car. Now, this bounding box for the car has a center. That center is here. This bounding box for the dog has a center. That is here. Similarly, the bounding box for the bike has a center. That is, let's say, here. Now, the way YOLO treats this distribution is such that this particular grid cell, is entirely responsible for identifying dog. This grid cell, where the center of the rectangle enclosing the bike is, this is entirely responsible for identifying the bike. And this grid cell, which has the center of this particular rectangle that encloses the car, is entirely responsible for recognizing the car. For rest of the grid cells, it is assumed that, or it is the way YOLO works is, for the rest of the grid cells, there are no objects. Although you know that there is a bike in this grid cell, there is part of bike in this grid cell, there is part of bike in this grid cell. So you know that visually, the bike is not just confined to one grid cell. Bike, in fact, is spanning over maybe 25 grid cells. But the way the YOLO algorithm works, which I will show you in a moment, is such that every object has only one grid cell responsible for it. Because at the end of the day, you don't care about identifying every single grid cell that the object is spanning. You only care about finding the bounding box, right? So now let's discuss how the center is detected. Some questions you have asked: how is the center detected? How are the bounding boxes drawn? We'll get to that, right? So firstly, let's discuss about an individual grid cell output. So this is the individual grid cell. And as I said, there are 2 types of outputs. One is the probability distribution for classes. So here, if dog, bike, and car are the classes, we will have P of dog, P of bike, and P of car. If there are n number of classes that we are considering, n type of objects, then we will have probability for it to be class 1, like that up to class n. So this is the class probability, which is the first output from every grid cell. The second output is the bounding box prediction. So here you can see that there is x1, y1, square root of w1, square root of height 1, confidence 1. But then you have a version 2, a version b. What is this? This is simply showing the fact that every grid cell can not just predict one bounding box, it can predict more than one bounding box. What do I mean by that? This grid cell may make a prediction that, hey, here is a bounding box that bounds like a cat. Then the same grid cell can make one more prediction that, hey, here is another bounding box that bounds another cat. So you can have the same grid cell make prediction of more than one bounding boxes. So to be exact, in the YOLO 2015 paper, the number of bounding boxes predicted per grid cell was 2. It was not 10, it was not 1, it was 2. So every grid cell was responsible for making the prediction of 2 bounding boxes. Now, whether that bounding box has an object inside or not needs to be decided based on what are the numbers inside those vectors, right? So the reason why we enable the grid cell to predict multiple bounding boxes is that so that you can detect more than one object. What do I mean by that? In crowded place, so let's say there is a photo of people in a crowd like this, right? So if you have an image like this, it is very likely that in some of the grid cells, so let's say there is a grid cell over here, right? It's very likely that there is not just one person in that grid cell, maybe there are two people inside that grid cell. It depends on how crowded your image is. So the more the number of bounding boxes each grid cell predicts, the more the number of objects each grid cell can detect. So obviously now you might think that, okay, one way to prevent this problem is just predict one bounding box per grid cell, but make the size of the grid cell small. So instead of having 7 by 7 grid cells, what if I had 14 by 14? So that you have 4 times more number of grid cells, so that you have very small grid cell, which reduces the probability of the head of 2 people fitting inside one grid cell, right? It can be done, but it'll slow down the process because now you have more grid cells to make predictions on. But the original YOLO architecture allowed predicting 2 bounding boxes per grid cell. So the size of the vector that each grid cell is predicting is what? I'm not going to show you this. Let's just write down the size. So each grid cell is predicting some type of vector V, and how many parameters this vector has. The first 3 parameters are the classes. In our case, we have 3 classes, right? Dog, bike, and car. So that will contribute to 3. So if n is the number of classes, n classes mean there will be n parameters in this vector. If there are 3, if n equal to 3, there will be 3. What about the rest of the parameters? There is a confidence score. I mean, we can write it in the order. There is x coordinate, y coordinate, square root of the width, square root of the height, and confidence score. So how many parameters are this? These are 5 parameters, correct? And what if I allow my grid cell, each of my grid cell, to predict b number of bounding boxes per grid cell, which means like this, there will be b items. So 5 by b. So 5 times b plus these 3 class probability distribution plus n. So my total number of parameters coming out from each grid cell will be 5 times b plus n, where n is the number of classes, 5 is the total number of parameters each grid cell, I mean number of parameters per bounding box per grid cell, where x, y, square root of width, square root of height, and confidence score, right? That is this 5. And b is total number of bounding boxes predicted per grid cell. The number b was 2 in the case of the original 2015 YOLO paper, right? So these many parameters will be output from each bounding box. Like that, how many bounding boxes are there? Sorry, not bounding box, from each grid cell. Like that, how many grid cells are there? We have 7 multiplied by 7, 49 grid cells are there. So this whole thing can be multiplied by 49. Yes. So classes are classes. There is a question. Can you tell what is the classes again? Classes are the category of objects present in our image. So let's say my training data consists of 20 different classes. The class person, dog, cat, mug, mobile phone, bicycle, car, truck, tree, etc., like that, up to 20. Let's say I am training my algorithm so that it can detect up to 20 different types of objects. Then the total number of classes that I have in my algorithm is 20. So that is the classes, okay? So in that case, the length of this will be 20. But here for simplicity, I'm just saying I'm only training my algorithm to detect 3 classes, right? So now B is every grid cell. So I hope all of you understand this thing, right? This P is simply in my current grid cell that I'm looking at, how does the class distribution look like? It can look something like this. I have drawn a plot here. It can look something like this. For one grid cell, the class distribution can look like, okay, it has a high probability for it to be a dog. low probability for it to be a bike and low probability for it to be a car. So this is the class probability distribution, right? For one grid cell. Similarly, and that is the vector that is shown here. I mean, vector or whatever you want to call this array that is shown here. But that same grid cell is also making one more prediction, a prediction about the bounding box location. Bounding box location for how many bounding boxes? For B bounding boxes, not for one bounding box, for B number of bounding boxes. So in the original YOLO paper, the value of B was 2, which means every grid cell like this yellow is a grid cell, will predict the locations of 2 bounding boxes. So let's say this green bounding box is the first one, this is the another one. Similarly, this grid cell, I can just copy paste this here. This grid cell will also make a prediction of 2 bounding boxes. So it may look like this. Maybe it will say that, hey, I have 1 bounding box here, another bounding box here. Similarly, the grid cell here will also make a prediction of 2 bounding boxes. Like that, there are 49 grid cells, which each of them will predict 2 bounding boxes. So totally there will be 49 multiplied by 2, that many bounding boxes being predicted. Now, obviously, you don't need that many bounding boxes. You know that only 3 bounding boxes are needed, right? One for the dog, one for the bike, and one for the car. So obviously, all these predictions are not being used. But this is how the YOLO algorithm works. You can also confine. Yes. So now there is a question: how can B box be drawn using the grid cell? Very, very good question. We are coming to that next. Excellent question. So I hope you understand. I'll come to the architecture in a bit because let's pause the architecture for a moment. It's anyway simple, but I just want to make sure that you understand how the output vector looks like. So I hope you understand this first part. First part is output class probability. There are 3 classes, which means there will be 3 probability values. If there are 20 classes, there will be 20 probability values. So I hope this part is straightforward. Now let's look at the second part. How do we predict X coordinate, Y coordinate, bounding box width, bounding box height, and confidence score? So let's keep the confidence score in the back pocket for a moment. Let's just focus on these 4 things. How do we predict X coordinate, Y coordinate, bounding box width, and bounding box height? Very simple. Exactly like how we predict softmax probability score in a normal CNN. So how do we perform image classification? We have an image, okay? Let's say image of a person. This passes through a CNN, right? And this predicts some kind of output, which can look like minus 3.5. And let's say there is one more class. So this is a 3-class classification, let's say. Person versus animal versus object. 3-class classification. Then you will get some numbers like this, 1.2. And then what do? These numbers you pass through softmax to get a probability distribution. It may look like 0.99. This will be, let's say, 0.001. Let's say this is 0.009, whatever. So some of these 3 should be equal to 1. So how do you go from this image to these numbers? You go with the help of a CNN that is trained. Exactly like that. In this case, you again have an image. Inside the image, there could be person, there could be multiple objects, but you go through a CNN and you predict some other set of numbers. Now, this time, what are these numbers? These numbers correspond to our, it will look like a tensor which handles all the bounding boxes predicted by all the grid cells. So how many will be there? We'll have 49 grid cells. So that many we need. For each grid cell, we are predicting 2 bounding boxes. So multiplied by 2. And for each bounding box, we have 5 parameters, X, Y, width, height, confidence score. So multiplied by 5. But we also have class probability for each bounding boxes, correct? So we will have plus, let's say there are 3 classes, person, animal, object, then 3. So this can look like this output it won't look like one single vector. It can look like a tensor with how many dimensions? I would say 3 dimensions. So, but it'll have total these many numbers, 49 multiplied by 13, whatever that number is. This vector, final output vector, will have, sorry, I don't want to keep using the word vector. The final output will have these many numbers present in it, right? And this, on one hand, was representing what? The output probability distribution for different animals, right? I mean, animal or object or person, right? So if this was a poorly trained neural network, what will this predict? This will make some random prediction, and maybe it may initially predict that, oh, this is very unlikely that this image is a person. It's actually an animal. So maybe this value is very high. This is 0.991, but other two numbers are very small. It can happen. But then the error will be very high. Why is the error very high? Because the ground truth will look like 1, 0, 0. So there is huge difference between ground truth and prediction, which means there will be a huge change happening to the weights and biases of the CNN. And that will make sure that you are slowly, during the gradient descent, moving these numbers closer and closer and closer to ground truth. Exactly like that, here in this case, we don't need so many number of bounding boxes. We just need 3 bounding boxes. What that means is the confidence score, right, associated with all bounding boxes except 3 bounding boxes should ideally be very, very small. Like if there is a bounding box associated with this grid cell, which looks something like this, then whatever that bounding box coordinates are, the confidence associated with that bounding box should be as close to 0 as possible, because that is how we know that that bounding box is a useless bounding box. We don't need to predict, we don't need to utilize that bounding box to show that there is an object, because it's a low confident bounding box. So ideally, what we want is out of these many 49 multiplied by 2, out of those many bounding boxes that are being predicted, we just need 3 bounding boxes of very high confidence. And ideally, because this image has one object of a dog, one of a bike, and one of a car, we need those 3 bounding boxes to have high class probability, one for dog, another high class probability for bike, another one should have high class probability for car. The rest of the bounding boxes that are predicted, which are present in this giant set of numbers, should have confidence score very close to 0. That's how we will discard it. Right? So before coming to the actual prediction of the confidence score, let's look at how the bounding box X, Y, and width and height will look like. So the values of X, Y, width, and height are always confined to be between 0 and 1. Otherwise, the problem is our individual bounding box predictions will look like this. So let's say inside a bounding box is 0.95. Now, if X coordinate is 500, if our image resolution is very high, X coordinate will look 500 for the center of the bounding box. Y coordinate will be 350. Height might be 600. Then width might be 900. Then probability for dog will be 1 or let's say 0.9. For cat will be 0.1. The problem is in this output, all these numbers are between 0 and 1, but the width, height, and the coordinates are not between 0 and 1. So this is not a good way to arrange numbers in deep learning. It's better you have a standardized or a normalized representation of numbers. So the way we have X, Y, width, and height is such that they are between 0 and 1. So how do we normalize? So let me ask you a question. Any bounding box, how do we normalize the width and height of any given bounding box such that we ensure that the width and height are between 0 and 1? What do we do? Divide by max width and height. And what is the max width and height? Max width and height of what? The answer is correct. Yes, you divide by the max width and height. You divide by the width of the image and width of the height of the image, right? So whatever the actual bounding box width is, you divide that by width of the image, and whatever the actual bounding box height is, you divide that height by the width of the image. And this will ensure that all the predicted bounding boxes have height between 0 and 1 and width XY. how do you normalize XY? So remember, XY are the center coordinates of your bounding box. How do you normalize this such that the number is between 0 and 1? What do you divide this by? Max distance is one of the comments. Can you elaborate what do you mean by max distance? So X and Y are the center coordinates, which are again, obviously, okay, max distance from origin. So X and Y, interestingly, this is how it looks like. So as I told you, there is one grid cell that is responsible for producing the bounding box that bounds the object. So as I said, if there are 3 objects in an image, there are only 3 grid cells who are responsible for creating the bounding boxes. Rest of the grid cells are useless. So the width and height, what you guys mentioned, is perfect. Width and height, you simply divide by the width of the object and width of the height of the image. Sorry, not object. Whatever is the width of the bounding box, you divide that by the width of the image so that you normalize the width. Similarly, you do for height. For X and Y, what you do is, let's say this is the X coordinate. Usually you calculate X coordinate of an image from here. So if this is the point, the actual X coordinate is something like this. This length is the actual X coordinate. Similarly, if this is the center, the actual Y coordinate is something like this, right? But you are calculating the X and Y coordinate with respect to the grid cell, not with respect to the entire image. So what you do is, so let's say the X coordinate predicted is some number, 233. You divide, you take the modulus operator, X mod S, where S is the width of the grid cell, then you divide by S. So please try to think about what exactly does this do. So let's say each grid cell is 50 pixels, right? Let's say the width of the grid cell is 50, height of the grid cell is 50, and let's say this coordinate, this location is around, let's say 67. Then what should be the normalized location of this? First, you have to subtract this guy from it, right? You don't need this. So you just need to calculate this distance. So 67, you divide that by 50 and take the remainder. And that remainder is 67 mod 50. What is the value of 67 mod 50? 17, right? Remainder is 17. But 17 is still not between 0 and 1. So you divide this 17 by the width of the cell itself, which is 50, to get a number. So this will be what? 0.34, right? So this number will be between 0 and 1. So X mod S divided by S. Similarly, Y mod S divided by S. So you basically now have X value between 0 and 1, where X is with respect to this particular grid cell under consideration. Y value also between 0 and 1. The width and height are between 0 and 1, but width and height are normalized with respect to the entire image, not with respect to the grid cell. Okay. So now the prediction made by the neural network will look something like this. There will be a probability for an object. So P object probability or objectness score. Let's say there is an 80% chance that there is an object. Then one more thing I forgot to mention is we are not directly adding width and height here. We are adding square root of width and square root of height. Okay. So just please keep that in mind. So objectness score. Then there is a X coordinate, which could be, let's say 0.1, Y coordinate, let's say 0.1. Then let's say width is 0.7, height is 0.3, and let's say the confidence score is 0.6. So look at all these numbers. All these numbers are between 0 and 1 now. So this is confidence. This is X, normalized X. This is normalized Y. This is square root of width. This is square root of height. So these are now the numbers. So now you can easily back calculate. If somebody needed to back calculate, you can easily back calculate how exactly where exactly the bounding box will look, where exactly will it be. So if I'm looking at this grid cell, if you told me that 0.1 and 0.1 are X and Y, then 0.1 may be somewhere here. 0.1, 0.1 means center will be somewhere here. And then you told me 0.7 and 0.3 are the square root of width and square root of height, which means width equal to 0.49 and height equal to 0.09, correct? Which means width of the bounding box is half of the width of the image. So my width will be roughly this much and height is 10% of that of the image. So this is the center and my bounding box will look something like this. The height is 10% of the height of the image. The width is 50% of the width of the image, roughly. So this is how we can construct bounding box if you have these numbers and if you know which grid cell is responsible for this particular prediction. Now there is an interesting question. There are two interesting questions actually. Why exactly are we taking square root? Excellent question. I'll come to that. There is also one more question. How exactly is the confidence score calculated? So I'll first come to how exactly is the confidence score calculated. Regarding the square root, I'll come to that at the end of the lecture. So now let's ask us the question. So I hope you understand how we get to the x, y, square root of w and square root of height. It is exactly using a neural network. We train the neural network such that predictions will be made such that predictions are these. And now these predictions, if they are matching the ground truth, then you are happy. If they are not matching the ground truth, your loss has to be high. Now, all of us should ask us the question because we have not discussed the loss yet, right? So two questions that we should ask ourselves is how exactly is this confidence score calculated and how exactly is the loss function looking like? So we should ask that question. One thing which I skipped so far, which I will come back to, is how exactly does the neural network look like? But I would say that is lesser of a concern right now because there are different neural network architectures we can put in place or whatever architecture we are going to discuss. But the more important questions are how is confidence calculated, how is loss calculated, and maybe one more interesting question is how is square root, why is square root being introduced? So how do we calculate confidence score? So let's first discuss, before calculating the confidence score, what should be the confidence score? What should be the calculated confidence score? It should be such that the confidence score for only 3 cells should be equal to 1. So the confidence score for this guy should be 1, this guy should be 1, this should be 1, but for every other cell, it should be 0. This is how YOLO works. And the reason why do I say that confidence score for this grid cell is 0? Although this grid cell encloses part of this bike, because only those centroid grid cells are responsible for making the object detection. What do I mean by centroid grid cells? The grid cell in which the centroid of my bounding, the ground truth bounding rectangle is present. So this is the ground truth bounding box rectangle, and the centroid of that rectangle will be somewhere inside this grid cell. Similarly, for bike, if I draw the centroid of that rectangle, I mean, I'm drawing it in a very bad way, but I hope you understand the point. The centroid of that bounding box rectangle will fall somewhere here. Similarly, for the dog, the centroid of this rectangle will fall somewhere inside this grid cell. And because of that reason, only these 3 grid cells will have confidence score of 1 in ground truth. The rest of the grid cells will have confidence score of 0. All right. So now there is a confidence score that we discussed, right? Which is nothing but, okay, let me just discuss one more thing, IOU, which I will have to anyway talk about. So this is something that I discussed earlier. IOU is nothing but intersection over union. So intersection over union is, let's say my ground truth bounding box is this, okay? And my predicted bounding box is something like this. How do I quantify how good this prediction is or how bad this prediction is? For that, we can use this parameter called IOU, intersection over union. So you calculate the area of intersection between the predicted bounding box and actual bounding box. So that is the intersection area. And union area is the total area spanned by the boundary of these shapes combined. So you will not be double counting the intersected area. You will be counting the entire area, this whole area. So in the best case, if your prediction is picture perfect, then your predicted bounding box will be like this. your real bounding box will also be like this. They will intersect, they will overlap exactly on top of each other. And your IOU score will be what? That case, if you have perfect intersection, your IOU will be dash. IOU will be 1 because the intersection area is exactly equal to the union area. What if you have your prediction is really, really bad? Let's say this is the ground truth, this is GT, and this is prediction. In that case, it will be 0 because you have a giant union area, but 0 intersection area. And in between, if you make in between predictions that are partially good, then you will have a number between 0 and 1. So this IOU number is a number that is between 0 less than or equal to IOU less than or equal to 1. Okay. So this IOU is one of the parameters that we consider in constructing the confidence score. So let's go back here. So the value that I am supposed to predict is IOU multiplied by P of object. So P of object is the probability that object is present in that cell. So my ground truth should be such that my neural network will be trained such that ideally this P of object value should be equal to 0 if I am looking at any of these red color cells. And if I am looking at any of these green color cells, the P of object value ideally should be close to 1. And which means the confidence score will be nothing but C equal to IOU multiplied by P, right? And P is a number that is obtained by the trained neural network. And for a green rectangle, this P will be ideally, if the training is done well, this will be close to 1 because there is an object present in this, which means P is supposed to be 1. And what that means is the confidence score is approximately IOU itself, assuming that this P value is given out by a trained CNN. Now confidence equal to IOU. Now IOU of what? IOU of the ground truth with respect to the prediction. So what is the ground truth? This rectangle is the ground truth. And what if my prediction was something like this? What if, let's say, my predicted bounding box is something like this? In that case, my IOU, let's say it's like 0.4 or something like that. And let's say this guy, this probability instead of exactly 1, this is 0.95. And let's say IOU is equal to 0.5. Then my confidence score will be this multiplied by P, which is equal to 0.5 multiplied by 0.95. And what is this? 0.475 or something, right? So this will be the confidence score. Okay, so the confidence score is basically calculated by using two numbers. One is the intersection over union of the bounding rectangle and the ground truth rectangle. And another score called as the objectness score, which is another additional parameter predicted by the neural network. The objectness score is supposed to be 0 for the rectangles shown in red, and it is supposed to be 1 for those rectangles shown in green. And this confidence score is the product of IOU and P. Now, let's try to read this. Now, if you see something like this and something like this for one grid cell. So I told you that yes, there is threshold considered to construct a confidence score. But let me ask you a qualitative question, right? So let's say I told you that I am looking at this grid cell, and for this grid cell, my probability distribution looks like this, and my bounding box parameters look like this. So bounding box parameters are like this, probability is like this. So the way I have to read this is, there is a 0.9, I am 0.9 or 90% confident that there is some object inside this grid cell. That object is enclosed inside a bounding box whose normalized x is this, whose normalized y is this, whose normalized square root of width is this, square root of height is this, and that object is 80% likely to be a dog. It is 10% likely to be a bike, and that it's 10% likely to be a car. So this is how you are supposed to read it. So confidence score simply tells you the objectness. It simply tells you whether there is any object at all or not. If it is close to 0, you don't even take it. If it is close to 1, it means there is some object. And this probability distribution tells you which exact class is that object. So just once again, if you see these numbers, you read it like this. There is a 0.9 probability or 90% chance that the current grid cell that I'm looking at, which is this guy, is responsible for some object. Now, this some object is enclosed inside a bounding box, and that bounding box is present inside this rectangle of normalized x coordinate for the center 0.2, y coordinate 0.4, normalized square root of width 0.8, normalized square root of height 0.6. So obviously that rectangle can look something like this, right? That rectangle is not confined inside the grid cell. It is confined inside the image. And this 90% confident object is 80% likely to be a dog. It's 10% likely to be a car, or 10% likely to be a bike. So this is how we read these set of numbers. All right. So just taking a pause, we discussed what is the input. Input is simply the image. We did not discuss what is the neural network yet, but we just said that it's a CNN. We'll come back to it. So this is the architecture. We discussed the output format, right? Input has just an image. Output has class distribution and bounding box, B-box parameters plus confidence score, right? So there is one question. What if there are 2 dogs in one grid? If there are 2 dogs in one grid, it's not a problem. Why? Because my B value, this guy, is 2 in my original YOLO architecture, this guy. So every bounding box is in fact not just predicting the probability distribution and one of these, it's in fact predicting 2 of those. But for ease of giving an example, I just talked about 1, but there will be 2 of those, right? So if there are 2 dogs in the same grid, there is no problem. But you think about how likely is that there will be two dogs in the same grid cell. If 2 dogs should come in the same grid cell, then there has to be one more dog, maybe very close to this dog, such that the bounding box of that dog, the centroid of the bounding box of that dog, also should fall in the same grid cell. So the likelihood of that is a bit less, because if the dog is even slightly here, then the centroid of that guy will be somewhere here, right? Unless the dogs are standing behind each other or something like that, then this issue won't arise. But yes, of course, to answer your question, if there are 2 dogs, it's not a problem. If there are 3 dogs, yes, then it's a problem, because only the 2 prominent ones will be recognized according to the original YOLO algorithm. The other solution is you increase the number of grids inside each image. So instead of 7 by 7, you make it 49 by 49, right? Or I mean, not 49 by 49, 14 by 14. Then you have 4x number of grids. Then you again further reduce the likelihood of having 2 centroids inside one grid cell. Okay, so we discussed the following items. We discussed the input. We partially discussed the CNN. We discussed the output. There were one more thing. Loss was there. Input CNN. Oh yeah, we discussed the ground truth, not loss. Ground truth GT. We did not discuss the loss. So let's spend a little bit of time on what the loss looks like, because I'm sure you are interested to know how exactly am I penalizing the neural network. So so highest IOU. So if we just want one bounding box out of the 2 predictions, obviously we pick the one with the highest IOU. So that is about it. Okay, here is one question. Okay, I had written this but forgot to mention. I told you that the way confidence score is calculated is like this. It's by multiplying IOU with the P of object, correct? Now, for calculating the IOU, I need the predicted bounding box and the ground truth bounding box. So I compare the predicted and ground truth bounding box to get the IOU. But here is my question. This works during training, but what about during inference? During inference, I don't have the access to the ground truth data, because there is no such thing in inference. So how exactly do we calculate the IOU? Or how exactly do we calculate the confidence? I'll just repeat my question in case it's not clear. So I said that the confidence score is calculated using the product of IOU and objectness score, correct? Now, objectness score is fine, but IOU, for calculating the IOU, you need a ground truth because you have a predicted bounding box, you have an actual bounding box. You compare those two, I mean, you take the intersection and union, then you calculate the IOU. But this is fine during training because during training, you have the training data. But what about during testing or during inference? How do you construct the confidence score? Because you might have seen the YOLO videos where not just the class name is shown, the confidence score is also shown. How exactly is that done? Just think about it for 2 seconds, because I can directly tell you the answer. Basically, so training is like, 80% of the data will be used for training, 20% will be testing. The data set will look something like this for every image. So let's say the image ID is 1, and there could be like a JSON file or CSV sheet, which has a column like image ID, then X, Y, width, height, maybe class name, whatever. And then let's say there is a person in this image and the bounding box is this. Then in the CSV file, it will say image ID is 1, X is whatever, 240, 220, 150, 150, then class is person. And if person is 0, this is how the training data will look like. There will be a CSV file with the annotated, bounding box parameters, and there will be a folder with bunch of images. Now, among the bunch of images, 80% we'll use for training. From the CSV file, those corresponding 80 rows, 80% of the rows we'll use for training. Remaining we'll use for testing. Excuse me. But we don't know. For creating the confidence score, we don't have the ground truth during the inference or during testing. So how exactly do we do that? So the way we do that is, instead of model predicting the P of the objectness score and predicting the bounding box and constructing the IOU. So instead of taking these two things separately, you make the model directly predict a C. And how do you know that the predicted value of C is good by the neural network? You know that because if the model is really good, what should be the value of IOU if you are looking at this particular cell? Let's say you have a very, very good model, okay? And you are currently looking at this particular cell, okay? It predicted some random rectangle. What should be the P of object? Ideally, the predicted P of object, and what should be the IOU for this particular cell? It should be close to 0, because the objectness score, ground truth score for this particular cell is 0. It's a red color cell. There is no object in that. So if the model is really good, and IOU is also 0, because there is no, since there is no object associated with it, there is no IOU calculation also. Because IOU calculation is only when there is a ground truth rectangle associated with it. So the product of these two, ideally, if the training was done properly, will anyway be close to 0, right? So if the neural network can successfully predict that P of object is close to 0 and IOU is close to 0, we can hope that the neural network is already good at predicting the class confidence, not class confidence, the overall confidence, the objectness confidence directly. Similarly, if you were looking at this cell, this grid cell, the IOU, if the training was done properly, IOU will be close to 1. Why? Because whatever bounding box is predicted, it should be very close to the ground truth. So IOU will be close to 1. And objectness, the objectness score will also be close to 1. Right? If the model is trained really well. So the hope is that the confidence score is already something that a well-trained model can directly predict. So during inference, the confidence score is directly predicted by the model. During training, the IOU is calculated. It's not directly predicted. It is calculated using the predicted bounding box. And P of the objectness score is directly predicted. So, and then if you want a class probability, right? Because you might have seen YOLO videos where a human is there, there is a box and it's written that there is a person here, and a confidence score like 0.87 is shown. So this 0.87 is not equal to this C. This 0.87 is C multiplied by P of person. So you know that every grid cell predicts two things, right? P of person, then what? P of, there was dog, and P of whatever. So let's say there are three classes, P of car. If these are the three things that are predicted by each cell, then, and let's say now my bounding box confidence score is equal to 0.9. And let's say my original image is 80% likely to be a person, 10% likely to be a dog, and 10% likely to be a cat. Then the class-wise confidence score is confidence for person equal to 0.9 multiplied by 0.8. This is the class-wise confidence score. This will be 0.72. So this number is what you finally see when you display confidence score in YOLO, because it's the class-wise confidence score. So just to summarize, confidence score during training is the product of IOU and objectness score. But during inference, confidence score is directly output. However, this confidence score is not the class-wise confidence score, it's the objectness confidence score. Now, whether the object is a person or a dog or a car, the confidence score associated with that you get by multiplying the class probability, 0.8 or 0.1 or 0.1, right? So this is how it is done. So basically, confidence score is utilized as a threshold for running. Exactly. So confidence score can be utilized as a threshold for, let's say you decide not to display any bounding boxes with confidence score less than 0.5, you can choose to do so. Now, let's come to the even more interesting part, that is loss function. So how will CNN behave / output differently during training and inference? So that we can, so CNN need not behave differently. We just need to utilize the last layer of the CNN to pick what we need. So if we want objectness score separately, and if there is one last layer where one node is, or let's say there is a layer where there are two nodes and one node is supposed to predict objectness score, another node is supposed to just calculate IOU and output it from the already predicted, bounding box coordinates. We can modify just the final layer and keep the rest of the layers intact so that the weights and biases are not changing. So freeze all the layers and change only the last layer. So that is one thing you can do during inferencing. So this is one way in which even vision language models are constructed. So in vision language model, you have a pre-trained CNN, you have a pre-trained BERT or some NLP model. You just modify the final layer, final classification layer, to get the output in whatever format you want. But the learning of the neural network is present inside the initial entire layers of the neural network. Can you repeat the objectness and P class? Yes. So inside an image, there can be an object, there can be a background, correct? The fact that there is an object present inside a bounding box is represented by the objectness P objectness. Now, whether that object itself is a dog or a horse or a human or some other object out of the 20 objects that you have in your training class is determined by the, it's denoted by the P class. So objectness score, from that point of view, objectness score is always greater than or equal to the class score, because you are 90% confident that there is something inside this bounding box. But you are not fully sure whether this is a human, this is a cat or dog. You are 80%, you think the probability distribution for this is 80:20, 10:10. Then your class confidence score is, for this to be a human, is 72% this is a human. So this will look like 72 is to, this will be 90% multiplied by 10. So let's say 9:9, something like this. So your objectness score, you are very confident that there is some object inside this bounding box, but you are not so confident that it is exactly a human or exactly a animal or an object. But you are 72%, not percentage, 72 out of 72 plus 9 plus 9, you are confident that it's a object, it's a human. Rest, you are sure that it's a animal or it's an object. So objectness score is greater than P class score. Okay. Now let's come to the last thing, loss function, before we implement the architecture. Firstly, for what all things should we penalize our network? We should penalize for making a wrong class prediction, right? A dog should not be predicted as a cat. So this should be penalized, correct? We should penalize for mistake in the bounding box location, correct? So B box location, wrong location should be penalized. What else should be penalized? There is one more thing you should be penalizing. So what I'm trying to say is, to construct the loss function, we have to know when we should penalize the neural network, correct? If a dog is classified as a cat inside a bounding box, it is a problem. So predicting the wrong class is a no-no. So it has to be penalized. Similarly, if I have a bounding box, I mean, if I predict the correct class, I say that, hey, there is a cat here, but the bounding box is 10 pixels off. That has to be penalized, correct? One more thing should be penalized. So IOU, we don't have to directly penalize because IOU is embedded in the bounding box coordinates, correct? Because bounding box coordinate is ultimately, so IOU is a derivative of bounding box coordinate. Center of object is also derivative of coordinate. There is one more thing I think all of you are forgetting. One important thing, confidence score. You should not say that if an actual object is present inside a bounding box, you should not predict a low confidence score. So low confidence, I mean, mistakes in the confidence score should be penalized. Everything else is already ingrained. Your center of centroid is ingrained in the bounding box. Your IOU is already part of the bounding box, because if you know the bounding box, you know IOU. If you know the bounding box, you know the center. If you know bounding box, you know the width and height. Everything else is derivative of that. So these are the three things you need to penalize. And these are the three things that are part of our loss function. So these two are, you know, embedded into one loss parameter, and this is embedded into another loss parameter. So our loss function consists of two losses. One is for mistakes in the class. So mistaking a cat for a dog. So that is this loss for class. And another is localization mistake. So localization meaning whatever mistakes come in the bounding box plus confidence score. Okay, so let's first focus on the class confidence. I mean mistakes happening in the class. So how do we construct a loss for mistakes happening to the class? What is the typical thing that we do? When you have a, let's say I have a person. So person, object, animal. And let's say my ground truth is person. So it's like 1, 0, 0. But instead of this, I predicted 0, 0.9, 0.1. Okay. I made some prediction like this. I have to penalize this. Typically, how do you do this? Typically, you use cross entropy loss in image classification. But here, there is a problem in using cross entropy loss. You have these predictions for many different grid cells, and you only care about that grid cell where you have an object. So there are only 3 grid cells in the example that we picked. There are only 3 grid cells in which there are actually objects. So what you do is you simply, so if you have 3 classes, you simply take a mean squared error kind of error. I mean, you don't take the mean, but squared error. So you do 1 minus 0, the whole square, plus 0 minus 0.9, the whole square, plus 0 minus 0.1, the whole square. But you do this only for those grid cells where centroids are present. So you do this only 3 times in the example that I showed. Only for these 3 grid cell predictions. Where is that? Only for this grid cell, and this grid cell, you calculate this loss. The loss for all other grid cells are 0 because you don't care about the class predictions for those grid cells. You only care because those are anyway grid cells where there is no object. So the loss with respect to the class prediction is calculated only for those grid cells with centroid. In the original paper, the mathematical notation is a bit more complex. Instead of writing in English like this, they have a mathematical notation. But if you ever open that paper and look at the loss, just ignore the first summation. All it is trying to say is you are looking at only at those grid cells. Out of the 49 grid cells, you are looking at only 3 grid cells. Similarly, this localization loss has 2 losses, as I mentioned. It has a penalty for wrong bounding box location. It has a penalty for wrong confidence score prediction. Okay, so let us look at those 2 parameters. So localization loss is the sum of loss in the confidence score, mistakes in the confidence score and mistakes in the coordinates. Now, how do we penalize mistakes in the coordinates? Very simple. There are 4 things which correspond to coordinate: x, y, square root of width, and square root of height. How do we penalize this? If x, the cap is the prediction, and if x is the reality, this minus this square plus this minus this square plus this minus this square plus this minus this square. You can add all these things to get the loss due to a wrong location of your bounding box. Here, the one without the cap is the ground truth. The one with the cap is the prediction. And here also, you only look at those grid cells where there is actually centroid. You don't care about the predictions that are made for the location of the bounding box for other grid cells. Why? Because those grid cells are not responsible for predicting the bounding box. Only the grid cells with the centroids are responsible for prediction. So this number, this loss is only calculated for that. But you also multiply it by a prefactor called lambda. This is typically done when you are adding different type of losses. So if you want to, give more weightage or less weightage to this loss than this loss, you can increase or decrease the value of lambda, right? So that is the loss due to coordinates. Similarly, there is a loss due to mistakes in the confidence. Now, here is the interesting thing. The confidence score, what should be the prediction? So how many cells are there, by the way, where you are predicting the confidence score? There are 49 cells, 7 by 7. There are 49 cells in this example where you are predicting the confidence. What is the ideal predicted value of confidence for this one? For this cell, what is the ideal value that we are hoping to predict for the confidence? 0, right? Because there is no object. It's 0 here, it's 0 here, 0 here, 0 here, 0 here, right? Correct? So out of 49 cells, for 46 of them, confidence score is supposed to be 0. For 3 of them, confidence is supposed to be 1, correct? Now, let's imagine that my CNN is really good at identifying background, meaning cells that are not part of centroid, but it is also really, really bad at recognizing the actual objects. So let's say for all the cells, my confidence score prediction is 0. So for all of these where it is supposed to be 0, it is 0. And for all of these where it is supposed to be 1, also I am predicting 0. Then if you are taking the loss by looking at how many mistakes you are making, only for 3 out of 49, you are actually making a mistake. For 46 out of 49, you are not making a mistake. But that is not because your model is good. That is because you're only considering these cells where centroids are present to be the important ones. So for somehow you should penalize this guy more, correct? Although you are only making 3 mistakes in the confidence score prediction, only in these 3 cells you are making mistake. Remaining 46 cells you are not making mistakes. But you should penalize this guy so much because so many more cells represent background. Only few cells represent the actual object. So you have to give this guy more weightage. So what you can do is you can multiply this by a lambda, let's say lambda object, and this guy with lambda no object. And when I say this guy, I don't mean this 4600, I mean the actual loss. But whatever is the loss associated with the background cells, you multiply it by a lambda for no object. And this number should be a smaller number. This should be a larger number. So the loss will look something like this. So loss will simply be the mean squared error of the value that you are supposed to predict and the value that is the ground truth. The ground truth for the ones with centroids, the confidence score should be equal to 1. Here, the confidence score should be equal to 0. This is the predicted confidence score. The lambda for no object should be, let's say this is 0.1, then this can be the lambda here. I mean, here there is no lambda, but this is 1, right? 1 times this. So just keep this number a small number so that you are accounting for the fact that there are only few cells with objects, but there are large number of cells without objects, right? Now you add all these 3 confidence scores. You add the loss scores. You add the loss due to mistake in confidence. You add the loss due to mistake in the bounding box coordinates. You add the loss due to mistakes in the class prediction. You have the total loss, and your entire goal of this object detection in YOLO is to minimize the sum total of these 3 losses. If you can do that, you have a YOLO. You might have noticed one thing. Here, now if we write this entire loss, it will look like optimizing certain parameters. So here, essentially, object detection is treated as if it's a regression problem. How? You have an input image, it passes through a CNN, and this CNN predicts bunch of numbers, right? Some numbers. And using these numbers, you have a loss formula. And that loss formula is this guy plus this guy plus this guy. And your objective is minimizing whatever that the sum of this is. So effectively, you are it's essentially treating this object detection as a simple regression problem. So this is finally the loss part, which is the 5th part of the YOLO architecture. So we covered input, output, ground truth, loss. Now CNN architecture, we don't need to spend too much time, but I'll just show you how the architecture looks like. So the architecture looks like this. Your input image is 448 by 448 by 3. So this is the height and width. 3 is the number of channels. You have RGB. And the transformation happens in the form of CNN, like the CNN filters passing through this. So you can see that the number of channels are increasing in the subsequent layers. So, but the XY dimension is decreasing, and this represents fully connected layers. And finally, at the output, you will have the parameters that are predicted, and you will have 7 by 7 grids. So you have 49 grids, and for every single grid point, you are predicting the parameters corresponding to the confidence, bounding box position, and the class probability. So this is the architecture. This architecture can be replaced with many other different types of CNNs, which is what YOLO, different other versions of YOLO tried. So the second version of YOLO had a different architecture. The next version had a different architecture, but the basic principle remains the same. Now let's implement the YOLO. But before that, one last thing is let's discuss the summary of, summary of the limitations of YOLO. So as I said, in this case, you are predicting 2 bounding boxes per grid cell, correct? But only one class is possible. So if in the same grid cell, if there is a person and a dog, so for example, if I'm dividing the image into grid cells like this, in this grid cell, the YOLO can detect 2 people, but not more than 2. The original YOLO, not the modern ones. And the original YOLO could not detect 2 different objects inside the same grid cell. So that was a problem. And this is the problem mainly when you have crowded images. If it's sparse images, then it's not a problem. Another problem is this aspect ratio. So in one of the lectures I had shown, like I took a mobile phone, and if I orient the phone like this, it can detect. But if I orient it like this, then it's like a weird aspect ratio, right? Then it was getting detected as a pen. I mean, it looks like a pen even for humans, right? So, but for the same objects, if aspect ratio is different, it's a problem in YOLO. Then the 4th issue is where I answer the question one of you asked earlier: why are we taking square root of width and square root of height? So the idea is this. Let's say I have a bounding box that recognizes a person where the person is over here, and another bounding box where I have a person over here. Let's say in both of these cases, the bounding box, I make a mistake of 5 pixels along the width and 5 pixels along the height. In which case is this mistake more of a problem? In the big bounding box or in the small bounding box? It's a mistake. It's a problem in the small bounding box, because if I move this bounding box, if I move this green bounding box even by 5 pixels here, then I'm not binding this person anymore. it might move out of the object, right? I mean, it might not enclose the object anymore. So for small objects, if we have small bounding boxes, those bounding box, the mistakes in those bounding boxes need to be penalized a bit more harshly. Why? Because mistakes in those means you probably won't be enclosing it altogether. If you are analyzing a football game, right? And the football might be small, the people might be big. So you're okay with small mistakes in the people bounding box, but you are not so okay with the bounding box corresponding to the football. So how do we do this, right? Check this example. So let's say you have a small bounding box whose width is 20 and but the prediction is 25. So it's like 5 pixels off. In another case, you have a large bounding box where actual width is 200, but prediction is 205, the width. So here also the mistake is only 5 pixels. So if you are taking the direct difference in squares, look at the error. 20 minus 25 the whole square is equal to minus 5 the whole square equal to 25. But and look at the direct error here also. 200 minus 205 the whole square. It's again 25. So the problem here is that the error contribution due to this guy and due to this guy are the same. It's 25. If we take the direct error without taking square root. But look at this, if we take square root, if we take the square root of this guy, square root of 20, square root of 25, I mean, we already discussed that these numbers are between 0 and 1. But if we take square root of 20, square root of 25, here the error is like this guy, 0.279. But here, square root of 200 minus square root of 205, the whole square is a much smaller number. So what that means is, if you look at now how you are penalizing this guy more than this guy, as you should be, because small box mistakes should be penalized slightly more. Otherwise, they will not be accurate. So for this reason, the original YOLO paper, they just started taking a square root. I'm pretty sure you could have taken, instead of square root, cube root, you could take other powers, but for whatever reason, they stuck with this square root. So that is a basic basic theory behind YOLO. Although it's basic, we spend quite a lot of time. Now what we can do is we can implement this YOLO for a simple problem statement where I have written a code for implementing YOLO for detecting suspicious activity like theft at a supermarket. So what I'm going to do is I will share the code with you block by block so that both of us can run it together. So the first part is simply importing the libraries. So CV2, which we had already done earlier in the OpenCV part. So OpenCV, NumPy. So Ultralytics is the company that has pre-trained YOLO models. So we are using that model. And just a second, let me just. And then we have one thing called MediaPipe. MediaPipe is by Google. It's mainly for pose estimation. So you might have seen videos where the different joints are estimated and you draw lines so that a human can be converted into like a skeletal format. So we need these 4 libraries. So I'm just sharing. I can share this entire code with you, right? I hope that's okay. So I'll just download. Okay, so I have shared the code file with you in the chat, and you will also need one video. That video also I'm sharing in the chat. So the video is this. Can you see the video? Can you see this video of some test happening in some school? I'm sharing my entire screen, right? Okay. Thank you. So this is the video where somebody is stealing. And what we are trying to get is something like this. So when the person is moving in a certain way, it has to detect suspicious action. I mean, here it's a direct theft is already visible. But if we were to train an algorithm to detect this, how would we do this? So that is what we are going to do. So just open the code file. You can directly try to run it, but I'll anyway walk you through it one by one. So we are using YOLO V8 Nano pre-train. So YOLO version 8, N for Nano, .pt for pre-train. So it's a pre-trained model. We are not training it from scratch, right? Then, as I said, we need the MediaPipe from Google for detecting poses. So MediaPipe .solutions.pose. So because they have other than poses, they have many other models also, but we are taking the pose model. And then this MP drawing is a variable that I have defined for drawing the nodes and drawing the lines using media pipe. You know that for drawing, we can also use OpenCV, but here for this particular drawing, we are using the media pipe provided library, provided functions. Then for opening the video, I have provided the path here. So what you can do is you might have a local folder in which you are running all this, right? So go to that video. So here my video was over here, shoplifting or something. Yeah, this one. So what you can do is in VS Code, right click that, copy path. And then once you copy the path, you just paste that path here. Then you should have the path ready. So here what we are doing is it's cv2.video capture of the path. But instead of path, if we give cv2.video capture of 0, then it will detect me. So here I can show it with my face also. Let me just do that. Cap equal to cv2.video capture of 0. And then here I'll comment this. Now this means it will directly, and I don't want to save. So I'll skip this part. I'll skip all of this. This I will run, and I don't need to make annotation. So, I mean, I don't need to save the annotation. So this I will skip. So this now, can you see me? Can you see this annotation? So basically, now if I'm raising my hand up, it's saying suspicious, hands up detected. But if it is down, it says it removes that. So basically, and if I stand up, the same thing, it can detect different poses, right? So what I have, the code logic that I have written here is, if the coordinates of my elbows is, of the wrists are above my shoulders, that means it's a hand up posture. It's slightly suspicious. So let me show you the logic part here. So I have nose, coordinates of the nose, left wrist, left shoulder, right shoulder, then both hips and both knees. So that way I have a full anatomy of a human body. And then for hip, I'm calculating the average hip position. I don't care about left or right. So I'm just dividing by 2, summing the left and right hip and dividing by 2. For shoulder also, I don't care about slight tilting in the shoulder. So I'm dividing by 2. For knee also, I'm doing the same. Then what I'm saying is, if the left wrist and right wrist are above the nose, like this, not the shoulder, above the nose, it can be anything, like it's just a human engineered logic, not the best of logics. If it's above the nose, it means hands are up. So then hands up detected. It could be a suspicious posture, right? Because usually people don't put their hands up if they are shopping in a shopping complex. But this is not to say that this person is stealing something. It's just suspicious activity flag. Then crouching is if my torso, if I'm sitting in a crouching position, right? So crouching is like this. If somebody is crouching, then in the image, the Y coordinates of the dots corresponding to their hip, two points of the hip, it will be very small compared to their torso. So if the hip is much smaller compared to the torso, then that is suspicious. Maybe they are crouching. So that is what I'm putting here. So thigh length is much smaller than torso, it's crouching. Similarly, it's lying down. If the shoulder and hip are along the kind of the same line, so if the Y coordinate of the shoulder and Y coordinate of the hip are very small, if they are close to each other, and if the Y coordinate of the knee and Y coordinate of the hip are along the same line, and if the Y coordinate of the knee and Y coordinate of the shoulder. So if somebody is lying down, their knee, hip, and shoulder will all be along the same Y coordinate, similar Y coordinate. So that is the logic here. Then for crawling, it's crawling will be like if somebody's head is a bit high, like swimming. So their knee and their hip will be along the same line, but their head might be slightly above. Then in that case, it's crawling. Then there is falling. Falling is anyway not suspicion, but it's basically activities. Then here I'll put back the video instead of my face. So I'll comment this and put this and just run this. So just try running this code. Just let me know if you're able to run the code and get any output at all, or if it is showing some libraries are missing. Most likely for your case, this library will be missing. MediaPipe, I don't think we have installed it before. So just check that. And what else? Okay, here I will also save the output. That will be better. So save the annotated frame. So basically in the image, in the processing, right? YOLO is not processing video directly. YOLO is processing it frame by frame, because as you see from the algorithm, this whole bounding box detection is happening for image, not for an entire video. So image is, video is split into frames. You calculate frame by frame and you stitch it back to create the MP4 video. So this MP4 video that I have here is something that I stitched back from the frames that I think it's gone, but I can show you another one. Yeah, this one is like a basketball game. You can estimate the poses. There are many things that you can do. You could do for security surveillance. You could do it for self-driving car, not the pose, but the object detection. You could do it for any cases where there are like sports analysis. So if there are coaches who are analyzing the positions or body postures of their players, they can do faster and long-term analysis without sitting down and watching a lot of footages. So these things have wide range of applications, and processing this also not very difficult. So here, as I said, YOLO is real time. Of course, it's real time, but this entire video is also like what few seconds, 13 seconds long. Plus, I am asking the YOLO to do some more annotations. So that is the reason why it's taking a few seconds for this processing. Right now, yeah, this processing is finished, I guess. And then I have to quit, press Q to quit, and just release the capture, and then the file should be ready. So now the file should be ready. So you can see that, the person, when the person has, so I'll just pause at some timestamp. See, crouching is detected. I don't think this is technically crouching, because I think this is a mistake. Crouching is when the person is a bit more lower. Yeah, right now it's crouching a little bit. This is crouching, and what else is there? Lying down is not there. Yeah, only crouching is there. There is no, in the code, there is no reference to the YOLO output, is it? Oh, you mean the YOLO output that we discussed in the lecture? So the output in the code is directly, so what we are doing here is, we are capturing frame by frame, and this variable, this results variable is where the YOLO model is giving you the results. And from that results, we are picking out the annotated frame. So yeah, so this annotated frame will capture the results, and we are then adding it on top of the existing frame. So this annotated frame, and then annotated frame is added as a text, and it is also added as the bounding rectangle. So this, just check out for this variable, annotated frame variable. I think our webinar has, our lecture has went a bit more than I expected, but I hope it was worth it. I hope you understand YOLO very deeply. I plan to carry out one more lecture on YOLO. That will be next Monday, and we will be discussing about building a little bit more interesting and useful applications using YOLO, which we can also host it as an online, either as a web application or something like that. So in the next lecture, we'll also discuss a bit about differences between the original version of YOLO and the later versions of YOLO. Although the exact architecture of the latest versions of YOLO are not, I don't think it's publicly accessible, but I'll discuss as much as it's publicly accessible. We can go through that. Not in this much detail, because the basic architecture of YOLO is still what we discussed in this lecture. For those who want to access to our pro content from this course, because this lecture is part of a course called Hands-on Computer Vision Bootcamp, you will have to sign up for that. But otherwise, you will get access to the video recording, which I'll be uploading. So thank you so much, everyone. I really enjoyed today's lecture, and I hope you enjoyed the same. And please try the code and try it for different use cases. It'll be so much fun. And YOLO actually has real-time, like actual industry applications. So last week, two founders who are running kind of big startups messaged me on LinkedIn saying that, so I had posted some posts about YOLO on LinkedIn. So seeing that, they also messaged me saying, actually, they are implementing YOLO only in their actual pipeline, industrial pipeline for security surveillance. So this is something that is not just for academic interest, right? This is actually having industry use cases. So thank you so much. So we'll meet again on Monday. See you then. Take care. Bye.
Today, we are starting a new module on Roboflow. So Roboflow is an amazing platform where you can build end-to-end computer vision applications, starting from creating data set, annotating it, splitting it automatically into train, validation, test, and then using it to create different versions of the data set, then selecting whatever model you want to select to train on this data set. And if you want to take a pre-trained model, you can do that and fine-tune on the data set. And while fine-tuning is going on, you can see how the accuracy is progressing with epochs, with dynamic graphs. And then finally, once the model is fine-tuned, you can test your model and you can also deploy it. So it's a very nice platform for building end-to-end pipelines. So I first recommend everyone to go to this website, roboflow.com. So we'll be building this together. So there are parts of today's lecture where it's purely about image annotation. So since I'm just one person, I won't be able to annotate it alone. So I will need your help. So I will be sharing the link also, and I'll tell you exactly what to do. So first thing is sign in using your Google account or your GitHub account. I have already signed in using my Google account. So in today's lecture, I thought we could do a few things. First is discuss how exactly to build a data set, annotate it, etc. And if we are building a object detection pipeline, we know that the data set could be frames of a video. The data set could be distinct images. And then the labelings would be the boxes, bounding boxes. So let's say we had a video that looks like this. So I have a video here called volleyball. Can you see this video screen? Can you see this volleyball video? So basically this is just some random volleyball game. But look at the, these advertisements. So let's say I am an advertiser and the purpose of me sponsoring an advertisement in a player's logo, I mean chest, or let's say an advertisement that is over here, like you can see some advertisements in these boards, this Mikasa. So the purpose of these advertisements is maybe maximum screen visibility when you are projecting it into the screen, like when somebody is watching live in a TV, right? So as an advertiser, my goal is to optimize, or my goal is to see at least whether my brand logo has been shown for X percentage of time of the screen time, and how much of the screen area was my logo occupying. So although this logo is physically big, when you are actually watching on the screen, maybe this player's, this chest logo might be actually bigger for the viewer. So for advertisement analytics, let's say you are a company and a client comes to you asking, hey, I would like to have some analytics of the your particular volleyball game so that I can analyze which type of logos are getting projected the most. The first and foremost task for doing this is to have a object detection model where the objects are these logos themselves, right? So the first thing is we need to convert this entire video into different frames, and those frames we will convert into a labeled data set by drawing bounding rectangles, and then that we will use for training maybe a YOLO V8 or YOLO V11 model. And then later, if we upload a new video, we can, let's say, hopefully we can get an annotation on that new video, right? So for simplicity, what we will do is we will only target two logos. One is this Maeve logo. This I hope you can you see this red color logo? Anyone in the chat, can you please mention this this player's jersey logo? That is the first logo that we'll track. Second logo is this over here. This one, this Mikasa logo. Sometimes it's kind of blocked by people standing in front of it, but only two logos we will track, okay, just for simplicity. Now we could even make it even simpler just by tracking one logo. Maybe we should try that. But in any case, the first step in this whole process is converting the video into frames. So you don't need an external software for this. So what I'm going to do is I will create a new project in Roboflow. So new project, and then it's an object detection project, and I will say volleyball logo is the project name. And here I want to detect logos. I'll just type logos. Doesn't matter, whatever we can type. Right now I'm on a free plan in Roboflow, so I don't think I can create private projects yet, but that's okay. These are not very high stake project anyway. So this creates an empty project. Now on the left hand side, you can see a bunch of options: uploading the data, annotating it. Then this data set means whatever annotated data set you have created, you will see that. Versions is different versions. You can create different versions of your model. And then analytics will show you as the model is getting trained, it will show you a few things. So we'll see all of that. So first step is upload data. So I will upload, click and select file. And I will go to this video. So here I'm uploading the data set. So first, what I'm going to show you is a simple pipeline which does not work. What I mean by that is a pipeline which does very well in training but does poorly in testing. So this video is around, if I'm not wrong, around 45 seconds. So if I pick 1 frame per second, I will have roughly 46, 47 images, right? So here I'll have total 47 images, depending on the frame rate. So Roboflow allows you to pick whatever frame rate you want. If you pick a large number of frames per second, the total output will be very, very big. And here it will be vice versa, right? So I'll pick 1 frame per second instead of anything else. So I'll have totally 47 images. And then based on this frame rate, now Roboflow is extracting the frames from this MP4 video. And then after extracting, we'll upload it into this Roboflow server. Don't worry about doing this with me right now, because I will anyway share this project workspace with all of you so that you can all assist me in doing the annotation. Exactly like how, let's say we are all working in the same company and we have a huge data set to handle. So a lot of data to be annotated. We'll be splitting the task among ourselves, right? So exact same thing we'll be doing today. So I'll tell you what to do once this uploading is finished. And meanwhile, I want to show you one more video. So this is another video of like, this is like a YouTube short. I'm not sure why this is not opening. Okay. I'm not sure why this is not opening. It was playing before, but we'll figure it out. But that is a video where there are a bunch of chocolates, and I want an algorithm that annotates chocolates, different chocolate brands with a bounding rectangle whenever it appears in an image or in a video, right? Okay, so here Roboflow is uploading the images. This is pretty fast. And once it is uploaded, it will show that 47 are not annotated and 0 is annotated. So which means I'm yet to start annotation. So first I will show you a sample annotation for 1 or 2 images, and then I will invite all of you guys to annotate with me so that we can together finish this very fast. Just give me one moment to finish for this to finish uploading. All right, so uploading is completed. And as you can see here, these are the different frames. So far, it's easy. Now here you can see a few options: label it myself, label with my team, auto label the entire batch. So auto label is if you have a model that is already trained to predict the bounding rectangle for this case, you can use auto labeler. Otherwise, here is an option: hire outsourced labelers, which is Roboflow themselves will assign people to label our data set at some small cost. So what I'll pick initially is label myself. Okay, so here I'm creating a labeling job. And initially you can see that all of them are assigned as training data set. So click any image. This will open just that image individually. And we don't need this. All we need to do is the following. This, you see this rectangle option? Just draw a rectangle around the logo. So let's say I'm only interested in identifying this MAIF logo, no other logo, okay? And then here I will name it as, yeah, just logos. This default name is enough. Now I'll just save. So what happened now is one image was labeled with the bounding rectangle. So if I go back, here you see annotated 1, unannotated 46, correct? Now what I'll do is I'm going to add all of you into this workspace. So let me go to workspace settings, team members, and copy. I'll make all of you admins. So just feel free to join this workspace and follow the exact same annotation which I just showed you. So I'm just pasting the link in the chat. Let me know if any of you find it difficult to, actually only 3 invites are possible here, I guess. All of you cannot join, but whoever joins first can help me annotate. And meanwhile, I'll annotate a few more data sets. So feel free to join with this link. I'll pick another image to annotate this one. So here also there is another logo. So just draw bounding rectangle and press enter. So the logo will be annotated. What if I wanted to detect 2 logos? That's also interesting, right? So let's say I wanted to detect the Mikasa logo also, this guy. This Mikasa logo. Then what I can do is draw a bounding rectangle. And then here, instead of this, just maybe type Mikasa or something, and then save. Then you can see that the class of this changed to Mikasa. I can add more classes here, I guess. Okay, not yet. If I go to a new image now, if I go here, and if I search, if I select Mikasa, now I have 2 options, either to assign logos or Mikasa, right? These 2 options are there, you see. So I'll select Mikasa, and logos, I can maybe rename the class name logos. Now I can rename to something else, like the name of the other logo. All right, so now whoever has joined the team, let me check if anybody was able to join yet. Okay, I can see that 1, 2, 3 more people were able to join. Others can't join, unfortunately, because I'm on a free plan. So what you guys can do is, whoever joined the call, whoever joined the workspace, so just go to this annotate section, and then please help me annotate those with logos. So here there are no logos. Okay, I don't care about other logos. So let's not annotate all these logos. Let's ignore that. Let's only annotate those 2 logos, Mikasa logo, and then this the other one, this MAIF. Okay, so since this is unannotated, I will just call this as MAIF. Save. Then go back. So then now I have the classes are mentioned somewhere here. I'll randomly pick images. So feel free to annotate along with me. And ignore these images where the target logos are not there, okay? So let's not waste any time on that. Okay, I guess we have annotated a few, unless you guys have missed any. Can anyone confirm, whoever joined the workspace, are you able to annotate? Did you figure out annotation? Can you mention in the chat? Okay. So please help me annotate all of this so that we can wrap this up pretty fast. So there are 11 annotated, and annotated is 36. So I'll let you guys annotate on the go, but I'll just move forward. So please do annotate yourself in this data set, but I'll move ahead with whatever is annotated so far. Okay. So see, the annotation, the rectangle annotations are visible here. Now what I have to do is, in fact, now there are 3 classes, logos, Maeve and Mikasa, but I'll add these 13, annotated 13 into my data set. So train, valid, and test. So here I can say split images between train, validation, test. Automatically you will be splitting, but this is such a small data set that there is nothing to validate. So, but I'm adding nevertheless. So I just added all these into train, test, train, val, split, train, val, test, split. Now I have to define, so data set, whatever we created, you can see here, and you see the label. This is training. This is randomly assigned, by the way. Train, this is test, train, this is validation. So test data will never be exposed to the model. It will be only exposed at the end. But train data and valid will be used. I mean, valid will be used for hyperparameter training. Train data set will be used for parameter training. And here in this versions, what you can set up is a pipeline for what all kind of pre-processing you want to have on your data set. So here there is auto orient already added, resizing. So every image is resized into one single size that is added here. I can add another pre-processing step. So for some of these pre-processing steps, I have to pay, but some of them I don't have to pay. So let's say this grayscale, I don't have to pay for it. So I can just apply grayscaling. So these are pre-processing steps added so that you let your model learn various things. So if there is a random rotation or random cropping, for example, here in the augmentation, I can add an augmentation step like, let's say, rotation. So that, and I'll keep this some 10 degree or something. So you will augment the data set by creating different versions of it. And I can increase this to maybe 16 degree. And I can add another augmentation, perhaps noise, adding some noise. See, noise grains. And I can again add some hue effect. So these are some augmentations to create new training samples, which will help us. I guess this is enough. And then continue. So maximum version size, I'll pick this default and then create. So now a version of my data set is created, all right, with augmentation and data pre-processing applied. Okay, so my images are ready. So now there are total 31 images. So the reason why this training data set has now increased to 27 images, previous I think it was 9, is because we did augmentation. We increased the training data set size by augmenting, by rotation or grayscaling or some noise addition, etc. Now we can train a model on this version of the data set. So select custom train to select the model which you want to use. So custom train. And here you will see different options, detection transformer, Roboflow themselves have some models, YOLO V11, and then here you see some of your other options for YOLO. What I'll do is like, I'll just pick the Roboflow 3.0 model and continue with it. And then there is 2 options, fast and accurate. Maybe initially let's go with fast option and let's see what we get. Okay, so I'll click fast. So these different models, these last 3 models are not accessible right now. For that, we have to upgrade to the pro plan, but on free plan, these 2 basic models are there. Let's go ahead with fast model. And then we can either do training entirely from scratch. So here, train from random initialization is exactly training from scratch. So weights are random numbers, and then you start from that. Or if we have our own previous checkpoint to start from, so checkpoint meaning if we have a pre-trained network, we can start the training from there. Or if we had already applied some training before, we can start from that. Or we can start from a public checkpoint. So public checkpoint is this particular YOLO V8, I mean, Roboflow 3.0 model is trained on COCO dataset with at this level of mean average precision, 37.3 mean average precision. So this is the best model that this particular pre-trained model has. Now I can click start training. So now this download is basically downloading the pre-trained model, right? And here's training is starting. So while the training is going on, one cool thing that Roboflow gives you is you will soon now see the accuracy versus epoch graph. It will dynamically change in a few seconds. It should be visible in one of these tabs. I'll come to this analytics in a moment, but before that, let's go to this tab to see the training output. So here, do you see this? We estimate 15 minutes for this run once it starts. So we don't want to wait for 15 minutes, but we will move ahead and do a few other things while this training is going on. So you see this, this is exactly what's being shown. So this is mean average, two different mean average precision numbers. And this model performance is for the validation data set. And you see the mean average precision has already saturated. Can anyone tell me why is this the case? Why are we having such a high value of mean average precision? So here we are doing hyperparameter tuning also. The model parameter, like hyperparameters, is because we are having validation data set and parameters during the normal training. But anyone, please tell me why this mean average precision is so high. It's very difficult to get, right? It's high simply because we don't have that much data set in the validation data set. I think we have only, 3 images or something, right? So it's a very small data set. So it's not too, it's perhaps not too hard to get accurate predictions because we nicely annotated the data, and it's actually a good, those 3 images that is there in the validation data set, they are not difficult to predict images. So perhaps that's why this mean average precision is very high. But here you can see class loss, object loss, box loss, etc. So box loss is how far off the predicted box is from where the ground truth is. Object loss is the confidence score, like how far off your predicted confidence score is compared to the actual confidence score, which is 1 for an actual object. Class losses here in our case, we have actually 3 classes. We should not have decided, design 3 classes. It should have been 2 classes, but anyways, that's not a problem. But that is the class loss. And within the object that is identified, among the 3 objects, among the 3 classes, which one it is. So when I go back to now annotate, I guess you guys are yet to annotate new images, but that is fine. Now let the training continue here. All right. And meanwhile, I'll show you one more thing with how to use pre-trained models. So if you go to Roboflow, if you type Roboflow Universe, you can go to this website where you will see a bunch of popular models along with data sets, right? So here, if you scroll down or even if you search chocolate, you will get some models and data sets that are specifically meant for identifying objects that are chocolates. So I will select some random model, random workflow or universe here. So this one has 492 images. So these are the images, and every single one of them, I think, are annotated, if I'm not wrong. So yeah, all of these have annotations. You can see that every single image, if I click, every single one of them have these bounding boxes. So there are multiple bounding boxes per image. Now, what we can do is we could try forking the data set, generating the version, and click custom train. Or I have already downloaded the data set. So I have a data set over here in my local folder. So here you can see train test valid split. And these are data sets where you can see there are images and labels. Images are like chocolates, like these. Okay. And labels are these, the bounding rectangle and the bounding rectangle coordinates and the height and width and the class. Class is 0, class is 1 here. So what we could do is we could create a new project in Roboflow. So just click new project. In fact, I do have the chocolate project already, but I'll anyway show you from scratch. So type chocolate detection, chocolate, and then this is object detection, create public project. And then I just need to upload that folder. So click select folder, go to chocolate data. Maybe I'll just upload this train data folder. That's it, no other folders. Then automatically I can split it into train test valid. So just use half, like one small portion of the entire data set, because train test valid, the big data is like, it's too big for me to upload and train. It'll take me so much time. So I'm just uploading one folder, and that folder itself I'm splitting into 3. So train is 70%, valid 20, test is 10. And here I can move this and adjust how much I want each of them to be, but this default is good. Now continue. So now we are uploading the files appropriately. And you will see that these are already annotated because I also uploaded the labels. So labels are here. These TXT files are basically the labels. So Roboflow automatically identifies those. And here, if you open, you can see that there are bounding boxes already drawn. I think we should be able to adjust the bounding boxes if need be. Like I can adjust this if this is how I want it to be. But anyways, I'm not going to do that. So we get nicely annotated data set from Roboflow universe itself. So now this data set we can use for training our model. So go to versions. All of this is fine. I'm not going to add any pre-processing pipeline. I mean, any extra things here. Augmentation also I'm not adding. Create. So this is the version of the data set that I'll be using now. And then custom train. So click custom train, maybe again Roboflow 3.0. And then this time I'll pick accurate. I don't want this to happen fast, but I want good accuracy. Continue. And then same Coco data set. So pre-training happens on Coco data set. Then start training. So right now that pre-trained Coco is being downloaded, and that will be used to start the training. So while this training is going on, let's go back to our volleyball project and see what's happening to our training. Yeah, so this volleyball training has been done. It just finished a few minutes ago. Mean average precision 99.5, suspiciously high. Precision is high, recall is very high, but we have to use what we have, right? Now we can try this model to see whether predictions happen very nicely or not. So click try model, and here we can upload. So what I'm going to do is I will go back to my folder and open the video of the volleyball game and pause it at some particular, yeah, I'm pausing it here. Okay. And I'll take a screenshot of this particular screen. And then come back to Roboflow and let's upload this particular screenshot. So now here you see there is a text that says getting prediction, and predictions, there is no prediction right now. I can try reducing the confidence threshold, and now there is a prediction that has come, you see. So the model is not so bad after all, right? This MAIF logo has been detected with 17% confidence. I could reduce the confidence score a little bit more. Now, so this is for an individual image. So this is a new screenshot that I uploaded. This exact frame, it's unlikely that when we selected 1 frame per second, this exact frame, it's very unlikely that it was part of the training data. Now what we can do is again go back, try this model, but in this try the model, we can upload a video and see what happens. So go to the data set upload the entire video so that we can get a frame by frame processing. And I don't want the 50% threshold. I want confidence threshold to be low because I don't think the model is that good. So I want the bounding boxes to be identified, even if the confidence score is very low. All right. So here model is being loaded. This time it will take time because there are so many frames. If we want this to be fast, one thing we could do is go back to video, open the video and just select a subsection. So let's say starting from 14 seconds till maybe 20 seconds. So I'll take a smaller portion of the video from 14 seconds to so that I'm not uploading a giant data set for inferencing. It's much smaller, then done and new clip. Version 2. Okay, so this is my smaller data set. Okay, by that time, I think this has finished detection. I'm reducing the confidence score to 9%. And let's play this video. Okay, before playing, maybe I'll download it, or downloading is not there. So you see this, you see what's happening. So confidence score I had reduced to 13, 14, 15%. So this is saying it's MAVE. But clearly this logo, I hope you can see the annotation, right? Can anyone mention in the chat whether you can see the annotation at all? Or is it too small? Because I tried increasing my, screen size, but okay, I hope you can see this. All right, so this is shown as MAVE, but it's not MAVE, you know that. And let's see where else the model is making a mistake. Yeah, here I thought I saw 2 logos that were detected. So here Mikasa was detected at 23% confident. Pretty good, right? Pretty good for a very bad model. We did not train it for too much data set. And here, hopefully something will be detected. If I reduce see here, it is detected as logos. It's very good. Like if I decrease the confidence, some other logos might be displayed. Yeah, see, quite good, right? I'm positively surprised to see that such a quickly fine-tuned model is able to detect some logos in this video. Very, very cool. See, Mikasa is getting detected. So I'm already happy with the model. Let's go back. I don't want to see too many things now. Now, one thing we can do is this model, we can evaluate. So what we could do is if you want to, okay, real time in browser. So I just want to see in browser what it shows. If there is a logo on my chest, whether that will be detected or not. Let's see. And then there is also option to download the weights. So the pre-trained model, fine-tuned model, we can download. And in the previous lecture, you guys had seen how exactly to use the pre-trained model weights in a new model. We could also deploy it locally in our own server. That's possible. So, okay, here I'm going to turn on the camera in this browser, and I just want to see how exactly like I have a logo on my shirt. I'm not sure if it's getting detected or not. So I just stand up. Yeah, I don't think it's getting detected. It's anyway not a MAVE logo. Then if you want to try this on a mobile phone, you can open the same link on the phone, right? So it's pretty cool in that way. So these are the main things about model training. And here, once the model is trained, if you go to this models, it will show you the different models that you have trained on the same data set and its performance so that you can select whichever model you want to select. All right. Okay, there is a question. Can you please elaborate on the data privacy and licensing aspects of Roboflow? So I'm not sure about the data privacy part. You will have to read their documentation. But as far as licensing, I think if you upgrade, right? So I guess your question, Mandar, is if I train a model in Roboflow and if I download the pre-trained weights, can I use it commercially or not, right? I guess that's your question, no? Yeah, so I think we can check that. I'm not 100% sure, but my understanding is that the whole value proposition of Roboflow itself is that, like, making it easy for teams to build and deploy models for their own purposes, not just for educational purposes, but for actual commercial purposes. But so my gut feeling is that I'm pretty sure they, at least if you are subscribed to their, their pro plan, you can have privately hosted things. Which you own, the weights ultimately you own, but we can check that. One more thing is, okay, let's go back to the chocolate training. So chocolate training has been finished. So so this I'm happy to see. Mean average precision is 57.4. I'm happy to see this because this is how things are supposed to be. You know that the YOLO model originally, when they proposed it, its mean average precision was 67 or 69%, compared to like faster RCNN, which had 76 or something. And here, okay, it's still updating. It's still 17 minutes are remaining. And meanwhile, I can show you one of my pre-trained, already trained chocolate project inference. So let me just open the workflow. So here there was one project. Yeah, this one I had already trained. So same process I went through, and this is now the trained model. And to this trained model, see here. So this is the place where we can play with the model's different parameters, upload a new image, upload a new video, and see what the prediction is. So these are now the samples from the test. Okay. So here, if I select it, this annotation is not my annotation which I gave. This is the annotation that the model is predicting, and it's pretty accurate. You can see 67% confidence. And here, if I decrease the confidence, maybe if some other, see, there are some more rectangles that are being detected at a lower confidence. Maybe some more are there. But in general, let's keep it a little bit high. And similarly, you pick any data from this test data set, it is showing the rectangles. If you want to see more rectangles, just reduce the confidence score. Okay. Now here, let me try uploading the video which I had, this chocolate video. I hope this is not corrupted. Yeah. So this is some random YouTube Shorts video, and you can see how well the model works. So here, loading the model means we are basically frame by frame performing the inference. And once the inference is done, you will see frame by frame the coordinates of the bounding rectangles that are predicted in this box. So let's wait for a moment. And I just want to figure out a way to share this with you guys also. But anyways, so here you see this is a video that is being played, and frame by frame, the chocolates are being detected. All I need to do is like decrease the confidence threshold, so that if you want this chocolates also to be detected, just reduce the confidence so that all the possible chocolates are detected, even at low confidence. So if 3 chocolates are detected in one frame, you will see 3 rectangle coordinates and their confidence score and the class code, just like how we were performing object detection in YOLO. But this is very cool, right? I really, really enjoy it. It's such a simple workflow. Now imagine we want to set up the same thing on Google Colab or Visual Studio Code. It's much more painful, but at the end of the day, same thing is happening. So here, Roboflow has abstracted away a lot of coding which you will otherwise have to do, so that you can focus on the, I would say, engineering aspects of the model. So think about the data set, how good it is, etc. Think about which model you are using. Think about fine tuning, or think about pre-training and inferencing. So just the main things. The rest of the syntax of the code, everything is abstracted away from you. So that's one reason why I really, really like this. One more thing we can do in Roboflow is building something called as workflows. So let me go to the workspace. So here, click workflow. And in this workflow, we can build an actual workflow and test it and also deploy it. So click create workflow. Let's close the tutorial. Okay. So inputs, model, output. So in the input, for the moment, let's say my input is an image. So here image is selected. The input can be image or video, but for processing video, I'll have to either deploy this locally or deploy it on a server, or help Roboflow itself to deploy the model. But for that, I'll have to pay. But so because of that reason, for now, I'll just keep it image. So image is the input. Okay. Now let's say I want to perform some task. So click add model. And here, if you look at the capabilities of the model, so there are model type, or there are my models. So these are the models that I have trained myself. There are public models, so random models classified according to maybe its popularity or whatever. But here I'll select based on model type. So there is object detection model, instance segmentation model. So instance segmentation is individually it will detect classes, separate objects within the same class, single label, multi-label. So everything, classification, segmentation, object detection, everything is there. Maybe I can select instance segmentation model, something like this. All right. And then click add model. So this will take us to here. We have to add a model. So let's go to public models, and maybe YOLO V8 segmentation we can do. So this is YOLO V8 Nano pre-trained, or we can pick YOLO V11. Maybe let's try YOLO V11. Why not? And click add model. So now the model YOLO V11 has been added. Next, outputs. So output is simply model predictions, and I'll show you what exactly the model prediction look like. So three things we have added. Input is an image. Output, the model is YOLO V11 segmentation model, and output is the model prediction. Now let's test the workflow. So for testing the workflow, I have to pick an image. Video won't work again. So in the image, I'm going to upload the same image that I earlier used, the screenshot, this one. Okay, so I'm just uploading it and run. So now this is inferencing. Training is not happening, simply inferencing on an individual data point. And here, when you see the preview, you will be a bit disappointed because you will not be seeing the bounding rectangles yet. You will simply be seeing the output numbers. Now I'll show you, I'll tell you exactly how to bring the bounding rectangle also into the picture. See, now this is the model output, the rectangles and their individual coordinate values. Not very exciting, right? This is useful, but this is not what we were expecting. So how do we fix this? How do we have bounding rectangles annotated on top of the image? For that, we will have to add a few more elements. So first, I'm going to delete these outputs. I don't need these output numbers. I want something else. So click add block and click visualization. And what I want is, in fact, not bounding box. I actually want segmentation visualization, right? Mask visualization. This one, apply a mask over detected objects. And now in the mask visualization, the image to visualize on is the input image itself, and predictions are these. Color palette, all of these are fine. Test, then let me test the block. So hopefully we should be able to see the mask, the segmentation mask. Ideally, it should not take too much time. As you know, YOLO is supposed to be super fast at object detection. Maybe for segmentation, it's a bit slower, but not necessarily this slow. Even when we implemented in Visual Studio Code, you remember it was not this slow. But anyways, let's see what we get at the end of this. But I also want to check how much my training has progressed. So mean average precision has improved a little bit. So this is still the training on the chocolate data set. So what I showed you, the results was the training which I did yesterday. This is a new training. And if you have any videos of people eating chocolate or whatever, just feel free to share with me. So here, this is the inferencing. If you open this image, this is the mask that is applied. So segmentation has worked perfectly on this player, on this person. You see the violet purple color segmentation mask. What if I don't want segmentation mask? What if I want key points using a post detection model? Then I need to change the model. So here, instead of this model, I will, maybe I can delete this block and click this plus to add a model. And I want key point. So post detection is called key point detection. So key point detection model. Okay, let me start from scratch. So add model. Then yeah, key point detection models. So something like this, it should do. Then add model. And from public model, I'll select nano V8 pose, then add model. And instead of this output, I want visualization. So click this, click visualization. Then I want key point visualization. So yeah, this one, key point visualization. So that's it, right? So input is the image, model is the key point detection model, output is the visualization. Let's now test the workflow. So in testing, the input image can be the same, then test the block. Now it should run and hopefully show the person's different joins. Okay, there is a configuration issue. So image is the same. Key point detection model is correct. Then in key point visualization, image to visualize on is the input image. This is the predictions. And then test workflow. Run. Okay, so now let's see the output. Okay, some required box inputs are missing. So I'm just rerunning the workflow because currently it is not working. I just input the same image again. Okay, so I hope I am facing an error here, which looks a bit weird. Model prediction parameter. Let's do one thing. I'll start from scratch because this should not be hard at all. Workflow, custom workflow, or rather new workflow. Input will be image. So I'll add an image and then model is key point detection model, add model, and public model. And then output is fine. And we should add one more block. Then add key point visualization. And hopefully this should work. If not, we'll figure it out. So drop the files. And visualization. So meanwhile, I encourage you guys to do something similar. Pick any model. So this is similar to N8N. If you remember, we had a workshop a while ago on N8N, not in the current bootcamp, but basically it's like constructing a workflow using blocks. And it will have input trigger. It will have tools that you need in the workflow. Some tools will be AI tools, and then the output will be whatever you want to execute in another tool. So now key point visualization, I hope you can see this. There are like these joins and lines connecting the joins. This is basically like a posture detection model, right? So different key points of a human anatomy are being now highlighted in this color. I think this we can edit also, because currently the visuals are not very good. So in configuration, I can increase the thickness. So if I make this into 10 in the test, perhaps thickness should be different now, not here. In the data out, if I run once more, the line thickness should be now 5 times bigger. Instead of 2, it should be 10. So you can configure different things. If I run the entire workflow, that should work. So this is how you set up a workflow. And the good thing is this model you can run from anywhere. So what do I mean by that? If you want a model to run, this link I'm pasting in the chat, you guys can also check the model. Basically, it will open Roboflow, this particular link, and it will open the model in your browser. But if you want the video detection capability, you need to have deployed model on either your local machine or on your own server or by Roboflow. So here, if you click deploy, you will see a few options. So for images, that part is easy. You can deploy it in various ways. For video, either local server or in-app or command line. So command line, they'll provide you the options. But I tried deploying it locally by using Docker, but it was too slow, maybe because of my internet, that I decided against it. But deploying should not be that difficult. This is pretty standard process. And meanwhile, our chocolate, so training has been finished for our chocolate dataset. This is the final mean average precision, 69.3, 44.1, the precision. And then here we can try the model. So to try the model, I can upload the chocolate video, and let's see how good this model is, because this was trained with a different model. So perhaps the performance also will be different. You see, if I reduce the confidence, more rectangles will be detected with low accuracy because they are less confident rectangles. But here it's not a really good model. You can see that clearly it's missing out a lot of chocolates. But I'm happy because the training was too short. All right, so this is how the Roboflow workflow works. But in Roboflow, there are many other models also. It's not just object detection. You could use it for tracking trails. If you go to Roboflow Universe, you can see many different models pre-trained by different people and interesting projects in computer vision. So just go to this link. I'm just sharing it in the chat. Just go to Roboflow Universe and just have a quick browsing through these different projects that people have worked on. This alone will give you a fairly good idea about what all different variants of computer vision projects are actually being done by people. Many of them are regarding physical safety. And as I always mention in this course, physical safety using computer vision is a very big area to make money. If you ever want to start companies, it's a good, I know many successful startups who are operating in that space. AI for physical security, which also includes a component of vision. See this one, this forklift. These are all physical safety. Safety vest, this is physical safety. Hard hats is physical safety. It feels like many of them are here also. This one is physical safety. I saw one more. Logistics. And even this might be useful in like Amazon warehouse. Amazon robotics might be, I'm sure, implementing some sort of object detection and segmentation models. So check out this Roboflow universe for popular models and try just using you don't have to train it yourself. Just use the pre-trained model, download the pre-trained weights, use the annotated data set and see what you can build with it. Okay. So we'll have to wind up today's session is a bit early, but we'll have one more session on Roboflow on next Monday. So I'll see you guys all on Monday. But in the meanwhile, on the Discord channel, please post your questions. I will also be posting one assignment where you have to build an entire workflow. And if you want to collaborate with your friends, feel free to do that. If you want to work alone, you will have to painfully do the annotation yourself, but it's possible. In one of the projects that we did for a company, we executed it using Roboflow, especially the image annotation part. So we tried different models, but image annotation was purely done in Roboflow simply because it's so easy. Creating frames from videos is also so easy. So even for industry level projects, it's actually something that you can use for your benefit. So if you work with clients on vision related projects, Roboflow is a very, very good tool. In our experience, that has been the case. So thank you so much, everyone. We are winding up the lecture a little bit early today, but I'll meet you again after on Monday. So that will be the final lecture of this bootcamp. And I look forward to seeing your assignment submission. So I'll be posting about the assignment on the course dashboard by the end of the day. So thank you so much. I hope you enjoyed learning about Roboflow. I did. When I started using it for the first time, it was like, oh, wow, amazing. Really good platform for computer vision projects. And it's purely dedicated for computer vision. So Hugging Face has many other things going on. It has a lot of amazing computer vision models also, but it has other things also. But Roboflow is purely computer vision. So it's a great platform for all of you. So thank you, everyone. See you again soon. Take care then. Bye.